you have to click Do Not Disturb.
That's fine.
It's fine?
Yeah, that's what we want.
It's okay.
The question is, does he want presentation mode? Like does he have notes or anything?
I won't worry about that.
Okay. All right. Joe, don't invite me. Just
yeah. All right.
tell people QR code.
Yep. Good morning, everybody. Good morning. May I have your attention, please? Thank you and welcome to JuliaCon. We're really excited to bring the community to this beautiful city of Pittsburgh, a city where we ask ourselves, how many bridges is too many bridges, right? So we have a couple of quick announcements before we'll bring on our keynote speaker. So let's do this. So firstly, we'd like to thank our local partners, Carnegie Mellon and University of Pittsburgh. They've been exceptionally helpful in providing us both accommodation as well as this beautiful venue for the conference. We'd also like to thank all of our sponsors, without which JuliaCon would never happen. Of course, we're deeply indebted to all of our sponsors. And we also have 4 exciting keynotes for you this evening. So without further ado, I would like to invite Dr. Viral Shah to introduce our first keynote.
So folks, Preet has an accomplished background, and I'm just going to share a lot of that with you. So he was the CTO of Ansys, which is now a company that, as of last week, merged with Synopsys. And he's responsible for driving the long-term technology strategy there. Prior to that, he was the CTO of Schneider Electric, CTO of ABB, managing director at Accenture, director of HP Labs. Spent 20 years in academia as professor, chairman, and dean at UIUC and Northwestern. He founded 2 EDA companies, Axelchip and Binachip. He served on the board of directors of Cray, Cubic, and Turntide, fellow of the AAS, ACM, and IEEE. He's received a BTech in electronics engineering from the Indian Institute of Technology, Kharagpur, and an MS and PhD in electrical engineering from UIUC. In addition to this, I wanted to share a little bit about Axelchip, actually. So Preet, as I was reading your book, so Preet has an amazing book called The Innovation Factory. I highly recommend you to get it. And I think if you read the book, you'll see that the Julia Hub journey has been exactly how Preet outlines companies can be built about academia, government funding, venture capital, and customers. But interestingly, in your first company, Axelchip, Preet, you built the Match compiler, which was MATLAB for FPGAs, and we see I at least see a lot of parallels with what Alan and I did back with our work, focusing MATLAB on parallel computing, and out of all of that work came out Julia. So we actually share a little bit of the path that has brought us together here. So without further ado, please clap for Preet.
Thank you very much, Viral, for welcoming me here. I'm absolutely excited to speak here today. And the topic is on digital twins, which is a very, very interesting, exciting topic, very interesting from an academic perspective, interesting from a business perspective. And originally, when I signed up, I was going to give a talk as a CTO at Ansys, but now 3 days ago, I joined the executive leadership team of Synopsys. And so I'm going to speak, so I had to change the format of my slides to Synopsys last night. So the agenda is I'm going to first talk about the Synopsys Ansys introduction, because it's a really interesting thing that is going on in the industry, and I want you to know why these 2 large companies got together, right? And then dive into the technical topic of digital twins, how it is relevant to various industries like automotive, aerospace, energy, and so on. and then go into the core technology, right? So there's two broad approaches, data-driven approaches and physics-driven approaches, and sort of the hybrid approach which we do. And then I'm going to talk about some of the key innovations that are going on in this general area of digital. And then I will end my talk about the future of digital engineering, which is, I hope I can get to these things, because it is, I'm painting a picture of what's out there, right? And again, I'm honored to have people like Alan and Bob in the audience, because this is the picture that I'm painting on behalf of the ANSYS, Synopsys, Dassault, Siemens. We are all actually going in that direction. So I want you all to see where the world is headed, and I will tell you up front, Julia Hub is going to be a very, very important part of that journey. So that's basically the thing, that the future is digital twins, digital engineering, and what this community is building, Julia Hub, is going to be a most important part of that journey. So with that, let me begin with what just happened last week. So 18 months ago, year and a half ago, Synopsys, which is the leading electronic design automation company in the world with about $6 billion in revenue, decided to acquire ANSYS, the leading simulation company with about $3 billion. The question is why? In the world of electronic design automation, right, when you're designing an electronic chip, like the NVIDIA's Blackwell GPU chip with 300 billion transistors, that requires electronic design automation. I mean, when I was a professor at the University of Illinois in 1985, I used to teach students how to do custom IC design, where on an IC you have masks. You have a red rectangle, which is polysilicon, and when you draw a red rectangle polysilicon over a green rectangle, which is diffusion, it forms a transistor. Those are the two mask layers that if you do it. Now, with that technology, you could design maybe 100,000 rectangles, so 10,000 transistors. So early part of VLSI design was computer-aided design. You had to design the transistors, the layouts, and the chip. Then the world of automation came in, where you essentially took standard cell designs like an 2-input NOR gate, 4-input NAND gate, and you entered your design not in drawing rectangles, but you enter it at the gate level. And then you use a automation tool like a placement tool, a routing tool to connect it up, and that's how you generate the rectangles. Then the technology went to RTL synthesis using technology like design compiler, and you say, okay, now enter it at RTL, VHDL, Verilog, languages like Julia, right? And push of a button gets the netlist of gates, push of a button gets the rectangles. And then there was high-level synthesis, which is what I did when I was at Excelchip, right? Taking high-level languages like C or Fortran or MATLAB and generate the RTL, VHDL, get this and so on. So this is the world that Synopsys has been leading, right? All these semiconductor companies, the chips, when you design them from Intel, from AMD, from NVIDIA, from Broadcom, Qualcomm, so the top 200 companies that are designing chips, they use Synopsys or Cadence. Those are the two big companies that do it. So that's the world of electronic design automation. In the world of systems, when you are, I'm sure you came driving a car, or flying an airplane, or powered by the energy of a wind farm or a solar cell, or you are using some kind of a pacemaker, I hope not, but if you... So in all the industries like automotive, aerospace, energy, industrials, high-tech, and healthcare, that world uses, you need to design and you need to simulate. ANSYS is the leading simulation company. And so the combination is, it turns out that on a Boeing airplane, right, that is, now it is no longer only the airfoil and whatever, right? There's a lot of software that is driving the airplane stuff, right? On a Tesla car, there's 100 million lines of code on a Tesla car, right? So it's a hardware-software combination ecosystem. So the world is moving towards hardware-software systems design, right? And while Synopsys was focused on only the design of the chip, Ansys was working on the system, bringing it together. We are now going to help customers build silicon to systems. So that is literally why Synopsys paid a lot of money, $35 billion, to acquire Ansys last Thursday. So because of it, now essentially you have the number one EDA company, which is Synopsys. Number two is Cadence. Number three is Siemens EDA, formerly Mentor. Combined with silicon IP, when you design a Blackwell chip, right, you don't design all 300 billion transistors from scratch. You say, hey, I need a HBM design. I need a PCI Express. I need an Ethernet controller. Bob, all the technology that you built, right? These are predefined IPs. I need a GPU core. I need a CPU core. I need an ARM. All of those things you put together, right? So Synopsys is actually the number two silicon IP provider. Number one is ARM. Number two is Synopsys. And number three is Cadence. So, and when you're designing these chips, you need to have the electronic design automation, and you also need the IP. Now you combine it with systems. This is a very, very interesting combination, and it's today a $9 billion revenue company. We had our executive leadership meeting yesterday, and we are literally going to change the world to do silicon to systems. This is our vision. So in that vision, you will see that Julia Hub will play a big role, and hopefully I'll get to that point. So now the technical part of the talk. So this is about digital twins. What is a digital twin? You have a physical asset like an airplane, right? This is the thing that is there, right? Or the engine on an airplane, or the car, or the engine in the car. Whatever is the physical asset, that's a physical asset. And then you have a digital model of that thing, right, in the digital world. And so sometimes people say, oh, a digital twin is just a simulation model. No. It is a simulation model, but that model is connected to the physical asset through, I put some sensors on that asset, right? And I collect data through an IoT platform, et cetera. And there's two-way information flow that happens. So you say, here is an aircraft engine. It is getting overheated. Oh my God, it's getting overheated. What if I could cool it down? I put cold water here. I do oil there. So I do all these what-if scenarios. So I do those what-if scenarios on the digital world. I say, oh, I should put a mixture of oil and vinegar or what, some random thing, right? And based on it, you make the decision. You do it, and you do it in the other part, right? That's what a digital twin is good for. And those of you who I know have watched the movie Apollo 13, that disastrous thing that happened, right? When people were stuck up there, right? NASA created a digital twin model of those things and said, oh shoot, how do I going to bring those people back? I put oil, vinegar, this, that, etc. Did all those things on the digital model. If I did this, we'll bring the astronauts back. So the concept of digital twin actually came out of NASA, right? So this that is the origin, but this is kind of what digital twins are. So digital twins allow you to track the past, deeper insights on the present, and predict the future. If we can say, this airplane is going to crash if you don't do certain stuff. This thing is, so if you could predict that with high accuracy, you can literally solve the world. So it turns out that digital twins, even though it started with NASA stuff, right, is now used in aerospace, that aircraft engine, like GE's basically they do predictive analytics of that airplane engine, right? This is normal things, you all own cars, right? You're supposed to do tire rotation every 5,000 miles or kilometers, right? Why do you do that? Because statistically speaking, if you drive your car normally, right, you're doing this, that wear and tear of the tire will be such that if you don't screw it, change it, you will have a tire burst, right? You have to do an oil change every 5,000 miles. Statistically speaking, if you don't do it, it'll mess up. But practically speaking, if you look at Prith, I drive like a madman, right? My tire, if I don't rotate it every 4,000 miles, if I don't change my oil every 2,000 miles, my car is going to explode. This digital twin on Prith's car will monitor the oil pressure, my tire things, etc., and say, hey, it's time for an oil change, time for whatever. And if I can do this accurately, instead of that $400 million airplane crashing, I will prevent that crash. So that is why having accuracy of prediction of a digital twin in aerospace, automotive, manufacturing, buildings, oil and gas is so important. Now, digital twins has been used in different phases, right? So in the product design phase, in the manufacturing phase, in operations phase. Let me give you an example. GE engines, aircraft engines. You all fly planes, Boeing planes, etc. You have those little engines there, right? The blades going around and so on. So when GE engineers designed that engine, right? There are 52 blades on the engine. They have to have exactly that curve. So it's a perfect, ideal CAD model of that blade. Now you try to manufacture the blade using injection molding or whatever, that blade, which is such a beautiful picture with a circle and the spheres and so on, when you manufacture it, it's a slightly different blade, right? So now you have a digital twin in the design ideal world. Now you manufactured it, it has all the imperfections. So every engine of GE in the actual manufactured world is slightly different, right? So literally, if you could track every one of the engines, and that's what they'll really do, with some sensors, here is how I designed it, here's how I manufactured it, I can track how that engine will work. And now this plane is an Air India plane flying from Mumbai to Ahmedabad to whatever, and it's all the suits and whatever, flying into China, doing this. So that same aircraft engine on United Airlines, only flying between San Francisco, New York, clean places versus sort of Mumbai and Beijing, right? That airplane engine is quite different after 20 years, and then a bird strikes that engine, right? So now that engine is slightly different. So in the operations phase, even though you started with a perfect ideal world of a CAD model, in the operational world, it got all messed up, right? Because there's a little bend there. So I need to predict through the digital twin, the model of that aircraft engine in the design phase, in the manufacturing phase, and so on, and you can do it beautifully through the world of simulation, powered by Julia Hub, which is where I'm getting to. So now there are these sort of two broad approaches to digital twins. One is, you say, okay, here is an engine, right? And that I will put some sensors on the engine. I'll just measure the pressure, temperature, whatever, etc., on that engine, on this blade. If I could put sensors on everything, right? And collect a lot of data. And so if you collect a lot of data, it's just that time series data, pressure, temperature, etc., and you build a model, all the AI stuff that you see today, right, is basically doing that. Data-driven modeling, that approach is totally general. It doesn't care about the physics. You do structural physics, you do electromagnetic physics, you do fluids physics, everything can be captured by data. The trouble is, so it is very general, the trouble is it requires incredible amount of data to train that model, right? It's like million times of data. If you capture it, then you will predict exactly how that aircraft engine will work. The other trouble is, it will only train it based on what it has seen. So if I have seen his aircraft going from San Francisco, New York, going from this to this, etc., it will never be trained to go into the streets of Mumbai with all the suit and so on, or whatever in Beijing, right? Because it has not seen that data. If it has not seen a bird strike, it will never be able to model the bird strike. But the bottom part is, if you do simulation-based modeling with ANSYS mechanical, here is this model of an airplane wing. Here is a bird that struck it, right? With LS Dyna, I can model exactly how much it will bend and whether that blade got cracked or not. It's physics-based simulation. So that is, I mean, it's like the ultimate thing, right? Because physics doesn't lie, right? The world around us is governed by the laws of physics. If I say this plane is going to fly, it will fly. If Fluent says this thing is going to fly, if it's going to stall, it will stall. I mean, I kid you not, because it is so accurate, because the world is following second-order partial differential equations, Navier-Stokes equations, or Euler equations, or Maxwell's equations. That's what we do in the physics space. The trouble is, that takes a long time. You try to model a bird strike, right? This thing, bird is striking this thing, it's like 10,000 hours, right? Or should I need the result every second? I cannot. So then what you need is, you take that simulation model, you have to build what is called reduced order models. Don't do the simulation at the level of the 1,000 million finite element method, but you reduce those orders from 10,000 million to 1,000 so that you can run it really fast. So there are these two broad approaches, and where we have landed is you need to do hybrid. Take the best of both worlds. Do data analytics to do the sort of easy cases, and then correct it through simulation, right? So the intuitive explanation is the following. Suppose you had a bridge, right? And there's a 6-inch crack on the bridge. Statistically speaking, of all the bridges in the world of the last 30 years, right? When you had a 6-inch crack in the bridge, within 18 months, that bridge collapsed. Statistically speaking. That's what our insurance companies, State Farm says, hey, based on all the people who are driving cars, right? If you are male, you have this risk. If you are female, you have this risk. If you are a male who is crazy like Prith, you have this risk. So they are putting it in a bucket of a risk, right? That's statistics. So that bridge with that 6-inch crack would, statistically speaking, will crack after 18 months. Now, if you could put a sensor on that crack and you monitor the crack, and now use ANSYS simulation to do crack propagation. If I have a 6-inch crack on his bridge and I have 1,000 cars going on the bridge with all the stress strain that is going on, I will predict that crack will be 18 inches in 6 months. Pure simulation. Now, I actually monitor what happened to the crack in 6 months. If the crack is 24 inches, I say, oh, shoot, I have under-simulated, so I need to push it, right? Push that simulation. Or if the crack was only 12 inches, I need to under-simulate. So with simulation, I predict that, and then with the actual measurement, I bring it down. That is intuitively what is going on with hybrid. There is a lot of math with the famous professors here will know, but I'm just giving you the intuitive explanation of why hybrid digital twins work. So we have sort of put together at ANSYS, now Synopsys, this overall view of digital twin. So you have to start with the assets. The assets are the wind turbine engine, the car, the aircraft engine. You name the asset, and you put some IoT sensors on the asset. You collect a lot of data. You put it on the cloud, on AWS or Microsoft, whatever, right? Then you do data level analytics, which is what, as I said, most people, when they start doing digital twins, that's what. When I was CTO at ABB, CTO at Schneider, this is what I did to those companies, right? They have a lot of assets, robots, switches, transformers, and so on. I just created this ability platform or EcoStruxure platform, build the digital twins. So ABB could say, this robot is about to fail, and let me send a repair person to fix it, and if there's an accuracy. Then I came to ANSYS and say, hey, let's do simulation-based or hybrid, and we'll do the accuracy. So what good is this digital twin? What it is it allows you to create virtual sensors. So if you could put a sensor on every part of the blade on a G's engine, right? There's 52 blades, and all that blade, you got to put it here, here, here. You could analyze the heck out of that engine. What is going to happen? The trouble is, if you put all those sensors, that engine will not work as an engine, right? Because you're doing an invasive change in that thing, right? Or you have a large oil well, right? It's 5,000 kilometers of oil wells and so on, right? And you're putting a sensor at every meter, every inch, every whatever, right? You could do all kinds of predictions. Unfortunately, that is not real. So in the world, what you can do is you can do virtual sensors, meaning just imagine a pipe. The pipe has oil coming in from this side, and the pressure, temperature, velocity of that thing is here. Now, if I had a sensor after 1 meter, it would measure this, because through fluid simulation, I can predict, because, hey, this is a pipe, this is a fluid flow, etc., with all the turbulence and so on. It has this pressure, temperature here. If I had a sensor, this is what it would measure. But I cannot have a sensor, so I'm creating a virtual sensor. At the first meter, second meter, third meter, fourth meter, fifth meter, at the 100th meter, I actually put a sensor to say, hey, did I do it right or did I screw up? No, you screwed up, Prith. You need to correct it. So that's how you do virtual sensors. So to measure missing data, to perform what ifs, right? So here is this Apollo 13 sort of up there, screwed up, right? And so how am I going to bring it down? Right? I have to do, if I did this, oil and vinegar plus this, then this is going to work. So all those what-if scenarios you do in the digital twin, digital world, and then based on that, I make a decision, apply it. Do very accurate predictions. Hey, this bridge is going to crash. Today is Wednesday, July, whatever, 23rd. It will crash on July 28th. If you could predict that so well, my God, we could make a lot of money because you could avoid a lot of disasters. And explore the, hey, this thing flamed. When this Air India plane crashed, right? I mean, you have heard these things, right? Why did it crash? Oh, these things happened. You could literally do physics-based stuff to do all kinds of analysis because the black box recorders have measured. Then you combine it with physics, you could do amazing things. So that's where the power of digital twins is. So now let me talk about the technology. So ANSYS has the core physics. We have the leading mechanical solver called ANSYS Mechanical or LS-DYNA. We have the leading fluid solver called Fluent. We have the leading electromagnetic solver called HFSS and Maxwell. So we take each of these physics and we can simulate it with the highest fidelity. I mean, if I say this is going to crack, it is going to crack. I tell you now, right? But it requires a 100 million finite element points, right? It will take 10,000 hours. The trouble is that is too long. So what we have in technology is we have these reduced order models. So think of if a 1 million finite element problem, right? Basically, it gets resolved into sparse linear solvers. It is a 1 million by 1 million matrix with sort of some sparse elements. And now you have to solve AX equals B. That AX equals B is an order n cube computation, right? Which is taking you forever. Now, looking at that matrix, you going back to your math days of numerical linear algebra, right? There are these things called eigenvalues and eigenvectors and principal eigenvectors. So on that matrix, if I were to take the most important 100 eigenvalues, the principal components, that's 100 of those. Those things are the most, I'll take those 1 million by 1 million vector matrix into 100 by 100. Those 100 by 100 are the most important things. That's fundamentally what is going on with reduced order models, right? Now, instead of taking order n cube time, order 1 million cube, I solve an order 1,000 cube, which is much easier to solve. That's basically what is going on with digital models. So we take all the core solvers, build the reduced order models, and do all this funky stuff with hybrid digital twins. Now we have a flow. Now within ROMs, there's all kinds of ROM technology. Again, this is just to impress you. Some of you are in the audience. Hey, Preet is just not doing nonsense. There is technologies on linear ROMs, non-linear ROMs, static ROMs, dynamic ROMs. Okay, I have impressed you. So now, we have built this sort of thing, the Twin Builder. So there's just incredible amount of stuff that is going on today, and that's where Julia Hub comes in, right? So we have to take this model of a electric vehicle or a autonomous airplane or this wind farm. So these really complicated systems having hardware and software in it, right? And this combined ANSYS Synopsys stuff, right? And you have to do this model building for either brownfield applications. You have a stuff that is there, or for greenfield, right? How do you build the model? Well, I will come to that. It is actually, Julia Hub is a fantastic thing that we are looking forward to partnering with, right? Allowing reuse of existing simulation models with AI/ML. I mean, AI is actually changing the whole world with ChatGPT and others, but it is really changing the world in our area of AI/ML applied to simulation. Enabling scaled runtimes and driving a lot of ecosystem partnership with the likes of AWS, PTC, et cetera, et cetera. So there's stuff that is going on. So let me just focus on the system level simulation part. So let's say you're trying to design an electric vehicle, right? In an electric vehicle, you will have a motor, electric motor. You can actually model it in Julia, which is the high-level system level model. Now that electric motor is powered by DC power. I have AC power. What do? I well, take the AC into DC, so I need some converters. Or I take a AC into DC, need an inverter. So I do all this, I'm sorry, DC to AC need inverters. So I need a battery, I need a motor, and inverters. Then you need to have something that once the motor goes, that motor will connect with a gear, and then it will connect to the actual things, and that's how the car moves. So you could actually go in and model the motor, model all of them in Julia, and build a whole electric vehicle simulation model at a high level. But then he said, oh my God, this electric motor has these rotors and stators and all that kind of stuff. Will it really, if I apply this much voltage, my model says that torque will be this much. Is it really that much? Well, we go into Maxwell, which is ANSYS, right? And we look at the actual CAD model of the stator and the rotor and all those fantastic Maxwell's equations with all the partial differential equations, and said the torque will be 3.212. In Julia, you said 3.1. No, it's 3.212. But it required now 1,000 hours of compute to get to that accuracy, right? So in this world, what you need is you need a system-level model to do this kind of stuff, but you need to go and validate with detailed models, the 3D models. That is, and if you can bring those things, right, together, that is sort of the interesting thing. Now, in this world, for the last 100 years, 30, 40 years, the leading system-level language has been MATLAB and Simulink, right? But as you guys all know, yes, they are literally the preferred things. You go into any automotive company, they will use MATLAB Simulink as the model-based design thing, right? Then they will, after they pick that motor, then they will go into an ANSYS or a Dassault or Siemens to actually model with the 3D. But with all the advantages that you guys are working on with Julia, right, with the compiled stuff and so on, thanks, Alan, for all the great work that you have done at MIT and the work that you guys have done in Julia Hub. This is where we at ANSYS are looking for the partnership, right? So the ANSYS Twin Builder, this system, Samir, are you here in the audience? There you go. This is the man. He is the GM for our Twin Builder. He is working closely with the Julia Hub team to say, hey, this thing, can I integrate with and build this system-level model, right? And which would be better than MATLAB, better than Modelica, better than all that is sort of what we are working on. Then building all these things with raw models, scale, I actually need to speed up because I really need to cover some of the other stuff. Okay, so there is other stuff. Sorry, Samir, I'm skipping through some of that stuff because I need to. They'll catch you after for the details. So then the thing is, we are working on an ecosystem where these digital twin models, you can actually visualize it. So those of you who have seen Jensen's keynote at GTC, he talks about the Omniverse. This is this visualization platform. You have a manufacturing thing at a BMW factory, whatever. You can see all those things. So that's that powered by GPUs and so on. So what all these simulation models that we have from ANSYS, powered by Samir's twin, is now you can visualize on the Omniverse. And so you can actually have the physical asset, which is this whatever thing it is, right? Is this the electromechanical stuff. Here's the physical stuff, and you can actually see it on the Omniverse, and you can predict, hey, if this has happened, I put oil and vinegar, this is going to happen, it will show up on the picture. So imagine if NASA had this twin builder and Omniverse in whenever Apollo 13 came down, it would have done amazing things. But we are here today, and I hope there is no more Apollo disasters. Then there's this technology that Samir has been cooking on, this thing called ANSYS COSIM, right? Basically, you have a multi-physics simulation stuff, right? You have multiple things, and you have to simulate a distributed system. Some of them are with sort of continuous time, some with discrete time. It is this really complicated stuff, and so we have a technology of ANSYS COSIM, which can do this massive distributed simulation together. And I know I'm rushing up because I want to cover the future of digital engineering. So all these things happen, customers love it. Sorry, Samir, we have used it in Tata Steel, we have used it in glass manufacture, so this thing actually does work. What I really want to talk about is the future. Because this is the academic audience, right? I just want to give you a peek of where are things headed. Where it's headed is in the industrial landscape. You all know we have gone from Industry 1.0, which is mechanization, to Industry 2.0, which is electrification, Industry 3.0, which is the automation and the electronics, Industry 4.0, which is cyber physical, IoT, sensors, etc. We are in Industry 5.0, which is the AI and human and all that kind of stuff. The technologies that are pushing us in that area is AI, all the chat GPTs and clouds and Anthropics and GenAI, the blockchain, the digital twin, The metaverse, omniverse is the NVIDIA's name for metaverse. Quantum computing, big deal, right? And 6G, right, with all the IoT connectivity. So that's kind of where things are headed from the Industry 5.0, the actual end users. So in that world, the world is moving towards, if you look at how people change from building enterprise resource planning, ERP systems, right, that was a big change that happened in the 80s, to supply chain management systems, to PLM systems, to model-based systems engineering. The world that we live in today is digital engineering ecosystem, right? So in the world of digital, I'm designing an airplane, right, with 100 million lines of C code, et cetera, and it will predict this autonomous electric airplane will fly, right? Boeing is trying to design the 787 Dreamliner, et cetera, the future versions, right? The entire thing, the specifications will come in languages like SysML, and output will be a beautiful thing that will, the airplane, right? Fully validated and will run. So in that world, this is kind of the picture of digital engineering. And if there is one picture you want to take, it is this. Yes, I'll take it in with me there, right? Prith Banerjee talking about future of digital engineering, yes. So in that world, remember I talked about the world of synthesis, right? Synopsys transformed the world of EDA to do electronic design synthesis. I mean, instead of drawing rectangles on the screen, you enter it in RTL, VHDL, Verilog, outcomes, gates, place and route, et cetera, and do the rectangles. That is electronic synthesis. Can we do system-level synthesis? Once you do that, can you virtualize, can I validate? Can you do this with the physical assets, the IT, OT integration? Can I do the digital operations and have the embedded digital twin? So this is the whole journey. And I have one slide on each of them just to give you an example, right? So imagine I come up with a system level requirement that I need to design a Tesla beater. I'm designing an electric car that will go from 0 to 60 in 1 second and a range of 1,000 miles. I mean, if I could build that car, Tesla will be out of business. And I can, if the cost is like less than $20,000. So that's my requirement. If I could specify a requirement like that, can I synthesize a design? So if you were to work in an automotive company, right, you say, oh, I need to go for a range of 1,000 miles, right? My last car, the electric car that I had, could go only 200 miles, and I had a battery of this size. So if I have to go 3 times as much, I need a 3 times larger battery. That's how a human thinks. I need to go from 0 to 60 in 1 second, right? My previous thing that I had went from, in say, 6 seconds. So I need to go 6 times faster. That one was with the 200 horsepower battery. Now I need a 1,000 horsepower battery. That's how a human thinks. But today, the human is making every one of those steps, saying, oh, for this specification, I think you need a 1,000 horsepower motor with a whatever size battery with that gear. So the human is choosing all those steps. What if automatically I could synthesize all the stuff that is in the human's head, right? All the knowledge is captured, and this is kind of what we are working on. So you do all these things, you say, this is the EV car, and I have actually shown Viral a demo of this, right? There are 6 different designs that automatically came in. Then with Julia Hub, you are actually simulating all of those. This is one case of this combination of this electric car, which has the motor with in-wheel drive, with all the motors in all these wheels in parallel. That is going to be the architecture, right? Or it's the architecture with only front-wheel drive, rear-wheel drive. So all the choices that a human designer would have done automatically, and that's system-level synthesis. The second one is virtual validation. You are designing this car, right? It is going on the streets of, driving from Los Angeles to Las Vegas, right? In the heat and so on. It's just super hard. And then the thing is going over this thing, right? So how do you actually test, virtually test, before you build that car, that it will actually work, right? So the normal way that you do is they do the unit testing. Test the motor, test the battery, test the gears and so on, and then you do physical testing, you do the combination of physical testing and so on. The future is all virtual. Because if I'm saying, if the world is governed by the laws of physics, if Navier-Stokes equation doesn't lie, if Maxwell's equation doesn't lie. You don't have to build a physical prototype. Go to zero physical prototyping, right? And we have actually done things with digital twins. The picture is, if you could show those videos, it actually shows here is a car going right from Las Vegas to whatever, really hot things over this highway, and is there overheating happening or not, right? So you could actually validate it. Then you have this IT-OT integration, right? I'm just going through this, right? You have all these different things, and you put sort of sensors, you put PLCs, et cetera, et cetera. So the OT part is having all these Modbus, OPC, UA, all those standards that you have. And then you connect, use all the latest Ethernet technologies developed by Bob here, right? And this is the world. The world is MQTT, broker, et cetera, et cetera. That's how, in a real system, you are actually building these things with IT-OT integration. Then you did the whole digital operations. I'm flying this airplane from New York to Kathmandu, or New York to Mumbai, right? And I will do all this thing, right? This is going this plane, et cetera. I have all the sensors. So doing this whole thing with digital missions engineering, digital twin, that's sort of digital missions engineering. The last thing is digital twin. This is kind of where somebody is headed with this stuff, right? So we did a little interesting project in this Covisa joint work, right, with companies like Bosch and all. So imagine you are driving electric car, right? And you say it's like only 30% charged. Oh my God, if I don't find a charging station, by the time this thing goes, right, I am toast because I am on the highway, I need a charging station. So this is called range anxiety. So let's imagine that I'm a driver and I have connected to all the power and electronics and AC and all the kind of stuff, right? On the thing says, I have to go on 30% things, and with that, I could drive only 100 miles, but my charging station is like 200 miles away. What the heck do I do? If you're like me, say, oh, sure, come on, turn off the lights, turn off the AC. So you do all those things, right? This thing would say, Prith, just relax. Don't turn on the lights, don't turn on the AC. You just reduce the AC from 75 to 42, and you'll be fine. And you're completely crazy, you just go in with the last amount of juice, go into a charging station, you're done. If you could predict it as well, that would be amazing. So it's an example of an embedded digital twin. I thought this was an entertaining morning. So what I talked to you about is the concept of digital twin, which can be done with pure data analytics or with simulation, and I think the world is headed towards hybrid. I am biased. I think we are well positioned. Samir and we agree on that. But the future is about this digital engineering area, and this will literally be powered by Julia Hub. I kid you not. So we are excited to work with Julia Hub and all of you in the audience. So thank you very much for your attention. Thank you.
Questions for the speaker? I'll start handing them the mic.
Yeah, thank you so much for everything that you've been, I think that we share a lot of the vision here, but what I'm really curious to hear from, your experience here is, we put together this idea of, here's how digital twins can change the world, and has the pieces with IoT and simulation, What is the weakest link of this whole connection? And how should we prepare for it, right? Is it, there's a few things that come to mind. Company structures might have it so that way the people who design assets might be different than those that maintain it. Is it something with IoT security issues? Is it ability to scale simulation? Like, where in this are you looking and you go, oh, I'm scared that this is the weak link, and how should we think about what we're doing to handle that issue?
Unfortunately, it's not a simple thing with just the IoT security. It is actually a range of the things that you can cover. But I think I painted a picture that if you could do hybrid digital twins, right? So pure physics-based digital twins, even though, I work for ANSYS or Synopsys, we would like to say it just is not accurate enough because it doesn't capture the bird strike that struck this thing, right? So unless you can connect it with the data from the actual hardware, right, from the actual sensors, it will not work. So you need to do this. The difficulty here is that you have to be connected to the actual IoT structure. So I saw that you listed ASML as one of your partners, right? And Viral and I kind of talk about it, right? So let me give you a classic case of something that we are working on, right? A digital twin of a semiconductor manufacturing plant at TSMC or Intel, right? They have these massive things with the hundreds of equipment, 5 equipment from Applied, 10 equipment from ASML, 15 from KLA 10 core, all these different equipment, right? Now, imagine if you create a digital twin of each of the equipment. In a semiconductor process, right, there's like 200 processes that you have to do. You have to do chemical vapor deposition, then you do ion implantation, et cetera, et cetera. And you do this complicated stuff, and then out comes the Blackwell chip, right? And this thing, the yield is only 1 in 100 work, right? So all the others are kind of wrong, right? And so you have a line, and you have bad stuff coming out, right? I have a yield issue. How do I fix it? So if I could come up with a digital twin of that manufacturing plant, right? I can improve if you can just improve the yield by 1%, it's like billions of dollars, right? But you can't. So in this world, what happens is, if you could do a digital twin of an Applied equipment, and actually Applied is our customer, ASML is our customer, we can build a super accurate model of that Applied equipment, that epitaxial process, etc., right? But to make it work with hybrid, you need the Applied sensor data to come in and so on. Now you put the Applied equipment TSMC, they'll say, hell no, I will not let you connect the data from Applied to this because this is my data, right? So the real practical stuff, I mean, the academics we know, if I could collect the data, right, this is there, but you cannot, I will not let you, right? So you have to, what we are working on a solution is to say, okay, TSMC, I kid you not, this is exactly what we are doing. TSMC, you will not let Applied have the data, but we have helped Applied build the equipment, right, with our models. So I have a digital twin of the Applied equipment and that epitaxial whatever process. Just let us have access to your data. And I will give you this thing, you do this on your stuff, and it will be so much better, right? So this is the case we are making. We are not there yet, but the challenge is this siloing of the stuff, which happens in real manufacturing. If you would crack that nut, well, it's openness and so on. People talk about openness. The real world is Applied doesn't want to, because they're all competing for this thing, right? So that is the real challenge. Sorry to give a really convoluted answer, but it is really hard problem.
So that was a fantastic answer. Any other questions for the speaker?
Oh, I'm so disappointed. Nobody cares.
No.
I love it when a speaker gives a vision of the future, because that's, of course, the hardest thing to predict, as they say. So you've been a professor, you've been a technologist. As a professor myself, students often come to me, and I get the feeling that they are figuring out a course of study based on what made sense last year. Do you have any advice for students who want to look into the crystal ball and what will be most relevant a few years from now?
That's a great question. And the book that Viral referred to, right, called Innovation Factory, I am not shamelessly promoting the book. I'll just say that the thesis of that book is that large companies like ABB, Schneider, HP, Ansys, etc., right, they do a good job in the Horizon 1 innovation. I have my Fluent, what feature do I need in Fluent next year, right? That we nail it, because that's an incremental stuff, right? The adjacencies, which is Horizon 2, is sort of, yeah, I have a thing working on-prem, I want to go on the cloud, or I have a transformer in North America going to China with 220 volts. That also people know. But it's very hard for a company that is making laptops, Macintoshes, to come up with a brand new thing like an iPhone. So it takes an Apple to do those kind of stuff, right? So what I say in my book is, if companies want to do it, they really need to partner with the Allens at MIT and the startups like JuliaHub. And so this is literally what I kind of say. But in my final chapter, I say, you are all students, right? You are professors. And so when Synopsys started EDA, or ANSYS started simulation 50 years ago, the computer that I had 1 megaflops of power, had 32 megabytes of memory. So I wrote my Fortran code with column major order to do this stuff, with all these stuff, right? based on the computing that I had at the time. And then the world of parallel computing came in. Oh, now you can do threading, so I can take my Fortran core, do shared memory threading with this. Now I did, oh, I have message passing on the Cray, so I can do MPI. So I took that Fortran code and chunk into domain decomposition, do this. And now GPUs came in. Oh, now I should take this Fortran code, now try to GPUize it. Then quantum computing came in, and now all these qubits are happening. So the real challenge that happens is you develop some product based on the technologies that were there at that time. Now, the students graduating from CMU, UPenn, MIT, Illinois, Georgia Tech, right? In 2025, the technologies that you have are cloud, IoT, blockchain, ChatGPT, GenAI, quantum. Now, if you say, I want to do a startup which is an EDA technology leverage with GenAI, quantum, GPUs, etc., it sounds fantastic, right? You put everything in the kitchen sink. The smart person, right, like Bob or Alan, say, it is a combination of blockchain. If I took blockchain and quantum and GenAI, I did this here, that would be amazing. So think of these individual technologies as pearls. You have to create that necklace, string together those individual points, and do something like an iPhone that the world hasn't seen before. So, I mean, the iPhone technology put together a bunch of technologies, right, in a beautiful necklace. And that is what the students at MIT, you should advise them, right? You have all these amazing technologies coming, and not all of them are available. Like quantum, we are working on, I mean, I kid you not, all the technology I mentioned, I have got in the CT office working on those things, right? But my CEO says, why are you doing this? Because I don't know what the necklace is. The future of digital engineering, this system level synthesis is actually leveraging AI, quantum, this, that, etc. That is the exciting thing for your students.
I think at MIT, it won't be the necklace, it will be the jewelry store.
I agree. Thank you. Thank you.
Thank you. I think there are a few more questions, but
I am around.
Yeah. Please do find Dr.
Take
Banerjee.
selfies with me, post them on link. I'm just kidding.
With that, let us thank the speaker again. Now for our next session, I'd like to invite folks from Julia Hub to deliver their sponsor presentation. You have like 15 minutes?
I don't know if this is going to work.
Yeah, we'll make sure.
Can you just, thank you. One sec. All right. So this is the Julia Hub sponsor talk. Actually, Preet, you did a fantastic job of sort of laying out a lot of the groundwork of what I would have covered. So I think we'll have a sort of a quicker talk with a little bit more focus on the details in this talk. Yeah, are we having? Okay, let's try the HDMI. So some of you, while this comes up, if it comes up.
You have to choose something.
Really? Let's kill that. It's not seeing it. Can I do it on yours?
Yeah, sure. The presentation.
right? How many laptops do you need to, did that work?
Why not? This worked yesterday like this. So. Yep.
Okay. All right, so some of you might have seen our announcement of the Dyad product. It's a, Dyad is a new DSL4 modeling and simulation, and we're actually gonna have some demos about it, show you what it does, and hopefully put a little bit of sort of detail into some of the things that Preet talked about in terms of how do engineers actually go about building some of these workflows. A lot of the motivation for this stems from, for work in the Julia community, right? That as we started talking to customers, of the kind that Preet talked about, a lot of them are like, Julia's great, Julia's awesome, but I need tools with higher levels of abstraction that will allow me to accelerate my product design, bring my products to market, and check all the boxes for safety, regulatory, all of that. So Dyad is a tool. So Dyad kind of combines a lot of, it's a dyad, right? It's a dyad of many things, or it's many dyads. Brings engineers and software engineers together. It brings, math and physics together. It brings, data and model-based design together. So we felt like this is an appropriate name for this product, is that it's a dyad. It's bringing two different cultures together. So here's what Dyad expects to do. It's accelerating a lot of critical industries. We spoke about a lot of these aerospace, automotive, high-tech industries. AI is everywhere. I was just talking to Chris today. I believe that everyone in this audience is already heavily using AI in some form or shape, at least when it comes to Julia coding. A lot of people have actually told me that it works quite well with, with Julia, most of the coding tools. And Chris actually topped it off last night by showing me 25 TMUX terminal screens on his phone.
32.
I think you might have added some money into your thing there. So he said he woke up and he had 6 more PRs that were merged by then. So we are entering a brave new world. But everything that we're doing with Dyad is actually built on all the open source tools and technologies that we've spoken about for several years, last decade at this conference every year. And we are sort of thrilled to show you some of that in action now. Uh-oh, I want to actually pull this whole thing up. So again, for those of you who are not familiar with engineering product design, this is the world of product design, right? You have requirements on the left-hand side, you have verification, validation on the right-hand side, and then your digital twins in operation. And I think that the thing that is relevant, I think, to this audience is that the top parts of this V cycle are actually modeled as ODEs. And then as you kind of get into the details, you get into DAEs. And then as you actually start doing component level design, you get PDEs. And while the PDE world actually has a lot of amazing software available from a lot of industrial vendors, the ODEs and DAE space is actually fairly light. And it would probably come as no surprise to you that Chris and I decided to focus on this world as we go forward. And we have over 50 talks at JuliaCon over the next 3 days that will touch upon the underlying mathematics, the underlying physics, the software engineering. How does Julia make small binaries? How to constrain the size of the system image? Every single thing that we all grapple with here is actually coming together into actually building real products for physical products, right? And so on. I'm going to move a little fast here. So our next thing, Chris is going to talk about the demos, but one of the cool things about Dyad is that when you talk to engineers, they're like, Julia's cool, but it's all code. I can't work with code, right? Engineers are not software people. You need to have a GUI. You need to sort of have an intuitive grounding in the kinds of models you're building. And I think Michael Tiller, somewhere in the room, he's the architect of Dyad. If you see him, he's all the way at the back there. If you see him, ask him anything you need to about Dyad or about the why of Dyad. But this is the fundamental sort of push and pull, right? That we want something that's a first-class coding environment. You want Cursor, you want Claude Code, you want the 32 terminals that Chris is running, to design every component of your airplane while he's sleeping. But you also need to be able to see what was produced and verify it and validate it and do all of that. And Dyad is our answer to all of that. So without further ado, Chris.
Yeah, so here's a view of dyad in action, right? So what you're looking at is we're constructing a digital twin of a DC motor. So this is actually being built using physical components. So you're putting down these components that have these physical equations. It's generating what's known as a differential algebraic equation that is all the physics involved in the object. And what's happening here, though, is someone who might not know as much about how the inertial elements work, how maybe the resistor or the inductor, you can piece together these models that someone else has already built. You can say, hey, connect these. This resistor goes to this inductor goes here. And what you're doing is you are working at a coding interface or at a GUI interface, right? You're putting in these values and you're saying, hey, this is my friction coefficient, but it's actually building a code under the hood. And it's actually bidirectional. If you modify the code, it actually will modify the GUI as well, right? And so you can also then look at this and say, oh, I can, you can interface with all of your Claude components or all of these AI tools as well. And now what this is actually running now is it's now going to do a PID auto-tuning analysis. So doing this kind of controls analysis on the model that we've created. Now, the cool thing about this is that these analyses, right, the fact that, oh, hey, it's able to do this noise sensitivity analysis and all this is done with an interface to JuliaCode. And so every one of you out there that has a Julia package, if you want to be able to put your special, your special things that you do, your surrogate generator, your digital twin pieces, if you want to make those work with the dyad GUI, there's a direct interface, so that way we basically just say, here's how you expose your code, so that way any possible analysis can be done with the model. Because what we really feel is the future is to be able to make all of the ways that the open source community is building out new ways to analyze models with all the pre-made models that are actually being built with high fidelity within these companies. I think that when we get these two together, then we'll be in a place that we haven't been before. And we're also then putting this together with automated code generation, so that way the devices that we build and tune through dyad can actually be put directly onto airplanes, cars, and be able to be the thing that is running the future. And so that is what we're really piecing together, something that is a graphical coding environment or a graphical modeling environment with a coding interface, tying this together with all the tooling of scientific machine learning to help improve the models that are generated, but also the generative AI tooling, so that way all of the code in the back end can be improved and the scale is run. And so basically this, it's not about just being able to build a digital twin, it's about being able to have a system where digital twins can continually start to improve themselves. And you start to have this run on a cloud system, the data's coming in, and the digital twin is just improving, and becoming more and more real because it is actually out there and living in the environment. And so we start to see this so this was a model built by Ben Chung, and he'll be giving a JuliaCon talk on other aspects. But here's, for example, an HL-20 lifting system, which is a model of one of the older spacecraft of NASA. And you can see that this GUI is able to build out these large-scale models of these pieces. But then we can expose these gigantic models of realistic systems as just a component. And you start to drag them in there, and we start to say, okay, here's a realistic battery, here's a realistic car. Piece it all together, and now what is the mileage that my Tesla will get 10 years from now after the battery's degraded? And these are the questions we can start to answer and be able to know, are we designing our vehicles appropriately? But for everyone who's here, it's all built on the Julia tools. And so if you want to be able to integrate with the system, right, if you're using Modeling Toolkit, we have APIs to be able to say, hey, look, here's how you can make sure your Modeling Toolkit type of code, here's how you can integrate with dyad. And if you're building analysis tools, if you're building things that make interesting plots, there's all of these ways to be able to say, if you want folks within, Ford or, any company that's potentially going to be using these systems in the future, here's how you integrate with the graphical user interface, so that way your tools, and all your things are directly exposed to those who want to be using graphical interfaces. Because this is what we see in the future, right? There are people who are using point-and-click interfaces, and there's people who are using code. I think that both will always exist, but making it so that way those two can tie together, and importantly, bring in the open source community, I think that is where we make a play that no one really has been able to do in the past, and that's how we then change how all things will be designed in the future. So, and we're integrating this directly with a lot of the tooling that, this is really kind of changing the world, right? So here, this is a cursor integration that is working directly on the dyad code. You can see that it is figuring out with this model, which is a model of an active suspension, how to be able to do the PID auto-tuning. It's understanding and giving out information about, how this controller should work. And it actually has made a change to the code to be able to put a controller piece in there, and then it's going to run a transient analysis to be able to tell you, oh, this is actually the optimal control signal for this for the force on the seat, right? Because the idea here is, could we have components where the code is actually improving, right? So you build a car once, but if the car is actually half software, can we make it so that way you can make a simple car, a cheap car, but because of software, it's actually more luxury than the most expensive vehicle you could build? Can a software update take a $10,000 vehicle and make it feel like a Porsche? I think that this is possible, and that's the future that I think that we can all head towards. And this is what we're enabling through Dyad. So if you haven't tried it out yet, please check out Dyad. It is a domain-specific language that interacts well with Julia. The components that you build, it's all generating Julia code, and so you can actually see, oh, what is it compiling to? How do I run with it? So everyone here in this open source community, if you want to get familiar with everything that's going on, give it a try. We're going to have a lunch and learn later today. Yeah, and Dyad, what? Yeah, and Dyad is actually source available, so we made it so that way the compilers and these kernels involved, you can take a look at the code that is in there, and then a lot of the standard libraries are open source as well. I will say that, there are certain libraries that we're using as a part of the productization, but there's a lot of open sources being integrated into the way that we're doing this, specifically because we think that this is the way that, we can help grow with the Julia community. And so with this, there's a whole lot of talks that are going to be happening at JuliaCon. Take your pictures. Basically a lot of things that are going on related to scientific machine learning, differential equations, and all the things involved with modeling toolkit, aerial vehicles. These are all going as part of this push for Dyad to really pull the Julia community from things that we're doing in academic space to the thing that is now running the next airplane and the things that are running the next automotive. So thank you, everyone. And if anyone wants to if you're interested in, using these tools, but also if you're just interested in, hey, how could I be a player in this change that's going on in how Julia is growing into the, big industry player, please come talk to us. We'd be happy to, tell you and, and have a conversation about, how we are interacting with this whole community and how things are changing and how you can be a part of everything that's growing. So thank you very much.
Thank you to Julia Hub for being a diamond sponsor at JuliaCon 2025. Are there any questions? We could do a quick question. No, I mean,
For the stream.
you should probably use the mic for the stream. Thanks.
So thanks for the inspiring talk. What's the are there any possibilities of us or the Julia community also, let's say I want to come in with another types of blocks. I come from quantum modeling, so I can see this GUI also be helpful to build systems in there. What's sort of the possibilities for that?
Yeah, fantastic question. So all of the Dyad repositories, they're actually Julia repositories with a Dyad folder that is basically giving it the information that it needs to be able to represent these components within the graphical user interface, right? And so if you're already using Modeling Toolkit, there's actually, the change from Modeling Toolkit to Dyad is not very difficult. I would say check out the Lunch and Learn, where we'll show what some of these Dyad libraries look like. Again, they're just Julia repositories. So if you add that Dyad folder to your library, then boom, someone will be able to grab your library from open source and be able to effectively integrate it with the graphical user interface. So yeah, and so there's the integration as model components, and then there's also the integration as analyses, right? I mentioned that there are these controls analyses that we can run, right? For tuning autocontrollers. So if you're someone who's working on instead here's a new machine learning method for better reduced order modeling, if you want to make this so that way it's available to this larger population, you can also make that custom analysis. There's an API for that, and it just generates the text boxes for the information it needs, and then boom, now you're directly integrated as well. So we specifically developed this because we work a lot with the Julia open source community. And we want to make it so that way everyone's work could be integrated, so that way you can get more people using your stuff, more people who are citing you, and finding out more about how this is being used in the real world, right? So we definitely want to help talk to you about how you can help make that connection.
Actually, I just wanted to, I think that was a very good question, right? Like, whether it's quantum or whether it's a systems biology, right, or QSP or any of the other domains that I know that a lot of the folks here have talks about. One of the things that you see with existing tools or the legacy tools is that, it's a two-tiered system, right? Like the people who design the system actually have incredible power to add features and functionality and models, but the end users actually get a black box. And I think the thing that's different about Julia is, as we all know, is that it gives you the same powers as, the compiler writers, the standard library authors, or the end users have the same level of access to the internals. And that's the same sort of idea within Diet as well, that everything that you see here with the GUI, with the models, is fully extensible by the user. So there is sort of no things, the end users can do all of this and completely extend all aspects of the system.
Thanks, Viral. With that, I conclude this particular session, so let's thank the speakers again. If you're interested in being part of the Julia Hub Lunch and Learn session, please do approach the Julia Hub. And before I let you go for the break, I do have a couple of announcements. The talks are going to be split between two buildings. So there are three rooms in this building, and then there's 2 rooms at the Cathedral of Learning. And the Cathedral of Learning is the tallest building in the area. You can't miss it. So it's like a beacon. If when in doubt, just walk towards the cathedral. So we have 2 rooms, G24 and 324, so the ground floor and the 3rd floor at the cathedral. Volunteers will be around helping you navigate between these rooms. Any other announcements? We also have coupons to various restaurants in the local area. Please do come to the registration desk and pick them up. We are here to help. And any other announcements from the local organizers? Yeah, go.
So we have coupons for some restaurants at the reg desk, and there's also 2 restaurants, K-Town and Columbian Spot, where you can just show your badge and get a discount. So please go and check all of those out, and all the other wonderful businesses around as well. Thanks, everyone.
Yeah. Thanks. Oh, and folks on the live stream, we will see you in about 15 minutes.
Test. Yeah, Yeah, I tried and it works. Everything looks great.
You plugged it in real quick.
Yeah.
Okay. Good. I actually, that's only half the battle. You see it there. And I saw it back there, so we are good. You know, that's for the stream.
Yeah, very cool. Okay, and this will be recorded, right?
Recorded and streamed.
Yeah, very cool. Cool.
What time you start?
Like in 5 minutes, 10 minutes?
Go ahead. Look it up so we have something. Nice MacBook Pro. They always work good, you know?
Yeah, I think that if I do that.
We're good. We have it back on the stream, too.
Test. Well, I mean, it's supposed to start in 2 minutes, so. But really happy to try.
Nice to meet you in person. So I'll just introduce you and also the music.
Yeah, sure. But probably I will not meet. But yeah, you're very good idea to be careful with that.
So the story is the stream is ready to go when you log in, and he thinks it will probably be best to schedule time, which is basically now. So why don't you get going? Thank you for participating in the symposium. Can I use this one? Yes. You know that one?
Okay, so it's 10:30, so we are starting the next session here. So this is the first session in our mini symposia about tooling, which is basically everything that we use to write Julia code or to deploy Julia code and these things around. So that's organized by Team Holy and Claire Foster, who couldn't be here unfortunately, and myself. And we will occupy this room for the entirety of the day, actually. So, all right. So first, let me introduce the first speaker, where we'll present a new linter. So the floor is yours.
Thank you. Hi, my name is Alexandre Bergel, and I work for the company Relational AI. and I live in Bern in Switzerland. And this is my very first JuliaCon, and I'm super happy to be here. Like, when I see all these famous names, I'm very happy. So Relint. So Relint is a new lint checker for Julia. So lint checker is a tool to improve the quality of Julia source code. Like most of the programming languages, they come with at least one lint checkers. And lint checkers, you know, like if you write just a few lines of code per day, then probably you don't need to worry about using a lint checker. But as soon as you have a large amount of code, as we do, then lint checker is very important. Like our software is slowly, you know, heading toward 1 million lines of code of Julia code. So it's very important to use lint checker to control the quality of some aspect of our code base. You know, a lint checker could be useful in many different ways. You know, for example, it can help you, it can help new Julia programmers to avoid some mistakes. Also, like, can help one forbid some particular construct, you know, Julia keywords or Julia API that you don't want to use. Also, like, you can enforce some corporate programming conventions, something very important as soon as you have, you know, a sizable amount of software engineers working on the same code base. Also, like, you can enforce some architectural invariant. You know, imagine that you have your software that is made of a number of components. You may want to prohibit, you know, one component accessing the API of other components. You know, let's say the core of your application must not refer to the test, but the other way around. And also, like, you can enforce some security policies, and I will give an example about that. So lint checker, a lint checker usually works by thoroughly looking at the source code. No matter whether your application can be compiled and run, you just look at the source code. So Relint. So Relint is a new lint checker that we design. It is distributed under the MIT license. So we are a company, and we think this is a very good idea to have Relint open source. So Relint started as a fork of StaticLint. So at first we used StaticLint, and we were happy, but up to a point. And I will explain about that later. And if there are some of you who are involved in design of StaticLint, then thank you very much. I learned a lot. Relint is small and fast. The core of Relint is about like 700 lines of code, and it is fast. So we run all our rules on our 700K lines of code of Julia code in less than 3 minutes. And usually, like, if you're just doing some incremental modification on a few files, then this is just very fast. And also Relint is with Relint, it's very easy to design and add new rules, and something which is very important to us. And also Relint can be embedded in a GitHub Action workflow and also a pre-commit. So, and Relint works by doing some pattern matching on the AST, the abstract syntax tree. So the abstract syntax tree is one example. Here we are, if you use the CST parser as we do and as StaticLint does, then you can have CST parser.parse, and here you have some Julia code as a string. And then the result of the parsing is just a tree. And then we do some pattern matching on that tree. For example, here, actually those 2 lines are some real tests of our test suite. You know, here you have this meta variable, whole variable, that can matches anything. In that case, the whole variable matches the 5 here, or the whole variable can matches the 5 plus 10. And that's really the essence of Relint. Okay, so you define some patterns, and those patterns Relint will look for instances of those patterns in your code, in your source code, and then you can define the rules accordingly. So I will give you like 4 examples of some of the rules that we design, non-trivial rules. So about task scheduling, you know, in Julia there is a number of ways you can achieve concurrency. For example, you can use @async, which takes an expression and run that expression in the same thread than its parent. Or you can use spawn, @spawn, and again it takes an expression and it runs this expression in any available thread. Both async and @spawn provide concurrency, but @sync does not provide parallelism, whereas @spawn provide parallelism. So we, as a company, we took the decision to forbid the use of @async in our code base to favor @spawn. So how can you use Relint to enforce this rule here? You know, you define here a subtype of violation lint rule, it's called async lint, and then you define this function here, check. And this function check takes x as a parameter, which is really the portion of the AST where Relint is checking your code. And then if there is an instance of that pattern async whole variable, then it will just return the error message. Then for this rule here, we have two checks. The first is at async and threads at async. And then here you can, an example on how to run relint. Then you see relint.runLint on text, and here you have some Julia code. And then you will have, you will have here an error saying that line 1, you should use at spawn instead of at async. So this is just one way to run relint. There is many different ways. Usually you just run relint on a folder, which is the root of your application, and will look for all the Julia files. As a second example here, I want to talk about like the Julia compilation. So Julia compilation may be significantly slow, and that could be really a significant issue. Like, again, if you just have a few hundred lines of code, this may not matter, but as soon as your software is very large, as we do, and especially like when you use the types in a very exotic ways, then Julia compilation can really be a burden. Thanks, there is this package compiler.gl, which is very useful. It speeds up the Julia apps by avoiding some just-in-time compilation. And the idea of package compiler is that it serializes all the compiled elements into a file. So there is two phases. There is these build phases, where you run your application in order to identify, like, in order to compile things and store everything that's been compiled into the file. And then you run your application in a normal way, where it will benefit from the previous compilation. And that's really great. Package compiler actually also like serialize all the compiled elements into a file, and the functions, but also like the value of constant variables. They are serialized. So it means that if you have a line such as const threads count equal threads and thread, which is in order to know like how many threads are there available, then using package compiler, I mean that you can have the expression being run on the machine where the program is built, which could be very different machine from the machine where you will run your application. So the thing is, so you don't want to run your application with the value of n threads coming from the machine where you build it. So how to forbid the use of threads and thread in a constant variable? So again, you define a subtype of violation lint rule, initialized with function rule, and here you have this check. The difference with the previous rule here is that you want this rule to be checked only when you are in a const, top-level statement. And this is what here we have. We have this marker saying that, if you are in a const, if I'm not in a const statement, then I just return. Then if I am, then I just evaluate these checks here. Then I say, if I found instances of threads and thread, then I will display that message. Same thing for isLocalDeployment or deployment.isLocalDeployment. As a third rule, consider this code here. If you have if foo and do something, else if foo, do something else, I mean, obviously this code is, is not correct. I mean, you can't have twice the same condition for two different branches. I mean, assuming, and this is a reasonable assumption that foo doesn't do any side effect, then this code is really like weird. And that looks obvious here, but if the two foo condition here are a couple of hundred lines of code away, then it may be hard to spot that. So you can define a new rule here saying, if whole variable a, so here I did this a here, whole variable else if whole variable a, it means that the content here must be the same because there is this small here label that comes next to the whole variable. It means that there is a constraint between these two conditions, they must be the same. If this is the case, then we just here display this message, unreachable branch. And as the last example about security. So like relying on external logging facilities is, this is very difficult. I mean, you must be very careful with what you can log and what you cannot log. And this is such, an important problem that we design a facility for that. We design a framework called safe logging, and safe logging is really like to prevent, data leaks in the log. And it's very simple to use, and it was designed that way. Consider here this example. You have the struct users with the username and the password. And here I create a user, my name and here the password. Obviously, this password is sensitive and must not be logged. So the way we can use our framework, safe logging, then you define here a safe show. Safe show here takes an IO and a user, and then here write in that IO saying, it's safe to write users, it is safe to write the username, and here it is safe to write some asterisks. And then you can use the safe show like that way. You have arrobas info, arrobas safe, created users, and here we, the safe is aware of the interpolation here, and then we'll make sure that this thing is safe to be interpolated. And here you have an argument, username also has to be safe. And then whenever you execute that, then you see that there is no sensitive information being logged. However, nothing prevents you from, doing arrobas info user1, where here you will have this sensitive information being logged. And we don't want that at all. And how can you prohibit unsafe logging? Well, you write a rule. So I won't go into details. This is a more complex rule, but the idea is, again, you create a new type, subtype of, in that case, fatal lint rule. So fatal lint rule means that if there are instances of that rule, then it will prevent the pull request from being merged. Something very important. I will discuss about that later. But and the idea is if I am, again, that rule, the rule that checks for unsafe logs is very important for our code base, but if I am in a test, the test suite, or if I am in a benchmark, then it is totally fine to have unsafe logs. But outside those, tests and the benchmarks, we must prohibit unsafe logs. And here we say, if X, again, X, this is the AST that I'm currently checking. If this is a macro call and the name of the macro call begins with arrobas info, then if all the arguments are safe, then that's fine, else I report the error. So I gave you 4 examples of some rules, but we have many more. So we have 33 rules like today, and those rules are categorized in 3 categories. So first here, we can have a recommendation rule. It means that if there are instances of that rule, then this rule will be reported to the person who will review a pull request. If there is a violation, then this will be reported and intended to be read by the author of the pull request. And the author must act on it. And then the fatal violation lint, this is again a violation that will, if there are instances, it will prevent the pull request from being merged. Again, this is all, we decided that we must not want to have anything that goes against some very strong rules. Okay, so that's the idea of the way that REPL works. And REPL can be embedded in CI/CD. For example, this is an example of a command that is being posted in a pull request on GitHub. And the idea is each time there is a commit being done, then you have REPL that works and analyze the file that has been modified and then give a report. In that case, there are 2 violations. Here that says, please use tin instead of Julia's in, or use T as key instead of Julia's as key. Tin and ASCII, those are some functions that we define, and we want them to replace the standard standard in and ASCII. And you can click here, and boom, it jumps you. It jumps on where the instances of that pattern was found. And here we have an instance of a recommendation that is good for the people who want to review the PR. Saying at inbounds, should be used with extreme caution, since it can lead to some unwanted way. And also REPL can be embedded in a pre-commit. So here this is an example of piece of code that I wrote. So here I have my code, and here I added this arrobas info, not at info, iterating over nodes, and KV, 2 value here. So if I try to commit that change here, just this new line here, the commit will be prevented. I cannot commit locally on my machine. And instead I will get this error here saying that at line 40, I have unsafe log statement. So this is an example of the rule I showed you before. So pre-commit is very interesting in that case because lint is run locally and not on the CI/CD. And that could be very important because running on CI/CD, like all, it takes time and money, but locally is very cheap. And since relint is fast, then we can have those checks, being done like at no cost. So you don't even notice that things are being run. Relint is easy to install. Like obviously you can clone relint and from the command line saying, oh, I want to use relint on that folder here that is the root of my application. Obviously you can do that, but also you can create a GitHub action workflow and that's very easy. So you just create here this workflow and whenever you commit, boom, you will have this workflow being run and then the command being posted nicely as a command pull request. Okay, so as I mentioned before, relint has been inspired by static lint, so it's heavily inspired. At the very beginning, we used static lint, and we tried to extend it, and by adding a rule, and that was going okay, but up to a point where, okay, no, we need to think a bit better. Static lint does not really, easily allow for new rules to be added. It was like very cumbersome, and also like it cannot be easily embedded outside VS Code. And for us, that was two very important aspects. So relint is designed to address these two issues, and that works nicely. On the other hand, relint does not really interact with VS Code, obviously. It could, but we haven't really made that a priority for us right now. Okay, I discussed with some of you about relint, and you guys gave me nice feedbacks. Maybe I can consider to use Julia syntax or Julia lowering or Julia server. That would be fantastic, and I'm very happy to be able to discuss that further. Things that I'm dreaming about is having relint to identify unused variables, unused functions. In the 700,000 lines of code of Julia code we have, probably there is dead code. And it would be great to be able to spot them. Also spotting typos, it happens all the time, and and it would be nice to have lint catching those things. Also exploring the type inference, also something we would like to use. At some point, we've been using Jet, but we've been a bit unhappy with Jet. Again, I would be happy to discuss about that. And so that's why I think Julia syntax and Julia lowering really gives very nice opportunity. So I think also relint, if you go on the website, I think it can be better packaged because currently relint comes with all specific and own rules, and if you want to use relint, and maybe you are not interested in all rule, so maybe we should split that away. That's just a small matter of programming, and yeah. So to conclude, relint is a lint checker for Julia, inspired by static lint. Relint is distributed under the Mighty license, so I mean that you can use it. You can use it even for whether you are a researcher or whether you are a company. You can just use it. Maybe send me an email about we are using it, and I would be super happy about that. And new rules also can be easily added. They can be added without touching the core of relint. Can be added. New rules can be added in a separate file and in a nice way. So relint works well. It is currently being run roughly 100 times per day on a 700K lock code base. Feel free to reach me if you want to try it on your code. We can just sit down and I will be happy to. So thank you very much.
Okay, thank you. Do we have any questions to the speaker?
Thanks for a nice talk. Since many tools in Julia are, both, written by their users, so that gives one sometimes an interesting experience in that when one wants to write a new rule, I imagine when you write a new rule, if you discovered that relint isn't yet set up really to support that kind of checking, you just extend relint, right? So what's your experience with what fraction of the time when you want to do something, can you just target the existing set of checks with the specific thing you're wanting to look for versus you need to, right? I mean, the number of things I could imagine wanting to check a code base for are very large, right? And so the question really is having essentially a sort of a finite API for doing that, does that actually cover most of your practical needs for it?
Kind of. So for example, like if I look at this piece of code here, you know, so this is here the example of thread and thread that must not be used in a const statement. You know, here, like, how do I know that I am within a const statement? And here I use these markers. And I think using those markers is a kind of a hack. In principle, like if I would have very nice regular expression, you know, library that works on the tree, probably I won't need those markers. But I'm not expert in regular expression. Like I never wrote a regular expression engine, and that would be something that would be really nice to have. And currently, like if you would have a full support of regular expression on the tree, then probably we would be better, like be able to handle some complex scenarios. But yeah. So to answer your question, so far it has been working very well. And the time we took actually was more like which kind of rules do we want to have as a recommendation or as a violation, or but we really spent a lot of time on that, not so much on building rules. And actually we had also some of our engineers who have worked on writing new rules. So it seemed to be very easy to write rules, and well, we are happy about that. But again, this could be improved a lot, I think.
Right, anyone else?
Yeah, when you do this matching in your, what was it called? When you define a rule, you have this match. Is that your own code running the matching, or there's some other packages like macro tools that you can also match expressions in Julia with? Or have you written your own to do that matching?
No, I've wrote my own. I tried to use some external libraries, but it didn't really work out that way. Maybe I didn't look at the proper way, but no, we wrote it yourself. Actually, like the AST given by CST parser is really like clean and very small, so it was not that difficult actually to create, something that compares ASTs.
Okay, thank you.
Hi, thanks for the talk. I'm curious about the interaction with pre-commit, because in my experience with the formatter, it takes a long time to recompile every time your function of the formatting. So pre-commit takes a lot of time when you write Julia hooks. So did you find a solution for this, or do you need to compile all your functions on your specific code every time you're making a commit?
It is true that pre-commit can take time, but in our case, like relint is small, so just running, like to have pre-commit run relint is very, like it's fast. And so like I did some measurement, like it takes like about 1 second. You often, like if you just change a couple of lines, couple of files in VS Code, then running like pre-commit runs in about like 1 second, between 1 and 2 seconds, and give a report, and which is acceptable for us. I mean, we had this informal thread, limit of 5 seconds. We don't want pre-commit to take more than 5 seconds, but we are currently like well below this 5 seconds, and yeah.
Are you planning on making like a composite GitHub action so that people don't have to kind of copy and paste that GitHub workflow you have?
Yes, that's the idea. Like, yeah, I mean, we can sit down and can try out. I would be happy to.
For example, in that threads and threads example showed, is the pattern matching purely based on names or bindings, or does it also take into account, for example, where the threads binding stems from? Is it like the thread that's rendered with base, or some other module that just happens to be named threads and has an and threads function?
No, like currently we are not doing any name resolution, symbol resolution, and this is something I would be really happy to have. Now currently this is just on the pure names, just on the names, and but we would like to go further, which is why this Julia syntax and Julia lowering really seems to be very interesting.
Okay, thanks.
Thank you.
Okay, we have time for one more question, perhaps. Okay, I have a question. So you mentioned that it currently doesn't integrate with the VS Code, but of course most people use NeoVim. So is there a way to export these violations as, for example, JSON? Because if there is, then it's very easy to just parse it and display it in the editor.
Yes, yes, that should be easy to do so. Actually, we are doing that. We are doing that. So there is several exporters of the report. You know, you can have the report as a markdown, as you can have here, like for whenever it is used, you know, on CI/CD. Also, you can have a pure text file. Also, you can have the JSON. And the JSON, for example, it is no, it is not JSON. We have a dedicated exporter for the report by being used that on, you know, to annotate the PR using on GitHub. You know, like if you click here, then it will jump on the page, and then you have things get highlighted. And just to have that, we had several exporters. So yeah, that should be trivial to have a new one.
Then let's thank the speaker again.
Thank you very much.
That? Presenting next? Yep. Great. So I've got HDMI on this side, I think. Oh, yeah. Make sure I have it back on the screen. Sure.
All right, so let me introduce the next speaker, which is Sebastian, and he will talk about the past, present, and future of the language server. So the talk after this one will also talk about the language server, so they are kind of shared or joint in a way, but we're sticking to the schedule and treating them as separate talks. So whenever you're ready, the floor is yours.
All right. Hey, everyone. Yeah, as Frederick just said, I'm talking about past, present, and future of the Julia language server. Let's start out with a brief history of Julia IDEs, Julia tooling. There are a few Julia-specific IDEs and editors in the past 12 years now, I think, since I've been kind of involved with the Julia community. And yeah, these are some of them. In the olden times, there was Julia Studio. It was a Qt-based, Julia-specific editor built by Forio, and it only worked for Julia 0.2. So when I kind of tried to use
Julia 0.3 and tried to find an editor. I tried this, it didn't work, which was a bit unfortunate, but there luckily were some alternatives in the work. In 2014, Mike Innes started work on the light table-based Juno editor. Light tables, at the time, very visionary IDE, I guess, built on Clojure and a bunch of web tech, essentially. And it was meant for Lisps, but as you all know, Julia basically is a Lisp, so it seemed very appropriate to hook into that. And the vision of Lighttable was to allow for very interactive development in the editor. And what Mike built with Juno sort of followed along those lines. But the initial implementation didn't have any particularly advanced editor features, no like IntelliSense or stuff like that that you might expect. Lighttable slowly died, but GitHub worked on the Atom editor, which also built on WebTech, but no Clojure, so maybe a bit easier to get into. And yeah, fun fact, Electron, which some of you might know as sort of the framework that a bunch of desktop applications are nowadays built on, like Slack or whatnot, was originally called Atom Shell and was written especially for the Atom editor, and then just kind of took off on its own. The Juno editor in Atom also focused mainly on full interactivity. It could display plots, had a debugger built in, had a workspace, inline evaluation, of course. That was sort of the main thing inherited from the Lighttable implementation. And slowly but surely, some more static analysis-like features crept in, especially when Shuhei sort of joined the team and did a bit of work on that. Unfortunately, Atom also got sunset a couple of years ago, so Juno is no more. But development did move to VS Code. I'll get to that in a little bit, but first I'll just give a very brief overview of the architecture of the Juno IDE. And yeah, essentially the client, Juno, Atom, would talk to the REPL process for everything it needed to either evaluate code or show plots, show the debugger, whatnot, but also to fetch information about the code base you're currently editing, so to get global completions, which would be implemented by reflection, right? You just ask Julia which names are available in a given module, but also local completions, and these are then built on a custom parser. And that's CSD parser. I'll talk about that at a later time as well. So this architecture is mostly fine, except when it isn't. If you're running the REPL and code analysis in the same process, in the same thread, then obviously the two will conflict at some point, and it turns out people don't like it very much when their diffie-Q solver runs an order of magnitude slower just because you open two files at the same time, or just stalls. So that was a big issue with loading the code you're trying to run and the code that's responsible for analyzing what's currently open in the editor into the same process. And yeah, crashes are also a big thing, right? If your REPL process dies because of some code you've written, then you also don't get any in-editor completions, for example, which is a bit annoying. As a sort of second point, which isn't really related to this architectural choice, but any kind of analysis we had was fairly basic. There were some local completions and so on, but nothing particularly advanced. But that's something that could have been fixed if the hours had been put into that. All right, anyways, let's talk about the present, I guess. The VS Code editor itself, I'm not sure when exactly they started working on that, probably like 2015, 16-ish. But the Julia side of things started out in 2017, so it did live in parallel to Juno. David and Zach laid the groundwork for sort of both the extension for VS Code and also the Julia side of things, which is the whole language server ecosystem, essentially. And in 2020, when it was, essentially when Atom was sunset, the remaining Juno team sort of joined forces with David and Zach on working on the VS Code extension and the language server. All right, so to the more in-depth part of this talk. The way Julia and VS Code works is that there are three main parts. The client, which in this case is VS Code, but in theory could be any editor. The whole point of the language server approach is that it's fairly agnostic towards which client is talking to the server. A REPL process for all of the interactive needs, which sort of got inherited from the Juno approach, and then a language server process that itself had a bunch of dependencies layered on top of each other. All communication between these three processes was handled via JSON RPC. That seemed like the obvious choice. And the REPL process itself, as I said, handles all interactive features, so it does code evaluation, plotting, profiling, debugging, table rendering, the workspace, and all of the other fancy interactive stuff. It also has some limited support for introspection. So for example, we can fetch information about which modules are loaded into the REPL process or get REPL-like completions based on the REPL state. However, that's not the main source of completions and other info about symbols in your editor. All of that is based on the language server process itself, which contains, as I said before, like a bunch of packages layered on top of each other, and I'll go into detail as to what these do in a bit. As sort of the overarching design goals of the language server implementation, there were probably more than three, but these are, in my opinion, the most important ones. First is that the language server process never runs any Julia, or not any Julia code, any user code to circumvent the issues we had in the Juno implementation, essentially. So nothing the user can do in their REPL process should be able to take down the language server process. Second one is crash fast, fix fast. Whenever something would go wrong in the language server, it would just crash up, print an error message, and if you've opted into that, send telemetry to the developers, which at the time allowed us to fix a bunch of issues very quickly because we saw them as soon as they happened, essentially. And the third one was that it needed to be fast. You want to get feedback on essentially every keystroke. You want to know if you've just, type out the variable name you're typing, or completions, need to take into account what you've just typed, otherwise they're going to be essentially useless. As a quick aside, the language server protocol is what ties together the client and the language server, and this was a standard pioneered by Microsoft to connect arbitrary editors or clients with servers, language servers, that would provide all of the fancy IntelliSense feedback that you'd expect in an integrated development environment. And it was basically developed in parallel to the main VS Code editor, so it's very, very much tied to that in a way, but at least in theory, it's supposed to be completely independent and can be adopted by various editors. And that has in fact happened, so NeoVim, Emacs, Atom, and many others that have implemented generic language clients or extensions for language clients that you can use to connect to basically any language server. And the way this protocol specification works is that it specifies which messages can be sent from the client to the server, how the server is supposed to respond to those, and it's completely JSON RPC based. Right, so let's take a look at how the Julia packages are implemented that power the language server. The sort of top level here is languageserver.jl, and this package essentially contains the interface specification, so it's essentially a mirror of the JSON spec that Microsoft designed for the LSP. So it implements Julia types for all of these. It sets up the client-server communication handlers for the various RPC methods the spec prescribes. It handles text document sync and workspace management, both of which can get complicated if you care about performance, especially if you're working with big files or if you're working on a remote server, because then you don't want to send the whole document across on every keystroke when it got updated. So in theory, the underlying infrastructure supported incremental sync before. Right now, I think that's essentially disabled for correctness reasons, but the spec at least supports that. Workspace management is also very much tied to Julia environment management. If you have a workspace open and that has a project.toml and a manifest.toml, then we can take that into account and figure out which dependencies you're loading, and this will get important further down the line. Yeah, and lastly, it also sets up the sort of request handler loop, right, that handles communication to the client and dispatches incoming messages to the correct handlers and prints the responses back to the communication channel. Communication is typically handled via pipes or sockets. Theoretically, there are also modes where a client can connect to the language server via standard in, standard out, but that seemed a bit more brittle than what we've gone with. Okay, so what features does languageserver.jl support? Some of what you'd expect, right? Completions, documentation about a method or a binding if you hover over it with your mouse or with a cursor. Auto-completions, some basic support for refactoring. So for example, you can rename a method or a global variable at its definition site, and that will then also make the according change at every reference to it. And speaking of, we also have support for the go-to definition or find references tasks, I guess. You can get signature help. So if you're typing a function, then you get a list of methods of that function and associated types. There's some support for test items. So if you're writing a Julia test file, then you can, in theory, run those piecewise. In practice, I think that's currently in a bit of a brittle state. We have some very basic support for inlay hints. So if you type if you're inside of a method or inside of a function call, then we can, for example, give you information about which keyword argument you're currently, or which positional argument you're currently sort of specifying, right? Because those don't show up in contrast to keyword arguments. And we also have built-in formatting via Julia Formatter. Also, there are some custom request types for VS Code specifically. These could get used by other clients as well, but aren't right now because these are mainly required by some of the more interactive features that the VS Code extension itself requires. And yeah, I've listed them here. Basically, things like, if I give you this cursor position in this document, then tell me what module this is in. And that's, for example, required for the inline evaluation feature because that allows you to evaluate certain code into a module. There's also like some basic block analysis also required for inline evaluation, and that will tell you which is, like what's at this cursor position the biggest non-module block, essentially. So that's sort of our heuristic for figuring out which piece of code makes sense to evaluate in this context. And then there's also a bunch of stuff for documentation and tests, but I won't go into that too much here. Right, So if you remember that big stack of packages in that diagram I showed, at the bottom of that there was tokenize.jl. That's a library that I think Christopher wrote originally, and that breaks a text document or a string into a token stream, and that can then be ingested by a parser. It still exists standalone, but also is now part of JuliaSyntax.jl. And yeah, if you're looking at using it, that's the version you should use. It's a bit more up-to-date and bug-free than tokenize.jl itself. But yeah, in this example, you can sort of see how it works, right? It breaks the foo.bar string into a bunch of tokens and assigns byte positions and sort of kinds, right? Types. So foo and bar are identifiers, whereas the dot in between them is an op or operation. Yeah, and parentheses and all of that stuff is nicely handled. This token stream is then parsed into csdparser.jl, which, as the name implies, parses Julia code, but it does a little more than Julia's femtolist parser, which at the time was the only option. There was no JuliaSyntax.jl at that time, in that it gives provenance info for every syntax node that gets produced by the parser. And that's important because that way we can track error information, for example, back to your position in your document. Otherwise, every bit of like linting and whatnot would be super imprecise, and stuff like auto-completions, for example, would be basically impossible without some very weird heuristics. CSD parser produces a tree of expr objects, not the Julia expr, but all caps expr, and that can be converted to Julia expressions, as the last line in that code block shows. This all caps expr object looks somewhat similar to Julia exprs in that there's a head and a bunch of arcs, but it also carries a bit more data around with it. For example, like trivia, which is essentially white space, and also information about where in the document it occurs. An important point to make here is that the node kind is not encoded in Julia's type system, right? Expr is not parameterized on the kind of the kind of the node, and that has to be that way because of performance reasons. A syntax tree is notoriously sort of type unstable, right? You can't tell anything about which child node will occur in a given expression. So it would just blow up the type system essentially, and have a bunch of dynamic dispatch. This last field, meta, is used to put context into the syntax tree. This will be important in the next step. Whether or not it's a good choice to put all of this meta information directly into the syntax tree, I'm not so sure about. It's probably not the greatest choice. All right, let's talk a bit about static.lint.jl. Yeah, as the name says, it does static analysis of code. However, it does also a bit more than just linting, so the choice and name is maybe not the best. But the important piece to focus on here is the static part, right? All analysis happens without ever loading user code, right? And in a way, you can think about static lint as a reimplementation of lowering or parts of lowering. So it does binding resolution and scope handling and so on. But at the same time, it's a very basic reimplementation and certainly not a bug-free one. So that obviously opens its own can of worms. Yeah, static.lint.jl takes csdparser.expression as input and runs essentially two passes on it, right? Some initial marking of bindings and globals, some very limited macro handling for like very trivial cases like base.net at no specialize or also base.net at eval and so on. As I said, it handles scope analysis and reference resolution and sort of puts all of these into the syntax tree essentially. And then after it's run through a whole module, for example, it runs another delayed pass to re-resolve references that might have been defined in the meantime, because if you're recursing through the tree, you might run into bindings that actually get defined later on in the document. And lastly, it'll run some very limited type analysis as well. Yeah, this is sort of a very basic example here, right? 2 plus break doesn't make any sense. So if we lint the string, we get a error object put into the meta object of the first argument or the third argument of the first argument of the produced syntax tree, right? And this is okay. Yeah, a break should happen in a loop, right? Don't just write that outside of a loop. Writing rules, as we've heard, is not super straightforward. So this is a very simple case where it's just about checking if a non-data type is used in place of a type declaration. So this is a very localized example. However, everything that's a bit more complex or needs non-local data is pretty annoying to write. It does, however, have some support for figuring out where a binding comes from. So, for example, it can distinguish, let's say, test.addTest from just some arbitrary addTest macro that got defined somewhere else. It is technically possible to run static lint standalone, for example, in a GitHub action. But yeah, please don't. It's annoying to set up, and the output is pretty, yeah, it's not great. But it's technically possible. Yep. Okay, yeah, bunch of alternatives to sort of the static lint stuff, right? Relint, as we've heard. There's also SumGrep and Argus, which are 2 projects pretty much in their infancy. And then on the not quite as static side, there's jet.jl, which we'll hear about in a bit. All right, so the last piece, I think, in the language server box I had in that diagram is simulserver.jl, and that does actually handle everything that's got to do with external dependencies of the code base you're currently editing, so everything that got pkg added to the environment. This is not static at all, right? It's completely reflection-based. It loads your packages that get sort of enumerated in the environment. It extracts binding and method information and then writes that back to disk. So that is subsequent run of language server.jl on that environment can just deserialize the cache and use that information. Yeah, this is sort of the steps that simulserver runs through. So as I said, it loads your package with basically no compilation at all. So everything that we can disable gets disabled because that should hopefully speed up package loading by quite a bit. It fetches all names in all defined modules, so it just recurses through the module tree. It attaches documentation to bindings. It enumerates methods that get defined. It asks the Julia compiler for return type info. That's not always possible, right? But if you have a fully concretely typed method, then we can get some info on that. It figures out which bindings get exported or re-exported, and then in the end writes everything into a custom binary format because custom binary formats are great, right? Mainly for performance reasons. Deserialization needs to be fast. All right, let's really quickly talk about issues with the current language server implementation. First one is probably performance. Both static lint and symbol servers are not super robust and can run into edge cases where they just take up a lot of memory, and the Julia process might get killed or a computer might crash, stuff like that. It's not great. And also, if you run into very big documents, for example, MTK-generated files, right, a couple megabytes big, potentially very deeply nested syntax trees, then static lint basically ends up choking on those. Might also run into stack overflows because of the way it's implemented and so on and so forth. Yeah, a second sort of big issue is the power of this approach, right? It is fully static, so it can't really do any of the fancy stuff the Julia compiler does itself without invoking the Julia compiler, and to invoke the Julia compiler you need to load the code, which isn't static anymore. So yeah, we're out of luck in that regard. If we were to sort of relax at our working design goal of wanting the LS to be fully static, then it's possible to do a lot more. And that's something we'll hear about in a little bit. Macros are also very big issue, right? We can special case some of them, very few, but everything that's actually, does something that is reflected in the resultant syntax tree, we cannot look at because that also needs the runtime, right? Macros can execute arbitrary Julia code. Speaking of crashes. Oh, nice. Yeah, I think the Julia process was taking a lot of memory or something and got killed. Funny coincidence. Right, so other issues, maintainability and extensibility, right? We heard a little bit about that in the Reland talk as well. Static lint itself is not super pleasant to work with. Writing new rules is hard. And generally, all of the CST parsers, static lint, symbol server, language server, code base is a bit hard to get into. And also, it needs to be maintained in parallel to every implementation of the parser in Julia base. So whenever someone wants to add some fancy new syntax to Julia base, right, they make that change in Julia syntax.jl nowadays. But it also, someone also needs to make that corresponding change in CST parser.jl, which is extra work. All right, so what's next with the current language server? It'll be maintained for some definition of maintained for the foreseeable future, but it's fairly unlikely to be actively developed too much. However, there might be something else in the future. So I'll refer you to the next talk. And yeah, if there are any questions, we can maybe take some now, but otherwise I'll be around after the next talk as well. Thank you.
So if there are any quick questions, we can take it now, but Sebastian will also reply to questions after the next talk. So, yeah.
When you update the support for new syntax, what happens when somebody loads an older, like a file from an older version of Julia? Do you fall back to previous code version?
So the goal of CST parser is to support basically every Julia version since LTS. In practice, it probably supports a few more as well. And yeah, basically it switches based on the version the language server is running on. So there are a bunch of if conditions in there that look at the current Julia version. In theory, we could refactor that to look at, sort of supplied Julia version, right? So that you can run a newer Julia version and load older code. But in theory, it should all work, yeah.
Quick question. Thank you very much for study Clint, first of all. And what about syntax highlighting? Is it something that you are supporting, or because you haven't mentioned that? So
sorry, say again?
Syntax highlighting.
Yes, so that's not currently in the language server.jl implementation, but the LSP specified support for syntax highlighting. So yes, we could do that. And it probably wouldn't even be that much work, but also, yeah, performance sensitive. And I think the current, Julia, for example, regular expression-based grammars or the tree setter grammar for Julia aren't, that bad. So basically, no one's really looked into it so far.
All right, so let's thank Sebastian once again. All right, so while the next speakers are setting up, let me introduce them. So we have Shuhei and M, and they will talk about the new language server that they are currently developing. And yeah, so whenever you're ready, then
okay,
the floor is yours.
Thank you. All right. Hi, everyone. Thanks for joining our talk. I'm Shuhei, and this is M. We are software engineers of the compiler team at Julia Hub, and today we will be presenting a new language server for Julia that we have been working on these days. So let's jump right into it. So Here is an outline of today's presentation, and first we will give a brief introduction to this language server, and next we would like to demonstrate the features that are already implemented, as well as some prototype features that we plan to merge soon. After that, we will explain the internals of this language server, and finally we will discuss the current challenges this project faces, and the future roadmap, and before moving on to the QA session. Okay, so first, let me briefly introduce what this project is all about. So JLS is a new language server for Julia, and you could say that it's our attempt to create a new development experience by bringing together all the recent tooling technologies in the Julia ecosystem. And as its name suggests, this language server uses JET for its core analysis, but actually it's also built by integrating other tools developed in the Julia ecosystem, like the tooling stack for Revise. Specifically, we use Julia interpreter and lower code utils for enabling special execution of Julia programs and allows the language server to load user programs in a way it can manage. And it definitely uses jet.jl to enable static analysis and error detection for plain Julia programs. And it also uses Julia syntax and Julia lowering to allow moving freely between source code level and the compiler level. And by combining those technologies, we can support all language features, including macros, while also getting advanced information like type information directly from the Julia compiler and feeding it back to the user. Okay, so I will hand the mic over to Em, and she will take it from here.
All right. Okay, I'm a little bit shorter. We already have languageserver.jl. What is different? We won't be talking about languageserver.jl too much in this talk. Sebastian already did a pretty great job with that, but it is worth motivating our work a little bit, of course. And Sebastian was nice enough to just give us his diagram. So we can just take this and compare and contrast with JetLS. So let's take a look. First of all, we don't really do much stuff in the REPL like this. We do take their LaTeX and emoji completion, so let's like simplify that a little bit. We don't run it in a separate process, so let's just like absorb that box into the language server or something like that. We have better things than CST parser now. We have Julia syntax, and it's in base. So let's replace that. The ghost of tokenized.jl is in there for those who know. Now the next problem is static lint.jl. As Sebastian said, this is basically trying to replicate some of the functionality of lowering. And I think a very wise man once said that once you try and start guessing what lowering tries to do, problems start occurring. So let's just replace that with a Julia copy of the actual compiler lowering passes. More on that in a bit. And I don't know about all this RPC stuff. We definitely do not use a symbol server, so let's just delete that. Okay, we're almost there. Languageserver.jl, that looks like a redundant box anyway. Let's just get rid of that. And we are missing a few things. So let's just add jet in there. This is where the box drawing language has started to see some difficulties in dependencies, but Jet.jl also brings in some other cool technologies that Juhei mentioned, and of course, the compiler itself, which I think deserves a big box and also fills up the remaining space. So, ta-da, that is the Jet language server. Okay, so I sort of presented that like a joke, but it really is the real answer. There are a lot of things that didn't even exist and weren't even beginning to exist as thoughts in people's heads in 2016. Basically, the fundamental difference is that we have the compiler on our side instead of like making changes kind of against us and we have to catch up. This allows us to do a lot of cool things. We also sort of, we aim to be an enhanced user interface for jet.jl, which right now, if you use jet.jl, you kind of like go to the REPL, you ask for a report, and you kind of, that's a manual process. You interpret the report in all its Unicode box drawing character glory. Yeah, the intuitive user interface for that is just to embed it straight in the IDE, run that automatically when you're done the 5% typing and you're on to the 95% thinking part. Okay, I will pass it off to Shuhei to show off some of the cool features this allows us to have.
Okay, before diving into the demo, let's quickly go over the development status of this project. And I have listed, okay, the basic features that are currently implemented and those we aim to implement in the future. To be more specific, the items with a green checkmark are already implemented, while those with a gear icon are currently under development. And the unchecked boxes represent those we plan to implement in the future. So yeah, but I will demonstrate each of them shortly, so please just consider this list as a reference. And, as a summary of this, I think it would be fair to say that the most basic functionalities as a language server are gradually being put into place. Okay, so let's wrap up the introduction here and actually see what this language server can do. So let me quickly go over the setup first. So for this demo, I will be using a demo package.jl, a sample package. Which is a standard Julia package, about 200 lines of code in total, which has only one dependency of static arrays. And I will be using a VS Code as an example IDE frontend, but you can get similar features in other IDEs like NeoBeam or Emacs, whatever. Also, in the second half of this demo, I will showcase some features that haven't been merged into the JLS master branch yet. So if you want to reproduce this demonstration, please use rb/demo branch of the JLS repository. All right, let's start the demo. I will go to VS Code window. Okay, can you see the screen? Oh, yeah, we can see. The font size, can you see? Okay. So this is VS Code with demo package open, and the source file of this file is quite simple. This top level file only has two interfaces exported, hello and do math, along with this object struct that is used by this function hello internally. And a file named included is included here. So let's go jump to it. And as you can see, some error lines have already been issued. They are called diagnostics in terms of LSP world. And yeah, so first, this hello1 method, which is currently called from hello function here. This function is just implemented correctly, so no error lines are reported here. But for this hello2 method, there is some line which indicates demo package Y is undefined here. This is just because of this typo. And if you look closely, there is also underline here on this argument X saying unused argument X. So yeah, those two lines are just because of this typo, so we can fix it. And if we save it, this error line disappears. So JLS can report typo stuff, and also it can also report undefined local variables. So looking at this hello3 method, you can see this Y variable is returned here, is used here, but it's actually only defined in this else branch. So as a result, JLS is saying a local variable Y may be undefined here, just because it's not defined in this then branch. So if we make this method return here rather than keep going, then the error disappears. So yeah, JLS is capable to report this kind of stuff too. And yeah, here is a more advanced example, and so because JLS can fully utilize compiler information, it can also detect method errors. So there is a common mistake that plus operator here doesn't work for string concatenation as like in other languages. But even if we mistakenly use this operator like this, JLS will tell you, yeah, this plus call would result in a method error saying no matching method found for plus string. So yeah, this kind of analysis is something we cannot get from the existing language server. And to show more complicated example, let's imagine calling a sine function on the result of try pass like this. Yep. Yeah, in this kind of a situation, it might be, we might often forget the edge case where try pass returns nothing, but with JLS, we can see this kind of case quickly because it says this kind of case with diagnostic. So yeah, if we, yeah, if we fix like this using something macro, this return is not necessary. Yeah, then error disappears. So this function is kind of valid right now. Okay, to see other features, let's take a look at this doMath method. So this method performs various arithmetic operations on its argument x and returns value depending on the this let argument, which is default to this dicta symbol. And yeah, let's imagine a scenario where we have been asked to debug and fix this method and see how each LS features can help us. So first, let's take a look at tests for this do method function. And the tests are in runtest.jl according to the standard Julia package architecture. And now I would like to introduce a feature that we call inline test execution. So this feature allows you to run specific test cases or test sets in a file directly from your editor. And it uses a package I recently developed called test runner to selectively run specific test cases and display the result in the format of LSP diagnostic. So if you look closely, there is a button saying run a name of test set. So they are the entry points for the inline test execution. And we can click this to run each test set while skipping executing other test sets. So when I click it, we have a progress indicator here. And once the results are back, yeah, we get a result in line. And the errors are displayed like this. And there are a few errors, but let's look at the first exception, which is saying, yeah, this value is simply kind of unexpected value and incorrect. So let's go back to doMath function method. So let's see what's returned for the default value of ret. So if ret is specified as this default value of dict, it's returned here. And from the test case, we can see gamma value here is kind of wrong. So let's use go to definition feature to see where it's defined. Rather, just use a hover feature. So from this hover feature, it seems like this gamma is just a local variable defined in this function scope. So we can use go to definition feature by clicking this variable, go to where it's actually defined. And from this comment, it seems like gamma is supposed to be computed as a polynomial of x according to this this expression. So I would like to use eval poly macro for this, but I don't know how to use it. So I will use a hover feature for eval poly, and we can see documentation directly within editor. And according to this documentation, I think I can just place x as the first argument. And now you can see signature help would pop up here, saying that which parameter corresponds to which argument, which parameter of REPL poly macro calls. And yep, we can write like this. Now let's run the test again. So yeah, it's still running, but now this error is fixed. Okay, so yeah, I think I fixed the first test, but there are still errors, and yeah, this one indicates that we kind of need to handle these kind of edge cases. So let's go jump back to do method, and where it's supposed to be defined. So yeah, this seems to be implemented correctly, and I guess from the test, I think argument error is expected. So let's raise it here, and you can see a completion feature in action here, and also a signature help for those methods. Edge case. Also, completion would work for this kind of case. So it would be easy to change this code to throw like domain error instead, while saying constructors, definitions, and also from signature help here. Maybe, yeah, this kind of, it would be easy to refactor this code. So let's run again. Now the test should pass. Okay, I think I need to handle is none case. Maybe is none. Yep. Okay, so let's run. And also note that there are underlines here too, because this is just because local variable gamma, no, delta may be defined here, may not be defined here, just because we have this branch, but we already handled this case. We can just simply comment out. No, delete it. Then this function is now kind of clean, so everything works. Oh, so okay, no. Yeah, so this error is from the previous run from this test set execution, but now it runs correctly, so we don't have any diagnostic here. Okay, I showed all the basic features, but finally let me show you a prototype of an interesting feature. So through a feature named inline hints in the LSP terms, JLS can display the inferred return type for each method. So I have configured my BS code to show inline hints only when a specific keyboard is pressed. So let's try pressing it. So yeah, now we have a return type, inferred return type displayed here in line. And yep, let's modify this code to exclude this static vector case. Then JLS will update the code, and the inferred return type is also gets updated. So as you can see, we are making progress on implementing features that utilize typing information, and currently we can only show return types, but by fully integrating Julia lowering in the future, it will be possible to annotate type information for the entire method bodies. Okay, let's conclude the demo, and let's go back to the slide.
All right, thank you for the demo. Back to this goofy diagram, let's take a look at some of the technologies that we use inside JetLS, kind of how we use it and how it benefits us. So let's start at the very beginning of the compiler. Claire Foster and Tim Holy did a really great talk about this at last year's JuliaCon, but if you didn't see that, I can kind of very briefly summarize the Julia syntax and Julia lowering projects. Basically, one of the very main goals is to extend the provenance pipeline from your user input to the compiler, where provenance is just asking, oh, where did this code come from in the user's file? whether that be a code that is, a piece of code that is recognizable to you as like an abstract syntax tree or some sort of like meat grinder output from lowering, something like that. So we can trace it all the way back. So once upon a time, we had these line number nodes that kind of were embedded directly in the code. It's like, I guess, this contamination in the pipeline, because it kind of is. Basically, there are a few problems with these line number nodes. First of all, we don't get that horizontal provenance, which is not so much a big deal. Like, okay, you got the right line number, it's fine. But the problem is that since we're embedding these in syntax trees and not in like files, not every line gets a line number node, right? We just have to decide places in the syntax tree to put them. And for example, if you have a really long like short-circuiting operator thing that takes up a few lines, that usually just gets one line number node, and that's not ideal. Yeah, so Julia syntax comes along and gives us precise byte-level provenance for every single node in the syntax tree. There's still a problem here, like Julia lowering doesn't take that kind of provenance. It's still written in femtolisp, so we convert that on the way to lowering. This is still a huge improvement in the user experience, of course, because you all have probably gotten an error on 1.10 plus, and it shows you a really nice error message. It's like, here's your problem, here's your code. But you've also probably gotten code that passes through, that makes the parsing pass, but fails at the lowering pass, and it's like, error, syntax, $sign outside of quote or something. So the missing piece here is Julia lowering. We don't actually, the error messages are not even that much of a big deal. The big deal with Julia lowering is that you can also track backwards through all the lowering passes, which is really important because you know what comes after lowering, right? Yeah, we figure out the types after lowering. And the biggest problem is that we have the types, we don't know where they came from. And in a LSP, or in a language server, that is kind of an issue, right? JetLS is actually able to use Julia lowering today, just because not every question that you can ask a language server really needs the compiler or Jet. It's like, what are the local variables defined at this cursor position or something? So we are able to make use of Julia lowering right now. Yeah, but we do need Julia lowering integrated into base for certain features. It's also beneficial to us for a much more mundane reason. It's just written in Julia, so we don't need to go through the static lint.jl type of thing. Where femtolisp, you can imagine it as one big red button that says lower, and it spits out a whole bunch of SSA values and slots, and it's really useful for type inference, but not so much to us. We actually just use the first three passes of Julia lowering to resolve scopes right now. Let's see. Okay, let's move forward in the compiler.
Okay, let's take look at the next phase of analysis performed by language server. So first, let's assume we have low word code here. So this is quite a challenge on its own, as you might know from M's explanation, but yeah, we have some low word code here. And then we analyze this low word code using low word code utils.jl and roughly divide it into definition and usage. The purpose of this is that for JET's analysis, we actually need to load definitions of method and struct into the analysis process. However, if we were to execute all usages like top-level function calls, it would just become a regular program execution, and it's definitely not suitable for language server purpose. So we need to separate them from the definition code. Then we execute only the definitions using Julia interpreter, and executing only a part of a program like this is referred to as a program slicing in terms of computer science world. And so in other words, JLS implements a non-standard executor for Julia programs using low word code utils and a Julia interpreter. And now Jet comes in, and we analyze the usages using Jet with abstract interpretation technique. And by doing so, if a function containing an error is called, we can detect such errors without actually executing code. And additionally, JetLS also performs analysis from the definitions themselves, and specifically it starts abstract interpretation from the signature types of method defined by a package, and it detects errors contained within method bodies. So this way, analysis can be performed even if program doesn't have a main entry point or similar, so which is especially useful for package development or analyzing those packages. And after that, analysis cache containing potential errors, type information, and so on is created, and the useful information from that analysis cache is formatted in a way that conforms to LSP and sent to the client via JSON RPC. And this is an overview of the analysis pipeline of JetLS. And for your reference, I added specific algorithms and interfaces used by each component inside of dashed boxes. So if you are interested in more details, please refer to them. Okay, I'd like to hand it the mic to M to discuss current limitations.
Yeah, so this all sounds really great. I want cool new features. Should I install JetLS right now? My answer is like, if you're not working on something super huge and you don't already depend on languageserver.jl already, and if you like to live on the bleeding edge, I would say give it a shot. It's still very much under development. We haven't bothered making it super easy to install yet. There's a little bit of a process, although there are instructions for VS Code, Emacs, NeoVim, Helix, and Z on the README, so if you'd like to give it a try. If you use languageserver.jl right now, you might be missing a few features, so user environment isolation is a big one, where your dependencies and the JetLS dependencies might clash, so we just need to, that's just a bunch of work to do. Some Visual Studio Code specific features are there in languageserver.jl, which Sebastian mentioned. And like Revise, we get a lot of power from executing user code, so we would like to do a pass, making sure the effects of that and the safety of that is okay. A few other limitations, as I mentioned, large packages, it takes a little while. Again, if you follow the 5% typing rule, it's fine, but if you're doing a lot of like vibe coding or something, maybe it'll get annoying. If you save the JetLS project and trigger an analysis, it takes about 5 to 10 seconds, but it is still very usable, and both of us use it. We do need to upgrade the caching in that area. Analysis for dependency packages isn't supported yet, so if you jump there, no way back. And of course, it's Jet under the hood, so type instabilities can prevent accurate diagnostics. This is just a subset of the many things there are to do. I've personally been working on full integration with Julia lowering, where this is necessary for the type annotations, as I mentioned, and the precise diagnostics. Yeah, support for larger projects and support for recursive analysis I did mention, and improved diagnostics. We would like to improve the provenance on that, as well as we are working with a Google Summer of Code student who is working on a configuration system, so you get to turn off the diagnostics that are more annoying and stuff. And of course, we want to improve the messages in those as well. All right, I think that's it. Any questions?
I'm curious if you guys have any thoughts on how you want to approach generic functions. So if I have some function in my code base that doesn't have any argument type restrictions, then there's not much analysis you can do in Jet without the users applying something.
It's actually pretty much supported as far as other functions call that generic function with some signature. So JetLS can start analysis from other functions too. So if other function containing that generic function, it would be analyzed. And also, if your test cases containing some function calls that use generic function, that would be also analyzed. So I think even if you don't add type annotations to every your generic function, they can be analyzed. But just because of type instability possibilities, it's preferred to add type annotations if possible. So yeah.
Since we have you all in the same place, what are your thoughts on integrating these two or replacing JetLS, like taking the core JetLS technology and using it to drive the original language server? Like, what are the parts of the original language server that we need to keep and add to this, and what are the parts that we can drop and replace?
We did plan for this question. Is this your slide or mine?
Yeah, so there's no immediate plans to replace the language server used by Julia VS Code by JetLS. But in order to do that, integration into Julia VS Code infrastructure would require some work, like implementing its specific LSP features just for the purpose of Julia VS Code extension. So like we need to implement Julia/get module art, but basically it's only the requirement to make JetLS as a backend of Julia VS Code extension. But I think JetLS is still pretty much in alpha at this moment, so I don't have immediate plans to switch, make it possible to use as a backend of Julia VS Code at this moment.
Right, so there are some more questions, but I think we should close the session now and take them afterwards. So thank you again to the speakers, and we continue after lunch with this.
Okay, good.
Yeah.
Test, test.
All right, so it's time to start. So the next talk in the session about tooling is from Christopher. and he will talk about interpreting Julia code. So go ahead.
Thank you, Fredrik. So yeah, my talk is called Interpreting Julia Code, but first we need to talk about what is interpretation and how it differs to compilation. And it's a little bit hard to give like really solid definitions, but it's kind of a little bit hand-wavy, but with compilation you often do like a full program analysis and then you produce some kind of artifact that you then directly execute like a program. With compilation you often do some kind of full-scale optimization on the whole thing in one step and then you run the code. And you often catch some type of errors before you actually run your code. With interpretation, you kind of do things as they come, or you do execute code statement by statement without doing much analysis up front. Most decision making is done during the runtime, and you don't cache so much of the processed code. You can cache some kind of like bytecode from it. There's typically not many optimizations, and you often have some kind of a virtual machine running that does dispatching to instructions and store things like function argument variables and so on. So what's Julia then? Is it compiled or interpreted? I would say Julia is definitely compiled. There's no like virtual machine running. It compiles to machine native code, but it's done in a little bit special way where code is compiled incrementally and more on demand, but it's still compiled. Errors, though, are usually delayed to runtime. So if a type error is thrown in the forest and no one is there to hear it, does it actually cause any harm? With Julia, we say no. But there's also work in more traditional upfront compilation with Julia. So we have this --trim, and there's a talk later about that here. So why would we want to interpret code? Well, we can just ask ChatGPT, right? So let's see what it says here. It says that you can have rapid feedback and iteration, and you can see the result immediately in the REPL. But I mean, we have a REPL, right? Dynamic features, reflection, runtime code generation, evaluating user-provided scripts on the fly. I mean, we have reflection, we have revise, we can do this even though we're compiled. Simpler tool chain, no separate build link step. You just install the interpreter and run it. Well, we just install Julia and run it. It's pretty easy there too. Graceful error handling, errors surface exactly where they occur, and if you know in Julia the stack traces, they also surface exactly where they occur. So it seems that there's no reason to interpret Julia code here according to the all-knowing ChatGPT. But in Julia there's actually a few reasons. One is to lower latency. Running the full Julia compilation pipeline can take a bit of time, while with interpretation you just start executing straight away. And if you're running scripts or just top-level code where it doesn't do that much work compared to the time it would take to compile it, it might make sense to interpret instead. Sometimes with Julia, you might not have a compiler available in some certain scenarios, then you can fall back to interpretation. And you might also have better debug information. With native Julia code, it's hard to sort of execute it interactively, step by step, and see what's going on. It just kind of goes by its own and executes for you. So if you're doing it in an interpreted way, you have more control over the execution. You can track things like the exact state of the program, the local variables, and so on. So first I want to talk a little bit just for some background about the Julia compilation pipeline. And Julia, I would say, have almost a unique set of tools to follow through the exact compilation pipeline. So we can start here. The first step is that we parse the code. Code comes in as text, but it's kind of hard to programmatically work with text. So parsing turns this text into a more structured form in the expert data structure in Julia. And Julia now uses juliasyntax.jl for this. It used to do a scheme version, which is still used for bootstrapping, but after that's done, then it's the Julia one that takes over. And macros work on this level, so it takes an AST, which is what you get after parsing, and returns another AST. Then after you're done with parsing, you move on to lowering. And lowering kind of simplifies the richness of the whole surface language or the whole AST into kind of a smaller set of building blocks. And all future analysis can then work with this simpler structure. And this does not depend on input types to a method, for example. So if you lower a method, it doesn't matter what the input types are. The lowering doesn't know really what's type and so on. It's kind of a syntactical process. So some things that lowering do is macro expansion. So if you have a show macro, it expands that to what the macro says it does. You do scope resolution. So if you have variables X that are in different different locations in your functions. It might not refer to the same variable, so which x's are actually the same variable. It does control flow linearization, so if you have if-else stuff, it changes that to just go-to branches. It does the iteration protocol lowering, so if you have a loop, like a for loop, it changes that into iterate calls. It does some other things, function calls. If you have string interpolation, it changes that to string function calls. So if we go back here, we used to have this mySum was the text there, and then after lowering, we have something that is more, it looks more complicated, but it's more simpler in a structural way. So we have the iterate calls there, for example, and so on. The lowering is right now written in Scheme, but if you've been here earlier today, there's a lot of talk about this Julia lowering, which is a Julia version about for lowering, and that's in progress. I put 1.13 question mark, maybe. We'll see. Then after lowering, we move on to type inference, and what that does is it assigns a type to every statement. So we have exactly what we have on the previous slide, except now after every statement here, you can see there's a type. And this is sort of the driver for almost all future optimizations. If you don't have types, there's not that much you can do. Not all statements, though, might resolve to a concrete type if you have like type instabilities, or if you write the code in a sufficiently complicated way, there might be some approximations done by type inference, but that's the step to get types and everything. Then we run the Julia optimizations. Now when we have types, we can sort of resolve what actual methods we are dispatching to. We can do something called scalar replacement of aggregates, which is if you have, for example, tuples, which is a sort of a collection of things, so we can split that out into its components. Constant folding, if things are constant, we can just compute them before we even run it. Dead code elimination, and the slot to SSA conversion, which is if we look before, we have these local variables, s and x and so on, while now after they are not even represented there, they've been turned into an even more simpler form. And we don't have really any function call here except to the most basic built-in function calls. And then we turn this into LLVM IR and run the LLVM optimizer on that. And there's both Julia-specific LLVM optimizations, but then also the general LLVM optimizations. And at this point, if we look at LLVM, we basically, there's no traces that this originally was Julia code. It's sort of gone down to this code could have come from any language. And then finally, LLVM selects actual instructions that will run on the CPU based on the current CPU target. And in this case, what we ended up with is these SIMD instructions for doing multiple additions in one CPU instructions. So we started with just a loop with plus, and in the end we ended with, this is for one iteration loop. It has done some iteration unrolling, so it does 4 of these for every loop iteration. And if you want to write an interpreter, then I would say the lowered code is a pretty good abstraction level, because if you haven't run lowering, there's a lot of things you have to do, like the scope resolution. You have to do the loop to the iteration protocol, and after lowering, you have a more simpler thing to look at. You could also say maybe I want to run type inference on that as well, but that adds some latency, and if you don't add any more further optimizations, there's not much point of having types everywhere. You could use it to divertualize some calls, but I don't think that would give you very much. And if you go even further with optimization, you lose quite a bit of debug information that for the things we're going to use it for here is pretty important. So if you want to write the Julia interpreter, what is it that you need? Well, first you kind of need to manage the state, which is these say SSA values. If I go back, every line here is an SSA value. It just makes it easier that every single statement has one value. You need to have check on the local variables, where you are in the program, the call stack, the static parameters, and so on. So you need to manage the state, but also you need to do the execution, which is like, okay, now I'm going to run this statement. It has something. I'm going to do the control flow, the go-to stuff, and so on. And then this is not really needed to interpret, but having some debug functionality like breakpoints and inspect local variables and so on is nice. So there is an interpreter in Julia itself, which is written in C, and it's used in some cases. So for top-level code that is unlikely to benefit from compilation, like it doesn't have any loops, for example, then Julia will try to interpret it instead. if there's no compiler available, or if you have disabled the compiler with this -- compile flag, it will interpret things. And there are some fallback cases where it will try to interpret things where something went wrong with the compilation. Yeah, as I said, it's written in C, but it's not really made with debugging as a goal. It's more like I would say a latency thing and also this fallback thing. And if we just look a little bit at the code, we have some state here, and just by looking at the names, we have the local variables are stored in some variable here, static parameters, like what module we're interpreting now, so we know if we're accessing a global. And this is a bit of a slide code, so I've removed some stuff and so on just to try and make the point, but we have some state here, and then we have our execution engine where we evaluate a statement, and then we're looking what type of statement it is. For example, is it a go-to node? Well, then we set the instruction pointer where we're going to execute next to where that go-to node tells us where to go. If it's a go-to if not node, we have to evaluate the condition, and depending on that, we might go to that one. If it's assignment here, we have to calculate the right-hand side and where to assign it and so on. So we basically have, for all types of statements we can have, we branch on that and we do what it means. So that was the C one. Then there's also JuliaInterpreter.jl, which is an interpreter for Julia code, but it's written in Julia. Just to give some history, it was originally called AST interpreter, started by Keno in 2016, and it was used in the very old debugger called Gallium. Then it was branched off as AST Interpreter 2 to kind of still work with Julia even though Gallium was discontinued. And then Tim Holey took over in 2019 and further did a lot of development on this. It got renamed to Julia Interpreter. And then I, Sebastian, Shuhei, and other people have done some stuff on it as well. And it now powers a little bit of Jet and the command line debugger, the VS Code debugger, and Revise. It's used for those. So if we look a little bit on the code in Julia Interpreter, then we also have some state and we have an execution engine. So the state we have is quite similar to the one in C, but there's a little bit more stuff in there. So we have some scope, which is what method we're evaluating, all the statements, and things like that. And then we have local values, static parameters, and so on. Everything we need to keep track of to interpret. And then gets put into a frame. So that's sort of the state, and then we have the execution. So we're stepping an expression here, and we're checking what type, again, the statement we have. If it's a goto node, then we set the program counter to that, what that goto node says. If it's a goto if not, we do this. If it's an equal, we do this, and it continues. And then we just move on to the next statement here. So if we just compare a little bit the structure of the C interpreter versus Julia interpreter, you can see it's virtually the same. We have the checking for the go-to node here in C. We do the same in Julia interpreter. We're checking for the go-to if not. We do the same here. Assignment here. So they're kind of structured very similarly. Yeah. So there's good stuff and there's bad stuff and there's ugly stuff about Julia interpreter. So let's start with the good stuff. So I would say that Julia Interpreter currently powers many useful tools, and that's sort of one of its strengths. It has enabled a lot of useful tools to be built on top of it. So the first one is debugger.jl, which is the command line debugger. So we're keeping with the mysum function here. If you load the debugger, you can enter it, and it shows you the code here. You can add a breakpoint at length, for example, and then if you continue, you hit that breakpoint. You can show the backtrace, and you see all the local variables, and you can execute code in here, and so on. So it's a pretty good debugger, I would say, for if you have quite simple code. And that's sort of built on top of the Julia interpreter then. And then there's also the VS Code debugger, which is works in a similar way, except that it's just a different graphical interface presented to the user. So you can also set breakpoints here, and you can see the local variables and do expressions that gets evaluated every time you step and so on. And Revise also uses Julia Interpreter. Most of you probably know what Revise does, but just as an example here, it can hot reload your code. If you have it in scripts or packages, you just edit the code, and it's going to immediately notice that and update your code in your session. So here's one example. If I load Revise and I use this include T, it's going to start tracking any changes to this file. And if I write it out now, it's just my some function that I have here, but if I went into my editor and I added this thing without having to include anything else, if I just run the function again, it added this hello JuliaCon to it. And it's also used in very few, but some packages actually use Julia Interpreter to speed up their tests. So in chainrules.jl, they're using Julia Interpreter because they are so compilation time bound that just interpreting their whole test suite is faster than having to compile the whole thing. So what they did here was that instead of just including the test file, they just interpret it instead. So some more bad stuff about Julia Interpreter. Well, one thing is that its speed is not very great. So if you remember, after we did all the optimization with the normal code, it turned into 16 additions per loop iteration, and that was 4 SIMD instructions doing 4 additions each. Now, if we look at one single iteration in a loop, Julia Interpreter has to get through all of these functions and built-ins and so on. And every time, we don't know, like we have to resolve which are we gonna dispatch to, and we have to look like, is it this type of statement for everyone and so on. So it has to chug through quite a lot just for a single loop in this, while when we did optimization, we did 16 loops with CPU instructions. And I mean, the way we write Julia code is that we know there's going to be an optimizer that runs things. So we don't worry about small functions. We don't worry about like tuples that they're going to get allocated because, you know, the optimization is going to take care of this and so on. So I'd say Julia code is a little bit of a tough case for an interpreter because so much of it is written with the knowledge that there's an optimizing compiler there. There's some stuff you can do to try speed things up, and that's by not recursing your interpretation down in sort of uninteresting modules or methods. So if you don't care about, I don't care about any debug stuff in base, so I'm just not going to recurse down with the interpreter there. I'm just going to run that compiled. But sometimes, if you write some certain syntax, if you do that, you'll miss some things. So for example, if I write a comprehension like this with G gets in this comprehension, if we actually look what's going to get executed, we're going to create a generator with some anonymous function here, and we're going to collect that. So if I just ignore base, I'm going to miss the calls to G here. So if I would want to be interesting, if I maybe had a breakpoint on G, if I just did this, I'm going to not hit that breakpoint because when it runs, it's actually going to run in compiled mode. And Julia is often used for computationally heavy workloads, as you know, so your own code might be the thing that takes time. But for me personally, quite often, you know, just making the input a bit smaller works quite well. And instead of running your full finite element code on it, you just run it on like a little smaller mesh, for example. Another thing that's a bit bad is it can't really follow into the runtime and scheduler. So if I have two similar functions here that just does something in a loop, one does it normally and one does it in a thread, and then I set a breakpoint on G here. If I just interpret this normal F, then I'm going to hit the breakpoint, then Julia Interpreter is going to, you know, stop and tell me, okay, you hit the breakpoint here. But if I run this thread, it just goes through it and it misses the call to G here because this actually gets passed into the scheduler and that's written in C and so on, so we can't really follow the execution through all the way there. It's also quite heavily tied to Julia internals. So many times when people change the Julia internals, they also fix up the interpreter in C, but maybe they forget about updating Julia Interpreter, and it's always lagging a little bit behind the state of things on the master branch. Revise uses Julia Interpreter, and that's actually tested as part of CI, but just because the revise test pass, it doesn't mean that Julia Interpreter is actually fully functional. And sometimes core contributors can be a little bit like, oh, I made this nice internal change, but now I have to update this Julia Interpreter code that's all messy and not how I would have written it. So it can be a bit of a friction there. Some of the more ugly stuff, I just had to put some stuff in here so I could get all three parts into it. But so one thing is this wrapper step through. So sometimes Julia creates this internal wrapper functions, and you'll see that is. So if you have default arguments or keyword arguments, so if we look here, I'm creating one function takes x and then y, which has a default argument now, and also a keyword argument, and it just adds them. Now, if I enter this with the REPL, you immediately goes to this x plus y plus z, which is what you expect. But if I actually look at things, if I look at what the lowered code of f(1) is, it just calls another function with this 1, which was the default value of y, put in there. Okay, but then I look at that one. Oh, but then that calls something a little bit strange here, because now it has put in the keyword as well. Okay, so now I look at the keyword, and then it does a bunch of sorting, and it defines this other weird function, and so on. So finally, I'm here with this var, some strange things, which has a bunch of stuff in there, and that's where the actual body of the code is. So Julia interpreter and the debugger sort of have to realize, like, all this stuff, it's not really interesting for a user, and step through that. And doing this pattern matches, that changes with the Julia internals, can be a bit messy. Another thing is C call and C functions. Those require a compiler to run. If you look at the C version of the interpreter, it actually, if it hits one of these C calls or C function, it's just going to error. Because you actually need a compiler to be able to do this properly. And in Julia interpreter, we actually look through the code and see if there's going to be a call to a C call or a C function. And then we kind of move that call into a separate function that we actually run in compiled mode. So we cannot fully interpret the whole language. We have to use the compiler for those parts. A little bit about the future. One possible thing is if we could merge ASD interpreter, the .c, the C version, and Julia interpreter. I mean, it would be nice to only have one implementation, but they also serve quite different goals. The C one is mostly for latency and things like that, while the Julia interpreter also tries to provide quite a lot of debug information, and it's possible there's a little bit of conflict there. Maybe having all this debug information makes it slower. So, yeah, I'm not sure. When it comes to the speed, maybe we can have some more friendly bytecodes, friendlier code to interpret. There's some ideas in the pull request here from 2019 by Tim Holy. It hasn't gotten a lot of attention since then, but with Julia lowering.jl coming, I would say that probably brings a lot of new ideas and freshness and willingness to work on this. So it will be quite exciting to do this. I mean, maybe someone creates a whole new interpreter from scratch based on Julia lowering, or maybe Julia interpreter gets updated. So yeah, I think when this Julia lowering is in place, quite a lot of interesting things can happen when it comes to Julia interpreter. Yeah, that was it for me. Thank you.
Can you go to the slide with the generator example?
Yes. Was it here? Yeah.
Yeah. Okay, so I think I suggested this once before, but I don't think anyone understood me. It seems to me the way to fix this is that when you, instead of passing G into the generator constructor,
you're not actually passing G here. You're making a new closure that passes in the X here into X2. But
it's the closure that calls G. But yeah. But there's some function there.
Yeah.
There's a closure. So instead of passing the closure into there, the way to fix this would be to wrap that in a new thing that calls the interpreter on the closure.
Yeah.
Right? Because then you have compiled code which calls a function which re-invokes the interpreter.
Yeah, you would sort of lose the way you got there, I guess, all the steps on the way until you start up the interpreter
Right,
afresh.
you'd have to have like a stack trace that you.
Yeah, but maybe you don't care so much about exactly how you're going through base to finally end up at your function.
Yeah.
So and then
couldn't you also, like anytime there's a breakpoint in a function, replace that function with a version of that function that is the interpreter interpreting that function?
Yeah, so I think there's been some attempts at doing that on like a bigger scale using, I think it was cassette maybe, or at least something that like uses the invalidation thing to, you change one function to have a breakpoint, and that sort of invalidates code and then when the compiled code calls that function, it calls the new one. It might work. I'm just a little bit worried about latency in that you have to recompile code and so on that's going to call that one. But and it's the same there. You're losing the path you took to get there because you're starting up a new interpreter session there. But yeah, that's also an interesting thing to work on.
If I can also comment on that, I think when we were first working on Julia Interpreter, we actually also had two goals, really. One was to get a functional interpreter, but the second was a possible application, and you mentioned it in some packages, using it to speed up their tests, as an experiment in whether we could interpret more things in Julia and not hit the compiler so much. So we very deliberately were trying to not do anything that would generate extra compilation in how we went at it. I mean, I think we know much more now, and we have package image caching and all this kind of stuff. So I think we could revisit, in principle, those decisions. But you know, it would be there would need to be some fairly fundamental work done to implement.
For the generator case, I think you've got a closure there already, so why not pass the interpreter state through the closure? So you can just continue on in the interpreter.
Yeah, well, you still lose sort of all the intermediate steps in between, but then maybe you can sort of patch things up between the time when you call G and F. Because I mean, if there's many steps within base tier that finally ends up calling G, you're not going to have all those steps. So I mean,
well, in this case here, this is a Julia generator, right? So you can actually generate whatever code you want, right, for that for loop. So you could track everything, I think.
Yeah, but at the same time, we kind of want to not do too much processing, I guess. We kind of want to be at the part where we're just blasting through the stuff here, basically. Because if we do too much, I mean, in the end, we just have a new version of Julia that has better debuggability. If you take this to the actual limit of improving things and making it faster and so on. So, at least to me, there's always this thing like how much work should be made at making like optimizations for this and so on, versus maybe another path is to, when it comes to debuggability, is maybe try to make Julia itself more amenable to debugging. Like most languages don't need an interpreter to be debugged. They just work with a debugger. So that would be, I would think, quite a lot of work. But maybe that would be, if we're on a local optimum now, maybe that would be more of a global optima where Julia itself is better at getting debugged. But it's hard because Julia is JIT compiled and it does many things in a kind of a non-standard way compared to how debugger are used to see code getting executed.
All right, one more quick question. If not, then we thank Christopher again.
Thanks.
And now we take a break from the mini symposia here on tooling, and I think there's a keynote in this room next in 5 minutes.
How are you? Start mirroring? Yeah, mirror's good. Yeah. Yeah, I don't have any. I don't have any notes. Notes. Okay. There we go.
Should I use this mic, or is there a lavalier? How about whatever? I don't mind walking around.
Okay. Got it. So no wearable mic. My computer's on a death, like it's got the death spinny thing. So I think I have another application open. I'm going to close it because it's being really, yeah. It's an M3 Max, so it's not like the chip. It's probably the memory or something. Okay. Yeah, I should probably shut down VS Code. I had like a simulation model running in the back. I should probably shut that down. So. All right, let's see. Not at this moment. It's not, that's on pause right now. All right. So I think now I should plug it back in, and then when it asks, I'll do. And then I have until roughly what time? I know you guys will have the time cards up, so I will take advantage of this.
So we'll have the time card up for, you roughly have 45 minutes, I would say. I mean, assuming we start now.
Okay.
And yeah. Yeah, 45 minutes.
So we're looking for. Cool.
From whenever you start, it's 45.
Okay. Yeah. All right. Sounds good. And then you guys will have that up, and then I'll put some. Yeah, I have a timer, so that way. Thanks.
But I think we can just get started.
Okay.
Maybe I'll go ahead and announce it. Hey everybody, could you please take your seats, please? There's plenty of seats over here as well, so feel free to come take a seat. So before we begin our second keynote of the day, I just have a couple of conference committee announcements that we'll quickly get through. Just another reminder that we've obtained sponsorships and partnerships with several local restaurants in the area. So there's Pimante Bros, that's on 3803 Forbes Avenue, Colombian Spot, K-Town Snack Bar, Hello Bistro, The Porch, and there's plenty of offers with all of these restaurants. Please come to the registration desk and find out more. And just help support the conference. It would help support the conference if you did. Appreciate it. Thank you. Without further ado, I'd like to introduce our second keynote speaker of the day, Dr. Karandeep Singh. Dr. Singh is the Joan and Irwin Jacob Chancellor's Endowed Chair in Digital Health Innovation and Associate Professor in Biomedical Informatics at UC San Diego, where he also serves as the Chief Health AI Officer for UC San Diego Health. In these roles, Dr. Singh leads AI initiatives within the Jacob Center and oversees AI strategy and governance for the health system, which is also going to be the subject of his talk today. He is also the maintainer and author of Tidy.jl and the associated ecosystem, and is a big Julia user. So let us give a round of applause for our speaker and welcome him to the stage.
Thanks, everyone. I'm excited to be here. This is my second JuliaCon. I started learning Julia, I think, 6 months before the 2023 JuliaCon and attended 2 years ago. Wasn't able to make it last year, but I'm really honored to be here to talk today. There won't be actually that much about Julia. I'll share some very high-level thoughts on code tooling to do operational AI stuff and kind of what things are helpful. But I wanted to keep this focus maybe on use cases, just to give you a sense of, I hope you're at the end of this talk, you're excited about some of the challenges we have in healthcare operations and can see how Julia and tools like Julia could be useful in helping us actually improve health systems in ways that I feel like in many cases are actually solvable, tackleable, as compared to many other things that are happening that are very tough to address today. So I have one disclosure, which is that I serve on the Consumer Health Advisory Panel for Google, and a little bit about me. So I currently am the Chief Health AI Officer for UC San Diego Health. I have a leadership role in the Jacob Center for Health Innovation, which was funded by Irwin Jacobs of Qualcomm.
And within that, I oversee an AI lab, which is an academic research lab within our kind of operations center. So it's essentially an academic lab charged with tackling health system operation problems where we're trying to bring the tech, but also partnership with operations to make sure that the people changes that need to happen so that the tech that we build actually is used to drive change. I'm also a kidney doctor, and although I don't work that much clinically, I work about 4 to 6 weeks a year. This week I happen to be working in the hospital, and so I have someone covering me today, so I appreciate Dr. Garmala covering me today while I am here, and I'm gonna fly back tonight so I can see my patients tomorrow. And then lastly, I'm a Julia user and developer, and as was mentioned, I have taken really dived headfirst into developing tidier.jl, and I'll share at the very last slide some of the 3 other talks that'll be happening. So I'm not going to talk much about tidier.jl today, but there are 3 other talks happening where you can learn more about tidier.jl and what we're trying to achieve. But it's essentially R's tidyverse re-implemented from scratch in Julia. From scratch is maybe too strong of a word. Implemented on top of best-in-class Julia packages to bring the R syntax from tidyverse into Julia. Okay, so how did I get into healthcare operations? My dad is a computer scientist. I grew up writing software. I ended up in healthcare, and I ended up doing biomedical informatics. And I was in the midst of the pandemic studying a set of models that were actually starting to get used now in healthcare. Prior to 2020, the biggest issue in healthcare with AI was you could do it on paper, you just couldn't do it in the real world. There was no way you could actually bring those things at scale and run them within the electronic health record, which is the main kind of operating system when it comes to healthcare. So starting around 2018, 2019, a lot of the tools, kind of independent of COVID, started to become available, and many health systems were starting to use AI tools much more broadly than they had ever used them before, with almost no, and in many cases, no independent evaluations published for any of the AI tools that we were using. So I had just kind of taken over the role of starting our AI governance back at University of Michigan prior to moving to San Diego. And one of the first models we looked to evaluate was a sepsis model developed by the electronic health record vendor. This was a model in use by hundreds of hospitals, and we were considering using it ourselves, and so we took it upon us to say we should actually try to do an independent evaluation, and we approached this in a really pragmatic way. We went to our sepsis committee. Sepsis is a body's response to a bacterial infection that makes you very sick. So we went to our sepsis committee, who are experts in this, and said, do you have a way to measure the quality of sepsis care? They said, yes, we have software we use, we have rules that we use, and we assign actually who has sepsis and who doesn't after the fact, and we assign a time zero of when that sepsis came to be, because a lot of these tools are being used in a dynamic way where they're generating predictions, let's say, every 15, 20 minutes. And so you'd want to make sure that you're not considering predictions made after the fact in actually driving care, at which point the care has already been driven by the clinician. So we found a little bit surprisingly at that time that the model that was in place in the EHR, commonly used around the country in the US, was not a great model. Later it came to, through journalistic investigation, it came to be discovered why. They were using a lot of the factors that clinicians use. They're using a lot of the evidence that clinicians essentially use as like treatments for sepsis to drive the prediction of sepsis. So it was like, doctor sees sepsis, starts treating sepsis, and now suddenly the model says, hey, I think the patient has sepsis. And that was kind of discovered as part of this evaluation process. This really got me thinking about all the things that we do in healthcare that touch technology, AI, where there's really no evaluation, and there's just a project management style, let's implement, and not look back and see did it work. And I wanted to see if I could try to change that through my kind of hybrid operations and academic role at University of Michigan. So this caused some press. This evaluation ended up being published in a bunch of news stories, and one of them by Washington Post. It ended up influencing the FDA's guidelines and what they consider to be a medical device. Prior to our paper coming out, sepsis models were not considered in scope of the FDA. And when they issued their final guidance after our paper came out, suddenly it was now in scope of the FDA. And obviously that may change now, but that's, at least what some of the impact was with some of the work. And then actually, when the White House under the Biden administration published their AI Bill of Rights, which said, not, what are the real Bill of Rights of the AI, it's what are the Bill of Rights of humans working with AI? So what rights should we have as humans? The first example they shared under unsafe or ineffective systems was the work that we had published on the sepsis model. So this is kind of the thing that really led me into both looking very, ground up at ways that we're using tools. That was something that, I'd written every line of R code myself to do that evaluation, all the way down to looking at how it impacts policy and how it impacts healthcare operations. And so I think something about that made me really kind of like, we need to do a lot more of this, and we need to now think, if this doesn't work, what's the alternative? How do we think about AI differently than simply as a bolt-on onto the way that we do practice medicine currently, which is not, always ideal. Okay, so health systems 101. What the heck is a health system? In every country, this term means something completely different because health systems vary a lot. In the US, there are micro health systems all over the place. So when someone says health system, they're not alluding to the US health system unless they say US health system. They're almost always alluding to the health system down the street, which may be a national chain, maybe regional, maybe local, maybe academic, maybe community. So it's really just a way of organizing the care and resources that people need when they get sick. And this is examples of some of the places where people interface with what they would consider a health system. There's a saying that if you know one health system, you know one health system. So anything you learn about one health system is not generalizable to any other health system. That's probably 80% true. I think that obviously the certain operations that every health system does are shared, but because of institutional culture and knowledge and just the ways that health systems kind of made some of the decisions they made along the way to get to where they are today, you can walk into one health system and something is totally normal, and you walk into the other health system, and that thing that one health system does would be considered completely bizarre and like why would they ever do things that way? So I think when you're entering these systems, you have to come in with a bit of humility. You don't come in with a solution. You kind of understand what is the way that the system has evolved, and how do we go about changing it, understanding what it looks like today. So I would say healthcare has two components. One is clinical care, and one is operations. So clinical care is we want people to get the best diagnosis and best treatments possible. Whereas healthcare operations is that we want to make sure care is as safe and efficient as possible. This is not unlike Amazon in some ways. So Amazon, has a team that works on their recommender system and makes sure that you get the best recommendations so that you're kind of hooked and you want to use the website. And then they have probably a separate team that handles logistics and delivery, because that's another part of their core business. You might really like the product, but if it doesn't get there on time, you're not going to be happy. And so similarly, healthcare has kind of that similar breakdown between, yes, we want to get you the best possible care, and that's why people choose certain health systems, but also we need to make sure that we don't make mistakes in the process of trying to deliver the best possible care. So a lot of this talk is actually not going to focus on clinical stuff. It's going to focus on what many people view as the boring stuff, but which I find is like the cool stuff. Because this is the stuff that you actually can easily change, because a lot of this stuff has evolved in ways that is just by chance, not necessarily that was the right way for things to evolve. I know most folks here are not in healthcare, but I'll just say it's an amazing time to be in healthcare. CAR T treatments came out a couple years ago and are basically curing cancers that were incurable. Refractory B-cell lymphomas was something that you died of, and now people get CAR T and they're walking around and they're totally fine, and it's essentially like they're cured. This article came out, I think, earlier this year. Kidney transplant with pig kidneys had been tried previously and always failed, so they went and they gene edited the kidneys for the pig to make sure it didn't react against humans, and gave it to a person, and the person eventually died, but they didn't die of kidney failure. They died of other things. And so there is potentially a pathway towards completely changing the supply chain around organs, which is actually one of the biggest and most effective treatments we have today when you have organ failure, is to give you a new organ. And right now that's limited by the fact that someone has to die in many cases for some of the organs, like heart transplant, for you to be able to get an organ. And so this opens up a whole world of possibilities in healthcare that simply wasn't possible even like 5 years ago. And then of course, CRISPR-Cas and the technology around gene editing. This is the case study published in New England Journal of Medicine where 2 patients with different types of disease, one of them being sickle cell disease, which people think of as incurable, had been gene edited out, and suddenly they don't have sickle cell disease anymore because they can now produce hemoglobin. So these are things that were science fiction 5 years ago, and they are like things that we can do today. So I just will say the clinical side of medicine is still super cool, but I'm gonna now use that to transition into the operations side of medicine, because we have to make sure that those treatments can be made available to people, because as we get more and more treatments, we have less and less capacity within our hospitals and our clinics to actually see the people to actually deliver those treatments to them. So healthcare is a continuum. People are at home, people are in clinic, people show up in the ER, people go to the hospital, and then after the hospital, they either go back home, or they need rehab, or they need long-term acute care, or they need nursing home. And I think as we think about, from a health system perspective, emergency and hospital are obviously like core to the health system. Clinic is a core part of the health system, but when any of these things has a transition state that gets backed up, it causes problems upstream. So we have problems getting people in for surgery in the hospital. You suddenly have problems getting in to see a doctor in clinic. And I think many of you who have seen kind of recently how much more challenging it is to get in to see doctors, a lot of that is a supply chain sort of issue where we have issues on the inpatient side and that spills over and makes it issues on the outpatient side. Okay, so how does operations look? And then we'll dive into some examples and some simulation stuff. Is on a macro level, health systems are constantly balancing inpatient and outpatient capacity. Inpatient is beds in the hospital. Outpatient is being able to see people in clinic or do virtual visits. So this is constantly changing. The things I just showed you, if we have a way to suddenly cure incurable cancers, we need a heck of a lot more inpatient beds for cancer care that can deliver those treatments, because those people don't go home the next day. They have to stay for a week or two to let their immune system reconstitute. And so suddenly, that creates an inpatient problem. So if we can see them in clinic, but we can't treat them, that doesn't solve any problem. And similarly, you acquire a practice. There's all kinds of consolidations happening with mergers and acquisitions where you'll see hospital chain A and hospital chain B have merged, or we've signed a partnership with that clinic where we will exclusively provide the inpatient services for that clinic. So you can imagine that balance between inpatient and outpatient is constantly changing, and that creates problems, and essentially people have to figure out how they're actually going to deliver the care that that patient might need or that a population might need. And then as many of you guys are aware, there are deep cuts to Medicaid and Medicare coming, which are likely going to lead to rural hospital closures. And so I think either those hospitals will get bailed out by larger chains, or there will be some kind of shift that will happen. But you will no doubt see kind of impacts on operations in states that are not rural as a result of rural hospital closures. We see that even in regions where there's a hospital that's struggling an hour away, we feel that. There's a ransomware attack at a hospital, down the street, we feel that. So there's a kind of a ecosystem of healthcare in any country, state, region where you can kind of feel that at a macro level. At a micro level, health system feels like a generous term. We have a lot of individual patchwork services that are glued together that kind of individually all work well, but don't always work together well. If you look at least every system I've been in, every service is nearly at capacity. It's like you look at the hospital census dashboard, and it's almost always close to or above 100%. So I remember when I was at Michigan, seeing 103%. I'm like, wait, how is that possible? That's when they're counting how many people showed up at a football game, and I'm like, wait, they only have this many seats. How is the attendance larger than the number of seats? And it's because of this very soft, flexible capacity that health systems have that they kind of, in some cases, acquired during COVID, or in some cases had it before, where they can get a bolus of patients, and their hallway beds, they figure out ways to care for people in ways that wasn't possible. And so one of the places this is most acute is in this concept of boarding. So a boarding patient is someone who is in the hospital, admitted to the hospital, but physically stuck in the ER because there is no bed upstairs, it might not be on the upstairs, but often upstairs, that can actually take them. So just show of hands, has anyone, who's familiar with the concept of boarding? Okay, a lot of people aren't. Some people are. And I point it out because every health system capacity issue comes down to either I can't see my primary doc, or there are too many boarding patients. And this is an area where optimization, I think, is really like needed. And question is it fixable? So, is boarding fixable? What I'm showing you here is data from 24 US hospitals that we published during the first week of COVID and onwards, an index to when their first COVID case was at those 24 hospitals. And this was looking at sepsis alerting patterns. So that was each of these lines here represents the proportion of patients that would have generated a sepsis alert at each of those hospitals. And you can see how after the pandemic started, like the alert rates went way up, at least in theory. Not all of these resulted in actual alert. This was based on the scores, and we know what the alerting thresholds generally are. But point being, that was kind of the main finding. However, if you look in the background, you'll see that little gray area shaded in. That was actually the number of number of hospitalized patients. And you might expect that when COVID hit, the number of hospitalized patients went up, but actually it was completely the reverse. And this is why there was all these COVID conspiracy theories forming that like hospitals are empty, or, I can't believe, doctors are complaining. And what was happening is that the reason they were empty was because all the elective surgeries got canceled. And not every bed in the hospital is allocated to someone coming from the ER. There are people who come directly from surgery and get hospitalized. And so all those had gotten canceled to create room for if we were off by one day and COVID rates were doubling in the hospital, you're off by one day, that was the difference between you can take care of someone and you are opening a field hospital. And so the margin of error was so slim that this is what many hospitals did. And so we saw that here. And you can see that this went way down. And I can guarantee to you this fixed boarding. But it also, economically, was not feasible. When hospitals closed their elective surgeries, they were losing millions of dollars a day. There were layoffs. And so, essentially, it required operational changes to fix boarding. And in many cases, a lot of those patients, I say elective, but elective doesn't mean, like, for fun. Elective means, like, okay, you're not like bleeding out right now, so you can wait and we can do your surgery, but some of the elective surgeries were people who have cancer. And so it's not, elective here is a very generous term applied here. So many of those people still needed surgery, they couldn't all get out of surgery, and OR admissions make up a large part of inpatient admissions. So it is fixable, but it requires operational change. And so if you look at each phase of the health system, there are things that a health system can do based on where people are to actually improve healthcare operations. Okay, so that was a lot just background. Let's dig into actual, like, what does this look like in a real health system with real data? So this is kind of now where I'm editorializing, and this is kind of my view on health operations. There's a lot of AI stuff that every health system is doing, so I'm largely gonna not talk about that stuff, because that's stuff that like is just happening and there's no point in talking about it, at least not here. So right now, most systems can't play back what happened in like any kind of real capacity. And one of the ways that you can play back what happened is kind of by hijacking the discrete event simulation system and actually feeding in the actual patients you saw and modeling how they progress throughout your system. So this is a 6-month period, I think it's 6, 7 month, at 3 of our hospitals in the UC San Diego system. And this is actually the time that people spent in days in the ER under the care of an ER physician. This is not patients who are boarding. They're still under the care of an ER physician. Actually, in some cases, it does include boarding. They're not on the floor yet. And this is the simulation time in days, populated with the actual, I call it a simulation, but this is actual patients we saw. This is accounting for, I think, 66,000 patients on this slide right here. This is the same thing, but for our inpatient services. So what can you see? If you go back, you'll see that the longest someone ever stays in the ER is like 4 days, which is a lot, but it's like an outlier. And the longer that someone stays in the hospital is like 150 days. And that's actually not even true, because I know people that stayed much, much, much longer than that. But that's just, I think, for illustration purposes, I think I may have cut it off there. But you get the point that, that's kind of the most resource that a person would use is that much time on the inpatient side. This is just patients arriving through. And the reason it ramps up is just because we start the simulation with people who are currently in the hospital starting there, and so many of them just get discharged. And so there's a little ramp up period before that simulation is reliable. Now if you look at resource usage, here's what the ER looks like. In a given day, an ER might be caring for 70 patients, and that same day, they might be caring for 5 patients. That's why you see this like crazy spikiness up and down. And that's because like by midnight, things are clearing out, and then, morning hits, and then suddenly it's going crazy, or in some cases, there are other periods of time. But you can see that emergency care volume is pretty unpredictable. And that's why any forecasting stuff we do, any intervention stuff we do is kind of ebb and flow of what's happening in the area really affects it, affects the care that you give. Inpatient care volume is also pretty unpredictable. And here what you'll see, I think, is you see the week-to-week kind of trends, because there's people get discharged closer to the weekend, they're home for the weekend, we're a little bit lighter on the weekend, and then things build right back up on Monday. But you'll see that there are periods where we actually were quite light and periods where we were actually quite heavy. And like with a delta of like, 50 or 100 beds. So it's one of those things where when things are busy, it really feels like there's no way out. Because you have people, when inpatient is busy, the ER is busy. When the ER is busy, urgent care and clinics are busy because they know that people can't wait. And so there's all kinds of stuff that we can do to try to fix this kind of one piece at a time. So where would you even intervene? This is a process flow diagram that one of my colleagues, Dr. Alan Muzem and Dr. Rob Alcare put together. This is all the steps that like a patient might follow to get from where they arrive in the ER to where they go to a hospital bed and get discharged. So there's a lot of things that you could actually intervene. But one of the things that's not shown here is that set of patients who arrive not from the ER, but actually from the OR, from surgery. So one thing we have been looking at is if we look at patients who are getting surgery, is there something where we could change the day they get surgery to try to improve the balance that we have over the course of a week? So like, here's just an example. Like over the course of the week, we're really busy on Thursday, and then we kind of drop out. This is combining our 3 hospitals. At least at our main academic hospital, there's a pretty big ebb and flow. Some of the other ones are more flat, and so we've been trying to figure out how do we fix the ebb and flow at that hospital, and one of the ideas is to move some surgeries around. So if you look at operating room admissions, it's one factor driving the variability. It's probably not the major factor, it's probably not the only factor, but you can see how this is what day of the week they arrive for their elective surgery. And what you'll notice here is that very few people arrive on Friday, Saturday, and people arrive on Sunday. Of the people who arrive on these different days, which day do you think is going to have the longest length of stay? So think about that for a moment. I'm not going to do a poll, but just we'll show it and we'll talk through why. But just think through like fewer people coming on the weekend, but who is going to stay the longest on average based on which day they came in? So the thing here is that simulation is useful, but in most of the situations that I'm being asked to look at, or I'm looking at, to see if we can change things, we don't just want to simulate the current system. We want to be able to simulate an intervention. Like what would happen if we did, move patients through a different path. And usually there are resource constraints. So I can't actually just say, take everyone who met this criteria and do that with them, because that everyone might be too big of a bucket. And so if we can't intervene on everyone, who should get the intervention? And this is where actually I think the next kind of building block comes in for health system operations is combining simulation with prediction. So what you can do is you can model patient-level risk of outcomes. And the idea is that in your simulation, as you would in real life, you try to hotspot. You take the patients who are highest risk of that outcome, and you move them. And so if you're worried about people staying the longest, you take the people with the longest predicted length of stay, and you actually move them and juggle them around, because the people with a predicted short length of stay, if your model is accurate for prediction, moving them around is not going to change much. And so you have kind of a way to balance things in your favor if you have a good prediction model and if you can do some back of the envelope math. So here's the back of the envelope math. This is our surgical admissions. The longest length of stay actually is people who come in Saturday, which I think is because we don't usually operate on Saturday. I mean, we do electively, but not like a scheduled case. So either these are people who are not truly elective, or they're people who need a bunch of stuff done because they're gonna get surgery later in the week. So like imagine heart transplant, or like we're gonna bring you on the weekend so we can do a whole slew of tests on you in preparation for surgery later in the week. And we know that we have availability of beds on Saturday, so we might bring you in on Saturday. However, you can see there's not that many of them. So then you can multiply, right, your number of admissions with the predictive days on average they spend, and you can get predicted bed days. So you can see that Monday and like Wednesday are the largest contributors to bed days. People who arrive on those days eat up the most amount of bed days in the hospital. So a simple question would be, can we change that? And what would happen if we try to simulate and change that? So you start with simulation plus prediction, right? Simulate the hospital as it is now, predict prediction risk for longer length of stays, and then you simulate the intervention. And the intervention I'm gonna show you an example of. This is really basic for folks who do like differential equation-based optimization problems and continuous and physics and all the SciML crowd. But this is like stuff that like hospitals don't even do, and it's basic like back of the envelope math. So we take 20% of the highest risk people on Monday and just move them to Friday. Why? Well, if they're gonna stay over the weekend, if they're gonna stay at least 2 days, that eats up days on the weekend and frees up days on the weekday. Like it's just simple math. And so if you were to do that, the intervention is, I'm taking the 20% highest risk patients on Monday, moving them to Friday. This is not what's gonna happen. This is just simply what is the intervention. Like we could try it out. Now to know if it works, you need to play back the simulation model, except now you bring them in on other days. And you assume that they're gonna stay the same number of days. You kind of make some assumptions, and certainly, you wanted to go true discrete event simulation, you can add all kind of cues and stuff and make it fancy. But this is like the back of the envelope discrete event simulation where we're bringing in our actual patients. And so here, we freed up 2 to 3 beds a couple days a week. And we added those beds essentially to the weekend. So you can see Monday got lighter, Tuesday got lighter, Wednesday got lighter, Thursday got lighter, Friday got busier, Saturday got a little busier, Sunday got busier. And we did this for just 20% of patients getting elective surgery, but you could do 40%, 50%, heck, you could do all of them. And you start to get the idea that like, now suddenly the equation changes. And the reason I don't like discrete event simulation, like the typical way we do it in this kind of a format, is because those 2 beds that are freed up, that might get other people through the system faster, or someone might schedule 2 more surgeries now and say, oh, we've got 2 beds now, let's schedule 2 more. And so I kind of think implementing queues and stuff with discrete event simulation in a hospital setting where there's such squishy capacity is like not, you can kind of naively assume, oh, suddenly people are gonna get out of the hospital half a day faster, not realizing that, oh, actually we're just doing more surgeries and we didn't solve the problem, we actually created a bigger problem, which is now we're doing even more surgeries and we have all the same problems we had before. So, patient level interventions can only take us so far. What I showed you is something where you would make a decision at the patient level, but one of the things that brought me to UC San Diego was an investment that Jacob's family had made in establishing a mission control. Many hospitals have this, like a command center, so this is not, this as a concept is not unique, but what is unique is that this is something that is really closely partnering our healthcare operations with our analytics and IT and AI teams, which means that we have a dedicated workforce co-located in one place who's actually empowered to change the time of someone's test. So, oh, your MRI's at 3 p.m.? Well, if you're gonna go home today, we can move it up and we will trade and trade and trade, with the idea being that if we can get you out of the hospital faster, we can fill that bed faster from the ER and create a bed in the ER that someone can get seen in. And so it's almost like a F1 pit stop, but in extreme slow motion. If we can kind of get you out and reduce that turnover time, that will create one more slot as capacity, and that adds up over time if you can just keep doing that over not 500 laps, but over 500 patients. So one of the things that we built around the time that I was joining UC San Diego was a forecasting model for how many patients we're going to have boarding in the hospital. And we actually give up to 10-day forecasts that go out to every leader in the system every single day, every morning. It's a model that's freshly trained every morning. So it's a live trained econometrics model. I worked with Dr. Lily Porceltan, who has a PhD and is doing a second PhD with me. And so, we had tried econometrics models. We tried Google's time series foundation model with and without external regressors or covariates. And where we are today is a model that's substantially better in terms of error than where we were when we started. And certainly better than what we had that was built into the electronic health record. So these are things where the model is cool. The cooler thing is that we have an operational workflow where if the model says we're going to have this many or more patients boarding tomorrow or in the next 4 days, we have a set of escalations and a set of things that take place within our health system. So that I think is the cool thing is you can't be a data science team without the, in our case, chief medical officer literally driving what's going to happen if the forecasting says it's going to rain. We're actually going to bring the umbrellas out. So this was cool. I spent a bunch of months working on that. We tried all kinds of different solutions. But one of the scaling issues is that what is 90% of the workflow in building a prediction model? It's not the modeling, right? It's actually getting the data, at least in the health system side. It is getting and cleaning the data is literally 90% of the work. And then the last bit is getting the right architecture and figuring out what you can do with it. And what I realized is that a lot of the reason we spend so much time getting the data is because the data is sitting in 8 different databases in all kinds of structured fields that have to be joined with missing values dealt with and all the kind of usual data science stuff that led me to develop Tiger.jl in Julia. But at NYU, they had published this paper on a model called NYU-tron, which kind of started to change the paradigm on how this works. And really, they looked at LLMs and said, we can use LLMs as predictive AI. So what you don't want to do is ask the LLM to generate a prediction. Vanderbilt tried that. I think it's dumb. It doesn't work. And every time you ask it, it will tell you something slightly different, which is good and bad, but is mostly bad in this case. But what you can do is you can take embeddings off of a large language model that runs on, let's say, someone's clinical notes, and essentially use that to train a prediction model. And what they did in NYU-tron was actually they trained a large language model from scratch on clinical documentation data at NYU, and then they supervised fine-tuned it for a whole bunch of different outcomes. And they compared that against something that was done bespoke, where the bespoke thing probably took a lot more time, although to be fair, because they were building and supervised training an LLM from scratch, they probably spent more money. But in the end, what they found is that the unstructured notes one, they can be used to train language models, but 2, you can fine-tune it, and 3, you actually get an AUC improvement. You get a performance improvement when you use these note-driven predictions than if you try to use the usual structured predictions. So when I came to UC San Diego, a lot of my thinking was, that's great, that's awesome for NYU that they have the money to do that. I don't have the budget to do that, but I still want to do this. So we came up with a concept of note casting. Note casting is basically a multi-step process where you take a clinical note, run it through an LLM that has a long enough context window to summarize one note or a series of notes or the entire chart. Then you run a filter across it for anything you don't want the model to consider. That's where you handle bias. So you don't want the model to consider someone's race. Great, you run a second step that says remove any mention of that thing that you don't want it to look at. Third, you run an embedding model, and we do this in AWS, where we run a model that generates embeddings. And then all we do is, once we have that, we build a prediction model on top of that with just a 2-layer neural network that can predict as many outcomes as we want in one model or separate models for separate outcomes. We're kind of still ironing out how that will play out in the real world. But the idea here is that if someone says, I have this outcome, and I want to look at the last 3 days worth of data, an hour later we should have a prediction model for that. It shouldn't be like a 6-month process. It should just be, what things do you not want the model to consider? Great, it's done. And this matches up with clinical experience where when people are validating the model, they don't just look at the numbers, they look back in the chart and they read the text to see like, was the model cheating? Was there some like leakage? This solves like 80% of that problem, if not 90%. And so this is our note casting kind of framework. And what I say is this is inverting the thinking on predictive AI. So rather than the old way of thinking, which is you have all structured variables and you convert unstructured data into structured data and bring it into the usual thing, this says, no, 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 no. We use unstructured data exclusively to predict, and if you want to consider structured data, insert that as context into the unstructured data and just completely reverse the way that we approach most prediction, which makes it scalable. And so what I care about is, can I do this at scale at a health system across dozens of outcomes? And my kind of stated goal for notecasting is predict every outcome for every patient every day. So it should not be a thing where we have a patchwork of different models. We have one framework, and we can do that to do a lot of different things. And it's really just one set of calls to get those notes, and then one set of embeddings, and then everything else is separate for different outcomes. So does this work? This is preliminary unpublished data, but so far it looks like, based on the current model we have in the electronic health record, we can do substantially better with just notes and basically zero mental effort. Again, you have to look at bias. You're not immune to all those issues, but essentially you've got this thing working. So you're doing simulation post-prediction. Do the resource constraints affect predictive AI evaluation? So think of it the other way around. Let's say I have a model that is a perfect performance. If I have resource constraints, does my model actually have perfect performance? And if you think about it hard enough, you'll arrive very quickly at the answer that no, it does not. So in other words, if you have only 3 open ICU beds, and your model says 10 patients need to go to the ICU, your realized performance is worse than what you think it is on paper. And so if you know the resource constraint, you actually can model this and say that the resource constraint not only affects the simulation, it also affects how you can evaluate the underlying prediction model. And we actually ended up writing a package in R called Model Recon for modeling with resource constraints that helps you actually calculate resource-constrained performance measures when you can apply absolute and relative constraints in like a real-world setting where you have a rough sense of, on any given day, how much openings do you have? And so whatever the model says, you only use the top X openings unless they have a higher threshold that you apply for a relative constraint. Okay, so I'm gonna, I think, make one comment on measurement, and then I'll go to kind of my final slide or two. So I think the other really low-hanging fruit is that we suck at measuring things in healthcare, and we spend millions of dollars on it. And people, when they try to measure things, they try to make the measures really simple. They try to measure it on very few people so that they can get it right, or they measure it really infrequently so that by the time the measurement becomes available, it's irrelevant. All of these things are not great. And so a lot of the other work that we're doing with operations is actually automating measurement with LLMs. So this is a paper where we showed that we can get over 90% plus accuracy in extracting sepsis quality measures, which are currently done manually at most health systems using an LLM-based approach. And interestingly, when the language model is wrong, nearly half the time, it was actually the human abstractor that was wrong. So when you go back and look, you can find what the LLM found that the human missed. So this kind of really just changes the thinking around how you do measurement. And so in response to that, we've shown a similar thing for patient safety, and we've shown that we may be able to actually do a root cause analysis and present a corrective plan back to someone before they ever even look at a thing. So they're not reviewing the incident, they're reviewing the incident and the potentially corrective action that they need to take. That's all kind of through LLM-based chart review. But we think this is such a basic thing that we've built a framework internally that we call Note Reader, which is a framework for note-based question answering where it's all Llama 4 Scout driven with 10 million token context window. So we can basically send the whole chart into a thing with a set of dates. We have a batch mode where we can run it on thousands of patients. We have a single patient viewer mode. We have a mode where you can a human can actually do a human in the loop thing where they make sure the LLM is actually correct and can fine tune their prompts. We can export it as a prompt library. So this is some of the things that we're working on. So let me just close out by saying in addition to all the cool things that we're doing, we do think AI governance is important. I oversee AI governance along with two of my colleagues at UC San Diego Health. We have this is our governance process. We have a AI think shop and a health AI committee that manages AI intake and manages how we handle AI. And areas, I think, this is my summary slide of where AI can support operations: simulation, prediction, intervention, measurement, automation. I didn't touch on automation because I think a lot of people are thinking about it and there's a lot of vendors that are doing that space. But what's required to get there is having really clear operational goals. So that's a key thing. IT cannot come up with that. That's got to be operations. Operations and IT have to trust each other, and literally, it's not IT driving the show. It is operations holding IT accountable to get something done where IT thinks we can do it if we stretch. You need data science expertise. You need data science infrastructure. You need workforce training. So we're doing a bunch of workforce training on AI agents and things that individual people can do to optimize their own workflows, not necessarily system level things. They need AI governance. And so throughout my work, I would say one of my messages is that hospitals are overwhelmed. There's so much AI slop going around that really every day I get 8 messages from vendors doing either really cool things or not really cool things, but I can't tell. Because from the initial thing, unless I am familiar with what they're doing already, you're going to be vetting a lot to figure out, is there a there for a lot of the stuff happening in AI? And so ultimately, I think we have to figure out what's working, do the back of the envelope math, figure out if you could get a perfect prediction, what could you actually do, then try to do it and get partnership with operations. And so my last slide, what is the implications for code and tooling? And this is my little mini soapbox. In general, any package I deal with, I want a higher level of abstraction also available. I want to play at the low level of abstraction, and as quickly as possible, once I grasp it, I want the higher level of abstraction. And I think many languages give you the low level of abstraction, but not the next level up. And in Julia, this is often macros. And so I would just say, macros is a really critical part of the Julia infrastructure to do higher level analysis. And I think it's super, super helpful and super critical for stuff that I do, either in Julia or in other languages where I use metaprogramming. I want deferred evaluation. I almost never want to eagerly evaluate something. I want to describe the system, have that description be an object, and then I want to execute it. R does a great job with the recipes package and the tidy models ecosystem where everything is deferred, and at the very end you hit run, and then it all runs. And so I think that's a thing I love. And then I want pipeable syntax. I think chain.jl is criminally underused, and I think that has to do with the coding style of many folks who I think code. So there's a whole set of folks who are happy in R, who I think look at Julia periodically, and it's the pipeable operations that really make sense from a data science mind. Very different than maybe computational modeling and other parts of the ecosystem. So just keep that in mind, that higher level abstractions for end users like me who are not mathematicians but are trying to use this to drive operations is really helpful. Stay tuned. There's a couple of tidier.jl talks happening tomorrow and Friday. Thank you for having me. Appreciate it.
We have time for one quick question for the speaker.
First of all, very quickly, I'm just curious what the inputs were to the econometric time series forecast model of patient volume. And then also I'm wondering how your experiences in healthcare AI imply these suggestions about pipeable syntax and deferred evaluation.
Yeah, so 2 separate questions. First one I would say is, I did not use a typical discrete event simulation. A typical one would be where you use Kendall notation, and it's MM1, where you have a defined number of servers, you have a queue and a wait time. What I did here was actually added individual patients into the model based on their observed characteristics. And so that's why I put simulation in quotes there. And the idea would be if you're trying to optimize a process, you would replace that with a set of queues and a wait time for that process, leaving the rest of the system intact. Because I think that there's too much squishy capacity in healthcare to actually try to simulate the whole system all at once and trust the result of simulation. The second question is not so much my health experience, it's mostly being a data scientist and a data educator. I just personally find pipeable, like I think there are people who don't and there are people who love it. And in R, there are data table users and there are tidyverse users. And oftentimes that determines what type of user you are. And I would say for the tidyverse users, which I've used both, I can comfortably use either one today, but I think much more in pipeable syntax. And that's why I love things like prequel, which is essentially pipeable SQL. And so like those are the things that I view as innovative. So I think those syntax where you're defining a recipe and then you're executing the recipe is my just preferred style of working with code for data science.
With that, let's thank the speaker again. So there are a few tidier talks that are happening at the conference tomorrow and day after. Please look out for these for the times here. We will continue with the rest of the conference program until 5 p.m., both in this room as well as the rooms that you've been to earlier today. Thank you, everyone. And thank you.
Thanks.
Oh, yeah, if you want to jump ahead. I think I'm at 3, but are we running behind or? Oh, okay. Oh, hold on, yeah. Oh, boy. Yeah. Perfect. Oh, okay. All right. Oh, Josh.
Tim is going to chair this session, so he will introduce you.
Oh, okay. Let me just make sure. Oh, gosh. Okay. All right. Plan B. Better?
That's immensely better.
I don't know, projectors don't like dark. I think we're.
Yes, we should get started.
The, oh, here or? I'm afraid this might be as big as it gets. Oh, a little better. A little better. All right.
Ready? Okay. All right, I'd like to kick the session off. So welcome to the second half of the tooling developer tools section. So our first speaker in this session is Josh Blanco, and he's talking about Julia's secret superpower, which if I remember correctly is REPL and lessons from other languages. So.
Yes. Yes, thank you. And thank you all for coming to the talk. So yeah, today I want to talk about what I believe is Julia's superpower, the REPL. And in particular, I am hoping to share with you things that I've learned along the way working with other languages that have slightly inferior REPLs. But I wanted to start off, actually, with one of my favorite quotes about programming from the venerable SICP. Programs must be written for people to read and only incidentally for machines to execute. Now, the reason I like this quote is because the first time I encountered it, I thought it was garbage, right? Why am I worrying about other people reading my code? If I wanted to talk to people, I'd write in English or whatever language they happen to speak. I'm writing code because I want to make a computer do something, all right? But over the years, as I got older and hopefully wiser, I came to appreciate the wisdom of that statement because human languages are imprecise, and computers don't speak human languages. I know we'll get there, but so if you want to program a computer and do so in a way that other people can understand what you're doing, you need to make sure that the code that you write is readable by humans. And the computers don't really care, right? Because a computer is perfectly happy reading this. I would venture to guess most of you are not as happy if you were having to read this, and not so many people are programming in assembly anymore. I think we would prefer to read this, which is the exact equivalent to what was shown before. And the reason I wanted to start with this little sort of diatribe about Abelman and Sussman's quote is because the conclusion I draw from this is that programming is a creative act. Much like composing music or painting a painting, it's creation. And much like those, creation thrives on iteration. So I want you to imagine for a moment if the writers of your favorite television show, when they came up with a new joke, had to write out the script, give it to the actors, have them practice their lines, record it, edit it, and show it to a live studio audience, only to find out that they didn't laugh, go back, and try another joke. Not exactly practical. And yet, most of us are doing that exact thing every time we program, right? We sit down, we write something, no idea if it's gonna work, compile, it compiled, great. Is it gonna run? Right? It really takes you out of the creative flow when you have to break up your iteration process. Even if your compiler is fast, your runtime is fast, it's still an interruption. Luckily, we do have a tool available that is much faster, and that is the REPL. So, as I'm sure most of you are probably aware, REPL is the read, eval, print loop. The name comes from the 3 functions in the original Lisp implementation that were chained together in order to achieve a REPL. And just so you're aware, I'm not going to be going into sort of the Julia REPL 101, though you should be aware of it. If you haven't played around with the Julia REPL, it's a wonderful REPL. It obviously can evaluate code, but you also have these additional tools like typing semicolon to get into a full shell, right? Using the square bracket to manage your packages, create packages, right? And the question mark to get help not only on the core utilities, but on any package you might have included, right? Which is really useful. So I want to challenge you now, though. So what is a REPL? Well, this is probably what most of you are thinking, and you'd be right. What about this? So if I can convince you of one thing today, I'd like to convince you that your text editor is a REPL. Why? Well, because in that original definition, there was no qualifier that you have to read from a terminal or that you have to print out to a terminal. Anywhere you can read from, you can evaluate in the process and print back out to, that's a REPL. Okay, does it have to be Emacs? Well, after almost a decade of being a Vi hacker, I came around and have been using Emacs since. Other editors will work. The qualifiers I would give you is that you should make sure that whatever editor you're using has a tool set that's able to send content from your text buffer to the REPL process, that can take the results of evaluating back from that REPL process into a buffer. And the last one is kind of a bonus. I find it useful occasionally to be able to actually take some code, evaluate it, and replace that code in your buffer with the results of the evaluation. For example, this is really good to expand macros in place, debug them, find out why they're not working, and go back. Okay, before we get into the exciting part of the talk, just wanted to give you a rundown of some of the tools that I'm going to be showing you. So first of all, if you are using Emacs, you definitely should be using Julia Snail. It is a wonderful library. I cannot sing its praises enough. I happen to have whipped up a quick fork because it has the basic send to REPL and display, but not the dump into buffer, and I just wanted to play with those today. So you can find my fork there, and I'll be contributing it upstream. I happen to use Doom Emacs for configuration, to each their own. If you haven't used Emacs and you want to get into it, it's a very nice, gentle introduction. I also put together a library that we'll see in a moment that I call Elegant REPL that has the secret sauce. And finally, unfortunately, we don't have so much time that I can get into all the nitty-gritty details, but I do want to point out that if you are using Emacs and you start it in server mode, set your Julia editor to Emacs client. Doing this allows you to actually use the edit macro, for example, and have whatever you want to edit open right there in the same editor that you're already in. It's really a wonderful workflow. Okay, so the second, or the secret superpower, and this is the second thing I'm trying to convince you of. It's something that after being a Ruby and Python hacker for many, many years, I finally got a chance to work alongside some real Clojure heavyweights. And I saw the way that they worked, and it really opened my eyes. And this is really the reason I wanted to come here and give the talk and share it with you. So here it is. You can laugh. It's nothing, right? But that's the point. So what does a macro like this do? Right? We already have line comments. We already have block comments. Why would you have a macro comment? Well, it turns out when you put code inside of a macro comment,
it must still be valid Julia syntax. And because your editor doesn't know that the macro is just eliding the code, it's still going to treat it as Julia code. It's going to highlight it, it's going to format it. But because you basically can operate without consequences, you can do whatever you want within the comment block, send it to the REPL doesn't know it's in a comment block, right? So if you just send a couple of lines from a comment block, it doesn't know that it should ignore it. It will evaluate whatever you send. And again, because it doesn't exist in the compiled code, you're free to pipe whatever you want. It's a sandbox to play in. Okay, so how do we use this power? Well, the ways that I've seen it used are, it's very good for inline documentation, right? So how many of you have ever read through some code and you see embedded there in the doc string of function a markdown block with Julia and a bunch of code, right, that you can't run because it's in the middle of a string, right? And it's not highlighted and it's not necessarily formatted. You have to copy it out, do something with it. Instead, you can put a comment block above your function with some examples that you'd like people to run. A very common use case that I've seen when I was doing a lot of closure is when you have database connections or servers that need to be initialized, right? A lot of times you don't want to have to go through that process every single time just to get to the function that you're trying to operate with. So you can put that initialization code in a comment block so that when you're in the file that you're working in, you can just really quickly evaluate that code, boom, you're ready to go, and you can be off to the races. It's helpful for debugging suggestions, right? So, you know, you can put something in a comment block and say, just eval this code and see what the results are, right? You can use it for inline scripts, right? So I've seen source files where it's a bunch of functions and then a comment block with, you know, these are the orders to call the functions in. But most importantly, it's good for exploration. Okay, so assuming we've done the appropriate sacrifices to the demo gods, let's try and code. Okay, so first thing I'm going to do is I'm going to start up my Julia snail process. And then the next thing I'm going to do is make sure that the project is activated. Okay, so what I've done is I've taken some sample code from documentation from some popular libraries. And I wanted to see what it would look like to use this tool and sort of the editor as the REPL to work with these. So this is from plots. And the only thing that I did is I imagined, instead of just being a series of lines of code, that it's some sort of function that I'm creating where I'm setting up a bunch of plots, right? And I want to make sure that the plots that I'm creating have been set up correctly. Now, you can't ship this code, right? Why not? Well, I'm going to evaluate the buffer, and you can probably predict what's going to happen. There's the plot. Now imagine you put this in the library. Every time somebody tries to run your code, or even include your code, they're going to get a random plot showing up. That's not good. But it is kind of useful to have that, right, to make sure that I'm on the right track. So here's what we would do instead. Take this up here. Evaluate that line, so we got the library in place. There's our example. Okay. So now, you can see we can, again, I'm going to, one more time, evaluate the entire buffer. No plot, right? We're safe. But if we want to see that we are actually doing the right thing, we just come up here, evaluate that line, there's our plot again. Okay, so pretty simple, but it gets better from there. Okay, so here's a slightly longer example that I took from the HTTP library. And this is an example that's trying to give an idea of how you might write authentication middlewares for a server, right? Now, I'm not going to evaluate this buffer because if I do, I'm going to get into trouble. I'm going to have to restart the REPL. It's going to be a problem. But we can already look and see why that's the case, because we have here some function called parseAuth that doesn't exist. And we have some function here called getUserData, which doesn't exist. And the last line here is a blocking call to start the HTTP server, right? So not good. We can't just evaluate this. But what we can do is we can set up a comment block. So first thing, let's copy this here. Okay, and now we're going to start playing, right? So this is where the creative iteration begins. So first of all, I know that I don't want to do the blocking serve. I want to do this. Could have looked up the documentation, but we'll save some time. And I'm just going to assign it to something. Oh, I forgot to evaluate the buffer, which I can now do safely because everything that's not defined is hidden in this comment block. Oh, or not, because we'll try this again. Okay. All right, so now I can evaluate this line. All right. Got to start that again. Okay. All right, so evaluate the buffer. And now evaluate the line. So now we have a server, okay? And to prove that we have a server, I'm just going to evaluate this variable. But this time, I'm going to use a slightly different way to evaluate it. I'm going to have it dump the contents into the buffer. So there we go, right? And now I'm free to inspect this, do whatever I want, look at whatever I need. I also know now that I can, say stop, evaluate that line. Oop. I think it's HTTP. Close, thank you. Right, so there we go, right? And I can, again, start it back up again. Right, so this is how we can, imagine this is a much more complicated server initialization. We can put this in a comment block, have it there, ready for us to use. Okay, but now I'd like to make a request. Okay, so I know there's a thing, HTTP request, but what am I going to do? Well, luckily, Snail has the ability to pull the documentation right up here, which is really nice. So I'm just going to skip ahead, and I know that I need to make a post request. So let's go ahead and do that. To the server I just started. And for the time being, we're going to send some empty headers and an empty body. Okay. So now I can dismiss the documentation window, and let's evaluate that line and see what happens. Boom. Everything blows up, right? Of course it does. We are referencing two functions that haven't been defined yet, right? Okay, but that's okay. Now we can see what they should be, right? So first thing here is we need a parseAuth. Okay, so that's the first thing that showed up in that stack trace. I don't have a parseAuth. Maybe eventually I'm going to pull in parseAuth from another library, but I don't want to do that right now. I just want to see what I need. And it's getting a request. What should I do with the request? Don't know. Let's just show it for now. Okay? So now I can evaluate that region. I have a parseAuth function now. It's in scope because I'm in the module scope for this. So now I can evaluate this line. I'm still going to get a 500, but now if I come down to my REPL buffer, I can see, the request, right? This is the thing being passed in. So I should do something with it. Okay. I'm going to skip a few steps ahead, and I'm going to say, I know that what I want to do is I want to say if the request headers authorization is set to, actually I'm going to do this. Okay, now, first thing. You notice, even though this code is not appearing in the final product, it's still being parsed by my editor. So it caught my typo, right? Can't do that in a string. Okay, so now I can evaluate that, and that's going to update that function. So now I can, again, come back to this line, right? And notice I keep coming back to that line. It's very handy to have there to just go up, eval. This is that quick iteration process, right? Okay, so now what's the issue? Okay, so now we're getting this method about, oh, right, of course. Invalid index authorization of type string, right? Oh, okay, geez, I would have thought that the headers would contain a thing called authorization. But look, I can do this. I can say, ooh, let's do this here, show request headers, and again, reevaluate, and again, reevaluate, and now look down here. Ah, right. It's a list of pairs. If I want to index by the key, got to turn it into a dictionary. Okay, so first we have to surround this. Okay, so now we have a version of our function. All right, let's try that again. There we go. So parse auth, and again, evaluate the line, and now come down here, and oh, authorization. Oh, right, of course, authorization's not found because, why? Because I didn't set it. Now I can evaluate that. And now I'm getting a different method, or a different message, right? Now we've gotten past the parse auth. Now we say get user data is not defined. Okay, so that's the next one. Well, let's do that. Okay, so again, I'm not sure what ident is, so let's just show it initially. This way I can get a feel for what it is I need to do. Come back up here. Okay, so ident says Josh is authorized. Okay, so let's see, what can I do? I can say if ident, oh, again, catch the typo. So again, I can reevaluate that function. Again, every time it just updates the same function. And now I can come back to the same line I've been using, evaluate the line, and now I've got an okay, right? Now, did I actually get my response? I don't know. Let's assign it, evaluate this, and dump it. Ooh, okay, yeah, it comes back as binary, so let's do this. Nice. Okay. So this is an example of different things that you can do to play around, right? Be creative. I did want to do one last thing, though. So there is one additional hidden superpower in Julia, and that is Julia's types, right? And I think it's something that we haven't really completely taken full advantage of. So one thing that I was doing while preparing this talk was playing around with what would happen if I took the ability to look at the types of everything in a context, in the REPL, all the methods that we could use with that, and give it to a process that might be able to do something with it. And now I'm going to use the version of sending to the REPL where I replace the line. Oop, all right. spoiled the surprise, I forgot. So I figure probably most of you, like me, are giving Anthropic $20 a month. I gave Apple a heck of a lot more money for this thing, and it'd be really nice to use that. So there we go. And it does come back as a string, so that's one thing that I still have to work on. But yeah. So right there on my own machine, I was able to get code generation out of Qwen, using the ability to inspect what's in the REPL. So, okay.
So I've used this thing called Vim Slime or something, which you can send code from your window to a REPL.
Yep.
But with your snail thing, what that enables is the bidirectionality and these things, or?
Yes.
And is it specific for Emacs, or what do you have to? What does an editor has to support to use the?
So Julia Snail is specific to Emacs. So there's a couple of ways that you can do this, right? So depending on your editor and depending on your REPL, you can either do it the hard way and basically parse out the terminal output, right? Always copy to the terminal. Basically, what you would do with a copy-paste, you can automate via the editor. The way that the Clojure folks do it, and Julia Snail does it, is you actually open a port at the same time that it just accepts I/O and runs the eval and responds back to the same port with that I/O. And then Emacs is really amazingly competent at doing I/O and all kinds of crazy things. You can actually do Julia Snail over SSH to a REPL running on another machine. So.
Thanks.
Yep.
Merci.
Would you still do it this way if, let's say, Snail supported org Babel better?
Say again, sorry.
If Snail supported org Babel.
Org Babel.
Better?
Snail does support org Babel. So yeah, I guess I should say there are other ways to do this. Because time was kind of short, I had to remove all the comparison slides. So you've got Jupyter Notebooks, right? But Jupyter Notebooks you can't package up in a library and ship very easily. Org Babel is very good. Usually there's a step where you have to strip out the stuff that's not the code, right? So the idea of doing things this way and with the comment macro is that this is pure code, right? It's not a notebook, it's not a doc, it's not anything. It's just pure code. And at any point in time, right? So if you're preparing a library, you know, you're probably going to take care to package it up and make sure it all looks nice. But if you're trying to ship something to production, you know, before the end of the day, you know, and you don't care that some of these comment blocks get left in there, this is really, really useful.
All right. I think in the interest of time, we should move on. Let's thank our speaker again.
Thank you.
All right. And our next speaker is Frederick Ekray, and he's going to be giving, I forget the exact title of your talk, but a talk on Runic, code formatting with Runic.
Yes.
So take it away.
Okay, thank you. Yeah, so today I just want to present my code formatter, which I call Runic. And it's a code formatter with formatting rules set in stone. So this is a project that I started basically on the flight home from last year's JuliaCon. But now it's, I would say, in a very good place where it's used by quite a lot of packages already, and I would certainly recommend you to try it out. Anyway, so what is Runic? Well, you can find it on this repository link here. The README is actually very comprehensive, so that's really everything you need. But I just want to discuss some of the decisions and things that I've been doing in this repository. So yeah, it's a code format for Julia source code. It's based on the new parser, Julia syntax, which we have heard things about before today. And in particular, Runic doesn't have any configuration. and I will come back to this choice in a bit. It has a unique style CLI interface where you can pipe standard in to standard out and things like that, which makes it very easy to use it together with editors or with CI or together with Git. And it's very fast, and you can actually statically compile it with Julia C. All right, so why would you format your code? So the main thing is, I guess, that you have then a consistency across your code base. And in particular, I think it is very nice if you have a multi-person project, so you don't really mix styles. So I think it can improve readability. In particular, some formatting choices can really make readability better. I find it easier to do code review. So if you are reviewing a pull request, if you have some automated formatting which you also check in CI, you don't need to spend time or comments or review cycles on commenting on the code style. And the fourth point here is something that I've really come to appreciate, is that I find that it reduces the, let's say, cognitive overhead when I write code, because I noticed sometimes that I can't really decide where I should, how I should align things, or how I should format or whatever. So if you have automated formatting, this is something you don't have to think about. It just happens. So the other main thing with Runic is that it doesn't have any configuration. And this is by choice, and a very deliberate choice. And this is inspired by GoFont, which is the Go source code formatter, which basically all Go code uses. And there is a quote about GoFont which I like and which I intend to apply on Runic as well. And it's that GoFont's style is no one's favorite, but GoFont itself is everyone's favorite. So the output of GoFont or the output of Runic may not be exactly how you like your code to look like, and it's not, in some cases, it's not even how I personally would format code, but I like that it does format code, let's say. All right, so just quick note on the usage here. So it has, the main interface is really the command line interface. So you can format files in place with just this in place command line file. You can format all of the Julia files in a directory. It has a check mode where it just returns non-zero if there are formatting errors. So this is really the main interface, and on top of this, there are some nice things built. So I mentioned earlier that you can do editor integration. So you can easily hook into various editors, format file commands, or format on save commands. So you can look in the README, there are instructions for VS Code, NeoVim, Helix, and Emacs, I think. Yeah, and there is also a Git integration which was contributed by Tim Bessard. So you can incrementally commit or incrementally format the changes. So Git Runic, the integration basically applies the formatter only on the diff. So you can use this to incrementally Runic format your project. And then you can also use it with the pre-commit hooks, as someone else mentioned during the day here. So for CA integration, as I mentioned, to reduce review cycles spent on formatting, you can set up a GitHub action, which will just error if you have formatting issues. So how would you then adopt Runic? If you're interested to adopt Runic, how would you do it? So the easiest thing is basically to just, let's say, rip the Band-Aid and format everything in a big commit. Or you can do it incrementally with Git Runic, and then as time goes, you have replaced all our lines in your library, and everything will be formatted according to Runic's style. So it's, you can pick what you prefer. Personally, on the libraries that I've used Runic, it's pretty easy to just do it in a big commit and then be done with it. So I'll just briefly mention a bit on how it works. So I mentioned that it uses Julia syntax to parse your source code. And of course, Julia syntax, with Julia syntax, we have a mapping between all of the tokens to the source bytes. So that's pretty nice. And basically, Runic implements a bunch of formatting passes on top of this syntax tree. So if we start with a simple code here, which is just a plus 1.0, if we look at the syntax tree, you can see that you have this similar to the Julia Expr, where we have now a top-level statement here. We have a call between an identifier, and we can also see the white space here, which is, of course, important when you're writing a formatter. And we have the plus operator, another space, and then we have a float literal. So in order to do formatting passes on top of this data structure, basically what Runic is doing is to pattern match. Okay, here we have a call, which is with an operator call, and then I want a white space on either side of the operator. So there's just a bunch of different passes that looks for the pattern and applies the formatting. So just going through some of the rules. So most of the rules or passes I think is not very controversial, and most of you would agree with them. So for example, it removes trailing spaces or semicolons. It uses consistent 4-space indentation. It places spaces around all binary operators, assignment, ternary operators, comparison, and type comparisons. So you can see the diff here, where you see the green stuff is the formatted, and the red stuff is the previous. So there are some notable exceptions to this, because most people don't want spaces around single colons and the power operator and so on. And another thing is that Runic inserts parentheses around operators in colon. So this is tricky because colon has a very low precedence. So it's not obvious what this red expression here at the bottom is doing, but it's much more clear when you put parentheses on it. So this is an example where formatting makes the code more readable, I would say. It uses the letter or the word in instead of the Unicode or the equal in loops. It uses consistent single space in what I call list-like constructs. So for example, method definitions, function calls, and tuples and literal arrays. It applies some floating point normalization or for literals. So in Julia, you can write 1 dot as a shorthand for 1.0 or .1 as a shorthand for 0.1. Runic inserts explicitly return statements. All block constructs are made proper block constructs where there is a new line at around the block. And the final thing I just wanted to mention here is how Runic handles multi-line list-like constructs. So here is an example where we have a long function definition with a bunch of arguments split into multiple lines. So this is how Runic would format this. So basically, after the opening paren, there is a new line with one extra level of indentation. We'll have all of the arguments, and then the closing parenthesis is on a separate line. So this is an example where things just happen automatically, because in Runic, the pass that does indentation, the function keyword increases the level with 1, and the opening parenthesis increases it with another 1. So it's natural that we have here 8 spaces. So common alternatives to this is this, where you don't have the extra indentation. The reason I don't like this is that it kind of looks like this closing parenthesis closes the function, similar to like a closing square bracket in C. And the other case, which is quite common, is this, where you kind of align the arguments like this. The reason I don't like this is that, okay, if you have a long function name, this looks silly. But also, if you change the name of the function, that will require a diff on a completely separate line. So I kind of like how Runic does it, because if you change the function name, nothing else needs to change. And I think this looks nice, that the end token is on its, what's actually looks like it's closing the function. All right, so my time is up, and thank you for listening. Yep.
So by all means, do approach him and talk about it. Our next speaker is Christian Golinsky, and he'll be talking about Docker files for Julia, caching and debugging.
Welcome everyone to my talk. My name is Christian Golinsky. I work at Julia Hub, and I'll be talking about Docker files for Julia, and especially about depot management. So what do we want when we build an image with Julia? So we want no compile at runtime, because we can do it at build time, so why would we do that? We want the smallest possible image size, because we have to attach the depot to runtime, but we don't want any things that might not be used, like some artifacts from a different package. And when we develop the image, we want no minimal recompile when we make some changes, so that we don't waste too much time. I'll be showing examples with the two following mechanisms that really help in achieving that. So with multi-stage builds, we kind of have the ability to branch off and run something in a separate stage, and then copy it over back to the main stage, and then discard that stage, so it doesn't end up in the final image. Another mechanism that I'll be using will be attaching cache to run commands. So for the time being of that single command, a temporary volume will be attached under the target path. And those caches can be reused across many builds. So once you're done with this build, you can reuse it in another one. So I will be keeping the Julia depot there, which is somewhat an uncommon use case. First, how do we get Julia into the image? We can use the official Julia image. Alpine, Debian, Windows variants. We can do the binary download. And as you can see here, I do it in a separate stage. I download the binary, unpack it, and then I copy it over back to the main stage so that I don't keep any of those artifacts in the image. There's also the Julia app version, but that requires more copying of those Julia app directories. But if you need Julia app in the image, this is always available. So I'll be using this package setup. So it's package A, depending on data frames, and package B. And when I will be rebuilding this project, I will be editing package B so that effectively we only need to recompile package B and package A. Data frames is kept in the cache, so we don't need to recompile that. So let's do no precompile at build time. And what you'll see is, obviously, please remember to set the CPU target, because you will probably run the image at some other machine. We copy over the project files, and then we precompile at runtime. And as you can see, the timings are awful. Even though the build time is quick, we pay the precompile price at every runtime. So this is not good to use. Now let's do standard precompile in a run command. As you can see, this is already far better, because we do this build time once, and then at runtime we basically don't do any precompile, so it's just 1 second of runtime. The thing that you might see is that rebuilds take the same amount of time as the first build, because we don't cache anything, so this will compile everything on each build. Now let's do a simple mounted cache. This is a method with 2 steps. So as you can see, this got a bit more complicated, but in the second line here, I'm mounting the depot, I'm mounting the cache under the path that the depot is set in, so root.julia, and I'm precompiling the project. What I need to do later is I need to mount the same volume again under a different path and just copy it over to the designated depot path. So using this method, I save 50 seconds on rebuilds because data frames is already precompiled. I only need to recompile package A and package B, which are maybe lighter, maybe heavier, but we still save some time. Runtime stays the same. What you have to notice here is that the ID needs to match, and those are global IDs, so it's best to have the same ID in a single Docker file, and sharing is private, so no other build at a time will use the same volume in a run command. So you might be thinking, do we have to do 2 steps? We can do 1 step, but I'm warning you, the first idea you might get will not work. As you can see, I'm doing the same thing. I'm mounting the cache under the Julia 2 path. I'm precompiling it to that directory, and then I'm copying it over to the designated depot path, which is root.julia. So this will not work because some packages are not relocatable. You will get issues at runtime. This example worked, but obviously you might hit a package that isn't relocatable. This is another method that tricks Julia into actually working with this method. So I first symlink the cache to the designated depot path. I precompile, then I remove the symlink. I copy over the depot from the cache to the depot location. And this should work. I haven't tested it too much, but this basically tricks Julia to precompile with the paths of the designated depot path, so even packages that are not relocatable should work just fine. So, and as you can see, this saves us a bit of time on rebuild because there's 1 step instead of 2, so it's slightly faster. Now, you may be thinking, like some of my colleagues at work, what if we used 1 single depot for all of our builds? So you can do this with the shared parameter of this cache mount. But the problem is that that depot will have way too many things that you need. So, but you only want the things that you need in your specific project. So I developed this move depot script, which will be in the repo that I link at the end, which cherry picks whatever dependencies that you might need from the big depot and moves them over to a different location so that it's possible to share a big depot and across many builds and then just cherry pick whatever you need to a single image. So as you can see, this is used with the 2-step method, but you can use it as well with the 1-step method. It's just replacing the copy command at the end and doesn't really affect the runtime. It's a simple script with dependency only on package.jl, so that's super quick. Lastly, I wanted to show you that it's even possible to speed up cases where you have package compiler usage. So as you may think, but wait, like package compiler can't be really sped up. It's always, building the same image from scratch, and that's still the case. I'm not really helping with that. But what you can see here is that I start off as usual, then I start another stage in which I will do the sysimage build. I will install G++ because that's needed for the build, but that's needed for not needed for my runtime. So I do it in this stage, which will be discarded later. I copy over the project files from the main stage. So anything before that will still get cached. We will not install G++ again on the rebuild. We will only do it once. And then I do the sysimage build. And please note that the CPU target is mentioned there in the command. This doesn't really get read from the env, so you might get issues when you build a sysimage and you want to, for example, run on a different platform. Then we get back to the main stage and we just copy over the sysimage. We copy over the depot using one of the methods. And as you can see, we save around 80 seconds on the rebuild, which is a lot considering this takes so much time. So that's all from me. You can find all the examples in this repo. And if you have ideas on how to improve the script, I would be very welcome. This is pretty hacky, but it works well for now. So that's all. Thank you.
So again, we'll defer questions for now, but some exciting things to talk about for sure there. So the next of our 10-minute talks here is by Anand Habagam, and on the state of continuous integration in the SciML ecosystem.
It's not showing up.
You have to mirror the display if it's not. We're seeing some changes now.
Okay, let me try mirroring the display.
Yeah, it's sort of a failed state. There.
Is that better?
Yep, at least it's legible. There you go.
Yeah? Okay. All right. Hi, folks. I'm Anant, and this is State of CI in the SciML ecosystem. So with this talk, I kind of want to give folks a broad overview of the processes we use in the SciML ecosystem for CI/CD. This is basically non-negotiable at this point, especially with the size that SciML has grown to. And so the first question is what runs where and where all these run. So most of our CI jobs are run on Linux. There are some packages that run on Mac OS and Windows as well. We primarily use two CI providers, GitHub Actions and BuildKite, and most of these are for different kinds of workflows. So to start off with, let's talk about GitHub Actions, and I think that's probably more relevant for folks in general. So GitHub Actions is used for more general purpose workflows. This is running tests, package tests, format checking, and so on. And these are all typically run on GitHub's hosted runners, so we don't have our own dedicated machines for these, or we don't have dedicated queues for these. They're kind of, they're typically considered to be essentially in any SciML repository at this point. If you import it, if you're importing a new repository into the organization or creating a new one. So this is what you're likely to see more across SciML repos. So how do you get started? The answer is two words. It's using our centralized workflows. And centralized workflows is this new thing that we've been rolling out over the course of the past year. And how does this work? It's super simple. We basically have all our workflows defined in a central location in SciML/.GitHub repository. And all you need is just this one liner in your job definition, and then it'll automatically run it for you. So why exactly did we come up with this? Besides convenience, there were also like active pain points that motivated this. Previously, the CI workflows that we had were basically just copy-pasted from existing repositories without any particular pattern or reason. They were not maintained. They were only tweaked when something broke down or like some very specific niche case came up. And when that gets copied over to a new repository, that tracks as well. There's also the other issue with these kind of copy-pasta workflows, wherein it's not always intentful, so it ends up being more wasteful. So even if you don't need to run Windows CI on your specific repositories, you end up running it anyway, and that just eats up CI time and usage minutes. More importantly, it's very difficult to propagate changes across the ecosystem whenever there are disruptions in the dependency change distribution. The biggest example of this is CodeCurve. When CodeCurve broke, all of SciML went, red like within the span of 1 day, and then we had to put up like over 100 PRs just to fix that, and that's not feasible. I mean, even if you can do it, it's not a pretty task to do. And this was before we had Claude to do these kind of things, right? So what all of this culminates in is a whole bunch of unmaintained and outdated workflows that are kind of inconsistent and painful to update, which is why the solution is centralized workflows, obviously. So why does this work? It's because it's a single source of truth, and we've set it up with sensible defaults, which is a very important thing here. So when we are migrating over to the centralized workflows, we took care to make sure that the status quo is maintained, that each and every repository's workflow needs are all taken into account, and we derive all these kind of patterns and commonalities between these workflows while moving them over. They are extensively configurable as well. So if you want to configure any of these default values, like if you want to turn off your coverage, or if you want to run your Julia tests with a different dep1 flag, right? You could just as well do that. And they have a staged rollout process right now. So how this effectively works is anytime there's a new change that's proposed or new change that we want to introduce, they're first tested in individual branches on isolated repositories. Once they're verified to be working there, they're kind of promoted to master, which might seem counterintuitive, but it's not really so much. There are select repositories like Modeling Toolkit, which are kind of beta testers for this master one. And these are all high volume repositories that see a lot of activity. So if someone breaks, I know someone's going to yell for sure. So once they're verified to be working there as well, and there's no issues, then it's promoted to a release branch of sorts. The release branches kind of ensure that if these workflows ever have a breaking change, like for instance, if you move away from Julia Formatter to using Runic or something, then the onus is not on the package maintainers to update all of their packages at the same time, right? So you can have a measured release process for these things as well. Finally, they're also generally available as examples for other organizations. This allows people to contribute their thoughts on these kind of things as well. For instance, I know that there's a Quantum Kit Hub organization that has adopted these workflows as well. And so what kind of tests do we run with this? We run tests, we run documentations and format checks with suggestions on PRs right now. We have downstream tests in the works. We have downgrade CI that actually works with Stefan's new implementation of the SAT solver coming up. We have minor benchmarking jobs that aren't intensive enough to be in SIML benchmarks there as well. And then we're also planning on looking at dependency management for the reusable actions within the workflows as well. Next one is Buildkite. I'm going to speed through this real quick because I have a few slides and I think I have like 3 minutes left. So the Buildkite setup is hosted under the Julia Lang Buildkite account. So we have access to like 116 agents, and a lot of them are AMD CI. But we don't use all of these because we don't have to, because I don't think we run a single SIML workflow on FreeBSD, for example. So what kind of jobs do we run on Buildkite, right? So these are typically jobs that are very heavy workloads that are either resource intensive or time intensive, or require GPUs, or they're a combination of all of these. We also use a lot of custom Buildkite plugins, for instance, for memoizing the repository, so we save on inefficient builds, and for security, for sandboxing, and all these things. Currently, we have 32 SIML repositories that run on Buildkite, but some packages use Buildkite a little more than the others, which we'll see in the usage section of this. So how do you get your repository to set up to run jobs on Buildkite? It's really simple. You just set up a new pipeline on the Buildkite's web UI. Then you set up a GitHub webhook to hook it into your repository. And once that's set up, you just need a simple pipeline file in your repository. So if you think your packages have workflows that are intensive enough to warrant running on Buildkite, please get in touch and we can work it out. Right. So now we come to the usage stats. This is a relatively new GitHub feature, which I'm glad came out right in time for my JuliaCon talk as well. So this information here is only from February 2025. So it's the last 6 months, right? So across IML, we've seen usage of little over 3.5 million minutes of CI time for Linux machines and 88,000 minutes of macOS machines. The action storage is basically what we use for caching. Ordinary DiffyQ is absolutely on top of the leaderboard with little under 900,000 minutes, with MTK closely behind with almost 800,000 minutes. MTK has had over 100 releases this last year, which probably explains this as well. Next, we also have the Buildkite usage stats. So Buildkite has had this for a while now. So this is since last JuliaCon, that's 13th July 2024. There is one package that almost hit 500,000 minutes of CI time, and I'm pretty sure it'll cross that mark over the next couple of days. I don't think there's going to be any prizes for guessing that this is ordinary DiffyQ. Of course it is, right? So I'd also like to point out SIML docs here. That's a bit of a special case because these are jobs that generate, aggregate documentation with the help of multi-documenter and finally deploy to docs.siml. Given how quickly things move in the SIML ecosystem, we want these to be up to date. So this is set up to run every couple of hours. But yeah, that's about it, and that brings me to close. If there's any questions, we can talk.
Yes, we have time for about one question. How many person hours did it take to develop this pipeline?
Oh man, so this was before Claude, so I would say a fair amount. But, yeah.
Yeah, with the ACI stuff on BuildKite, we've had some success integrating with the results test suites within BuildKite. I don't know if you're familiar with it, but it's quite good because it can track kind of flaky tests.
Yeah, so we do see that, but typically the SciML ecosystem just moves so quickly that most results just automatically get resolved by the next release itself. Most failures. So, which is why I didn't put up the statistics for the flaky tests on there.
Okay, great.
All right, we should cut off questioning right there. So, let's thank the speaker again.
Thank you.
All right, and our next speaker needs no introduction, Jeff Bezanson. He's going to be talking about the state of trim.
All right, let's see, how do I do this? That should be good, yep. Okay, where do I plug in? USB-C, yeah. Good, good.
Looks like it wants you to type something on your screen.
All right. Well, this is not what the talk is about, but it's some Julia code, though, so why not? Okay, better. Great. All right, ready to go? All right. Hi, everyone. Good to see you all. So I'm going to talk about the thing that everybody always asks me about, which is building binaries and building smaller binaries and this new trim feature that we have been working on. So I want to begin with a little history of us not building binaries, because that's something I know about. There is some relevant history. Yes, no binaries, text only, please. So what things looked like in March 2011 was we had, note the command carefully, ls*.j. So this was all of the Julia source code that existed in the world at that time. And it wasn't even in a subdirectory yet. There was, pretty soon after this, we put it in a subdirectory, which is a great improvement. But, the way the system worked was that one file start.j, every time you started Julia, it loaded that file, and that file simply included all of the others. So we just loaded all of the source code every time you started it up, which was okay when it was 200 lines, but it actually got to the point where it took about 10 seconds or so, and we actually lived like that for, I don't know, a couple of months or something. You actually had to wait 10 seconds for it to load and compile all of this code every time you started Julia. And that started getting very annoying. So we very quickly had to do something about it. So here, this is actually before even the public release, thank goodness, I put in this system image thing that you've probably all heard of. So the system image concept and terminology basically comes from Smalltalk and Lisp, where it's a very, very simple idea. And the idea is you basically just dump out the entire contents of the system and save it for later reuse. So the initial version of this was very, very primitive. I literally just traversed all of the data structures in the entire system and just serialized them to disk. And then the next time you started, we just deserialize it. And so that at least saves you all of the parsing and compiler analysis effort of putting all those data structures in place. So that basically solved the problem for a little bit of time. But this was a very primitive version of it. In particular, it only saved our data structures. It did not save the native code. So that was the next obvious thing to do. So a little while later, about 2 years later, Jameson comes along, and he has these great understated commit messages, but a static compiling prototype. So, and what that meant, there's a longer message below that, but I had to cut it off here. But what that basically means is now we are saving and reusing native code as well as the other data structures inside. So then now we didn't have to regenerate that. So there's an improvement there. And then a couple years later, we do the same thing but for packages, right? So before that, we were saving and reloading the kind of the base code, but packages you still had to load, totally separately every time. So eventually we got sort of the same thing that we had in 2011, but now for packages. So this is just very, very slow, laborious process. And then it even took a much longer time, an additional 7 years before we could save the native code for packages. And it was just very technically difficult to get that working, because when you have, pieces of native code do not like to exist in isolation because everything is referencing everything else. And so working out how to get the cross references between packages when you might be using different combinations of packages than we anticipated, and getting all the references to work and invalidating things that can't be used, and the logistics of it is difficult. So it took a while to get this working, but we did eventually, and that worked even better now. So one question is, why are we so weird about this? We're saving out about 4 different kinds of compiler artifacts at this point, and absolutely none of them are what people sort of really are used to or want from traditional languages like C or C++, like a small standalone executable or something about that. And the basic reason why we're so weird about this is traditional languages use this compilation model called separate compilation, where you look at a piece of code once on its own, save out a binary artifact, and then whenever you use it, you never look at the code again. You're basically not allowed to look at the code again. If you want to use that, you look at a header file. You can look at the header file again, and it tells you what's in there, and you go through that, but you never look at the code again. And we don't do that. We use more of what's called a whole program model, where we're always looking at all the code all the time. So when you use a library, the next time you call that library, we might look at all the code in it again, because we want to basically re-optimize it for whatever you're doing. So that has some trade-offs. That's very powerful in many ways. There are lots of powerful things you can do. You get certain performance properties that can be useful, but the trade-off is you get latency and you get big binary sizes because everything is kind of together in one big blob. So, in some sense, the Unix system image is the entire contents of usr-lib, which is probably a couple of gigabytes. It's sort of, that's the Unix system image, So but we just put that in one file, like it's sort of what's going on, So the next kind of thing that happened, which is kind of a tangent that I'll just put off to the side here, in this process of us trying to be normal about binaries, one thing we did along the way was make the compiler optional. So we at least had to decouple the large LLVM and our code gen system from the runtime. So it was at least possible to run some Julia code without the compiler, because it's a really large dependency. So if you ever wanted to have a standalone binary, you certainly wouldn't want to be tethered to the entire compiler, which is probably more than 100 megabytes. So this has now happened. So we've been gradually setting the stage to maybe build some proper binaries. And now we are really getting there. So the most recent thing in this category is this trimming feature. So what is it all about? So basically the basic idea is we want to be able to get rid of the stuff you're not using. So my program only prints hello world. I don't need the other gigabyte of libraries. So we're going to remove all the stuff you don't need. So here's basically how it works. So you mark the entry points you actually need, the things you actually need that you want to call, or it can be implicit if you're writing an executable. Obviously main is the entry point, so that's sufficient for that. Or if you're writing a library, you'll mark the points you want to be callable from C ABI with @C_callable. And so then those become your entry points. And then you put this through Julia C. We will try to prove what code is reached from those entry points. And in that process, you might get some compiler errors, because if we can't do it, we'll give an error, fix the errors, and then eventually you get a small binary. And the main use case for this these days is, well, by far the main use case is creating a library to be called from C, C++, Python. Much smaller use case as of now is executables, but that's obviously something people really want as well. And I should point out as part of this that a lot of times people wonder, oh, well, why not just use the precompiles? And it's actually very different from precompile statements because the precompile statements are sort of speculative. You're trying to sort of guess everything that might possibly be needed at runtime. And it's generally going to be way too much for these purposes. So in this process, we actually totally ignore precompile statements, and we just throw them out. And we only trace from the entry points that you specified just for this purpose. And the other thing that's interesting about it is that the particular way it works is very specific. So you might think one thing you might want to do is try to prove what code is unreachable, right? Because if I want to delete some code, ideally I should prove that that code is unneeded, and then it's safe to remove it. But that doesn't actually work because it's very, very hard to prove that something is absolutely not needed. As long as there's one thing in the system that, well, maybe it might end up there, so I have to keep it. So that sort of puts the semi-decision on the wrong shoe, on the wrong foot. You need to do the opposite kind of semi-decision for the undecidable problem. And you need to only try to prove what can be reached. And anything else that I don't know about, well, I'm just going to throw it out and hope for the best. And it's going to be your problem because the important thing is that we get a small binary. It doesn't matter if the binary works, but it has to be small. You see, that's how we've designed it. So a little more on that later. So here are just some examples of some things you might do. So if you want to write a library that's going to be called from C, you can do @C-callable and put C-compatible types for the inputs and the return, and that'll go in there. Or you can do this @main thing. So we had to add this because the name main was never special in Julia. If you say function main, that just defines a function called main. That's it, nothing else. So it would be breaking to do anything weird with main, so we added @main, which is, it defines a function, but then also says on startup this function is going to be called automatically. So it adds that behavior to this, which arguably we should have always had, okay, but we didn't, so we added @main, and it gets a string vector of the command line arguments. And as of now, it's supposed to return a C-int, just a C exit code. Maybe that's okay, I don't know, maybe it should be based on whether an error is thrown or something. Actually, if an error is thrown out of this, we will exit with code 1, so that sort of works already, but there's that. And all right, what if you do C-callable main? Well, you can actually do that as well. You can write C main and just put C-callable on it, and then that will be your C ABI main point. But then, of course, it has to use the correct C main argument signature. So you will get a C-int and a char star star, and have fun with that if you really want to do that. So one thing that came up in this is, so basically when we do the trimming process, we give errors basically for dynamic dispatch. That's the easiest way to think about it, because at a dynamic dispatch, we don't know where the control flow is going to go, so we're not sure what to include and what not to include. That's the basic idea. But very quickly, that didn't really work very well for a lot of real-world code, because this kind of pattern is very common, where someone is doing just a simple, classic object hierarchy kind of thing, where there's some possible types, and then you have a vector of maybe some different types, and we do something to all of them. And this is a pretty common pattern, and it looks very general. It's just an abstract type with some struct subtypes. Well, that's pretty general, but there are some specific things about it that matter. So usually there's a small number of subtypes. It's not 1,000. It's probably like less than 10 or maybe less than 20 or something. And there's a method that has a concrete signature defined for each one. So that's also important, because inside each of those area methods, since the signature is concrete, those are probably very type stable and very statically compilable. So those are all sort of perfectly innocent, easy to compile methods. And so then if I call one of those, it turns out this kind of has to be allowed in some way, because just way too little code works with trimming unless you allow something like this. So is this allowed? And so yes, this is actually allowed sometimes. So basically it has to fit this pattern. There have to be kind of not too many methods, and they all have to be concrete. Then we will go through and compile all of them. So the question is, okay, what if there were 1,000 subtypes of it? Maybe you do actually want us to compile all the methods for all 1,000 subtypes. So in that case, we currently use a heuristic for this. In that case, that's an upcoming work item that you'll see. We want to be able to support that, but there'll have to be some kind of a configuration option or annotation for that. So you can tell us, no, really, I really want you to compile this for all 1,000 types. So that's kind of a work in progress. So all right, here's sort of a to-do list of some stuff that we have done over the past year or so, and then things we will do hopefully soon. So yeah, getting JLLs working was a big one, because there, of course, that's any binary dependency you have, that has to work, and they didn't work initially, but we got them working. So yes, handle some of these sum type things, which was a big roadblock for a lot of applications. Another big issue was the show function, because anytime we print something, we usually tend to print its type. And printing types, it turns out, is very, very dynamic, and itself very not type stable, because types have basically untyped vectors inside them of their parameters, so we don't know anything about what is in there. And basically, we don't specialize the printing code on every type, even though we could, because that just seems pretty excessive. So we don't bother to do that. So we had to write a basically statically typed version of this, so you have a fair shot at being able to actually print something, which people often want to do. And then supporting finalizers, that was an interesting one, because when you register a finalizer for something, the function is not called at that point, obviously. It means that function is going to be called by the runtime sometime later, right? But so that means we need to include it in the binary, but there's no call to it in your code, right? So that requires a special case. And it actually has to be done pretty carefully, because one way I thought we could implement it is, okay, when you see a call to finalizer, just pretend the finalizer is called at that point, right? Just like as if there was a call there. That might be how you might do it, but it turns out that doesn't work, because if you do that, then the compiler, the optimizer, thinks that that thing actually is called in there, and then it assumes that sort of those things are happening at that call site, but you don't want it to make those assumptions because it's not really true. So it's not very accurate to tell the compiler that that call is happening there. So you want to handle it a little differently. So it's a little bit subtle. Another cool thing that Gabriel and Cody added was basically automatic JL init. So this makes using libraries way, way nicer, because you don't have to tell someone, oh, by the way, before you call our functions, you have to call JL init. Very annoying. So now it's basically automatic. You can just give someone, libm written in Julia, they call sign, and it just automatically works, which is really, really cool. So yeah, that was cool. And of course, we've got CI now for both correctness and size. So if this of course has happened. If the hello world binary gets bigger than a certain size, we want CI to fail. So we have that now. And this is going to be released. It's still labeled experimental, because we're not sure about some of this design, but it's going to be released in 1.12, and it's labeled experimental, but it's totally usable. So yeah, a few things upcoming that we need to do. So weird standard in doesn't work, which might seem like a pretty weird omission, but libraries don't really need to read from standard in, so it just hasn't been very important. Tasks are very similar to finalizers, and we just have to do the same thing for tasks that we did for finalizers. And yes, this configurable sum type limit that I mentioned. I think also the logging is also very, very dynamic. It turns out we have a very, very complicated logging system, and it doesn't work with this, unfortunately, so we have to find some solution to that. And tooling. So if you saw Shuhei and M's talk about the new language server, that is perfectly suited to helping with this. So basically, there will be a mode where you can say, okay, I would like this to be trimmable. Tell me everything in my code that makes this not trimmable. And it's a very similar analysis, but it's actually not exactly the same analysis that you always want, because, like, for example, sometimes you care about type stability, but type instability actually by itself does not prevent something from being trimmable. So you want a slightly different tailored analysis for that particular problem. And also, so there's this JuliaC script, which for now is just sort of awkwardly stashed in the contrib directory, which is not great, but that's just sort of a place where you can find it for now. We should figure out some better way to package it and properly install it. And it's basically, it's similar in spirit to what Package Compiler does. Package Compiler is basically a thing that builds artifacts with a kind of API type of interface, and JuliaC does it with a command line interface. They should have basically equal functionality, but just different style of interface, so they should be basically fully combined into just one thing, or if you can either choose to use it from Julia or from the command line, as you prefer. And yeah, if you're generating libraries, you probably also want to generate header files for people. So generating header files or whatever binding code is needed for the calling environment would also be very, very nice and convenient. And then, of course, the build infrastructure, so you can, if you want to write a native library in Julia, you can automatically get builds going on GitHub. So that's a bunch of stuff we have to do, and there's, yes, a lot of good hackathon items in that list. So, all right, more broadly though, yeah, what's next for binaries? So in maybe, I don't know, hopefully next year, maybe in a couple years, if I were to add to that series of commits in the beginning about improvements to building binaries, so some things that are coming up is being able to basically get a private copy of the runtime with your library, possibly statically linked into it. And we've got some hacks in objectfile.jl that now make it possible to do that. And that's useful because you can get something that's hopefully more self-contained. If you can give someone one file, that's better than giving them 2 or 3. And also you can load more than one of them in a process. So if you currently, if you build one of these and you try to load this in a Julia runtime, it will not necessarily work if you try to load more than one of them. Because each one sort of thinks it's a system image on some level. So the system image expects to be kind of the only one in the process. So you can't have more than one. But if you give each one of these its own private copy of the runtime, then in its own little world, it thinks it's the system image and it's happy. So that lets you do this. But it's pretty primitive because you have to basically interact with them using ccall, which is pretty unusual to call Julia with ccall, but that's how it would be. But it does at least get you these things. It at least gets you these things for a little while. Another thing we're planning to do is just use compression on the system image data, which should be sort of an easy win. And in fact, it's mostly implemented already. And of course, just ongoing work on shrinking the footprint and making more things in the language work. And I think it's possible there could be different ways to do trimming. So this is just complete speculation, but I think there will probably be a lot of programs where the call graph control flow based version is just never going to work because it's just too dynamic. And I think there are other things you could do, like for example, basically look at all of the identifiers that are referenced in the program. And as long as you never try to fabricate a symbol by constructing a string and evaluating it, as long as you never do that, we might be able to figure out that certain entire types or functions are never used and we can remove those. So I think that might be an alternate approach that could be possible. It would be nice to have to do some experiments on that and see how well that works. And then the really big item, the one I'm kind of excited about, is the prospect of implementing kind of real separate compilation where you can have separately compiled Julia code, but that will share a single runtime, which is better in many ways. And this actually we don't have this feature yet, of course, but it's actually slightly underway because Jameson put in this very under the radar, inconspicuous commit that basically doesn't change anything user visible at all. So I don't expect anyone would have noticed this. It's very under the radar, where he basically made every method in the system is now inside a single data structure, where they used to be kind of sharded out among types and everything. Now they're in one data structure. And well, why does that help? Because if you're going to have really separately compiled things, in the Julia world, what that means is each artifact has its own completely isolated view of what methods exist. So those need to be totally isolated from each other. So one of them could be using like a totally different definition of integer plus than another one, and they wouldn't interfere with each other, right? So that means you need to have all the methods that exist encapsulated in one object. And so that has already been done. So that is actually one step along the way, and that's done. So we're getting there. And yeah, you would basically, if we have these, you would load and invoke them just like ccall. So you can do it now with ccall if you have one of these @ccallable entry points. In the future, it'll be like some kind of invoke type of command, like invoke inside compilation unit kind of thing. So if you know about what we do now with these so-called frozen worlds, where sometimes we run code in a fixed world where it can't see new methods, this is basically a general version of that that's far, far more usable and scalable. And yeah, you'd have, with a shared runtime, you'd have a shared GC heap, shared thread scheduler, so much more efficient. They could even reference each other's objects and so on. So this is kind of a goal. I don't think it's super hard to do. I think it's doable. I hope we get this pretty soon. And then of course there's some stretch goals like doing things like cross-compilation and targeting different kinds of platforms, and these are very speculative sorts of things. So this is kind of what I'm thinking about, and that's it.
Very exciting talk. Are there questions?
Hi, was just wondering if you could also add to the to-do list. So you added some extra code for JL init, so you can use it as a shared library on C++ or whatever, see? Could it be possible to do a similar trick so you can generate Python extensions and MEX files?
Yeah, I mean, so everything can call C, so yeah, you can eventually make that work, yeah.
Well, those are special entry points used for Python extensions and MEX files. That will be quite useful, so you can just start building libraries for Python and MATLAB, but in Julia.
Yeah, I think adding, nice Python and MEX interfaces is just a matter of sort of grinding it out, because once we do this, it just becomes like calling C.
Okay, thanks.
Yeah, I wanted to ask if there's a possibility that in places where there's type instability, you don't know which methods are going to be called in a certain place, that you can add some sort of profiling mechanism to the static analysis, so that you basically say, I know what's statically reachable, but in the places where I would usually give up, I know from this test run that only these 3 types appeared in this place, and so I'm just going to use those and fail for the rest.
Yes, so you can do things like that. Actually, one thing you could do is take your precompile statements and just search and replace precompile to entry point, and then we will include all those things. So that might include more than you need, but it will take care of anything that was in your profile run will then be included. And so you could do that, and we have the trim unsafe option, which it does exactly the same thing, except we just don't print any errors. So if you're very confident that you've covered everything that's needed at runtime, then you can just turn off the errors and we'll just generate it anyway, and you can try your luck. So it is possible to do things like that. And there's a whole bunch of things you can do with type unstable code. Like sometimes we will actually turn a call site into an if statement where we break out some cases, or there are all sorts of things you can do to make some of those cases work. But yeah.
Did you want to comment on the dynamic dispatch tracing that got added in the upcoming 1.12 and whether that integrates with the trim option yet?
Well, I think that's similar to like the precompile tracing, or yeah.
A missing feature that we talked a little bit about this is basically a localized unsafe. We've talked a little bit about this, like say, want everything to be safe, but I know that this specific place is giving an error. You put like add ignore or something on that function, and it then when it's verifying, it says, okay, this function, the user said they don't care about it, and then potentially it makes the experience a little less unsafe. It's still, and by unsafe here, what happens is if the method isn't found, it throws a method not found error. So it's not gonna necessarily blow everything up. It's a pretty well-defined behavior what happens when you don't have the code.
And I think we have time for at least one more.
Yeah, thank you for the nice talk. So I've actually been trying for a while to, we have some nice Julia code and we want to make it accessible to our colleagues, and so I want to wrap it in some, let's say, pip installable kind of package. And one thing I've noticed during the last months is that it's for me always actually quite unclear, what you can do and what you cannot do yet with the Julia C, and so you always end up kind of implementing something and trying it out. And actually the runic .jl was kind of one example where you can see, which you wrote, as kind of a nice reference point to see what is possible. But I would really love if there was maybe one kind of reference program like Runic, and then maybe going forwards, just as kind of a sort of documentation to see what is already possible, and also what kind of a reasonable build process would look like, getting this kind of Julia to Python or to C or whatever. So this is maybe more like a wish or a request or an appreciation for the documentation is already there, and yeah.
Yes, totally. Yeah, recipe books are always good. We should have recipe books and as much automation as possible. And it's it can be a little bit hard to predict what will work, but we have the growing list of like common pitfalls, things to look out for. Is kind of all you can do for now.
All right, with that, just for the reasons of time, we should call it quits. Let's all thank the speaker again. And, you know, he'll be around, so feel free to ask more questions then.
Thank you, Tim.
Thanks, Jeff.
This likes to fall. Keep an eye on it.
All right, our next speaker is Jacob Krell, and they'll be talking about speculator reduced latency in a single line of code.
I gotta switch my settings 1 second. There we go. Okay, great. Yeah, my name's Jacob. This is Speculator. So gonna assume you know the problem with latency. So here we have various techniques to deal with that. We have the static method where we're doing static completion. We have the manual precompile calls, which we don't really want to deal with ever. The very popular precompile tools, and then this other category, speculative, where we have precompile signatures and speculator here. I will say precompile signatures predates speculator, and I found out after I was mostly done. There are some differences, but I encourage you to also check out that package if you're interested in this one. Yeah, so here's a single line of code. This is the package precompilation for speculator. It's niche in its use case, but we can kind of get into why soon. And this is the main function that you're going to be interacting with. So we have the main speculate function, and you give it a value. This value can be a module or anything callable, and it's going to search that for methods that it can just compile. And during that search, you might want to avoid certain names or types or modules or whatever, so you can provide this predicate, which allows you to skip that. These other commands lets you run it in the background fed. You can do a dry run if you set compile equals false. We'll go into limit shortly, but that prevents you from generating methods with too many concrete specializations. If you set the path to anything, it will write these directives to the file, and the verbosity is just the logging behavior. So it only depends on interactive utils, so loading time's pretty fast, and so we're gonna define a method. We can handle abstract types and union types, but not union all types. And so if we call speculate on that with the limit is 2, then you can see it compiles both of those individual specializations. If we'd set the limit to 1, then that would exceed it, and it would do nothing in that case. If we call it again, this time we provide a filter. You can see that it's not identifying the string method, and it does identify that the method with char is already precompiled, so it's it tells you it passed on that one. The searching itself is fast, so with every single loaded module in Julia, it will search all of them in less than 2 seconds in this particular example. So your real, the performance bottleneck is just compilation itself. If someone has performance problems, I'm sure there's ways we can optimize it, but it seems like a minor concern. A novel feature that we implement is here. So I think at the REPL we have a lot of time where we're not actually doing anything. We're typing, or we're thinking, or petting a cat, and I think a REPL can use that time more efficiently. And so it'd be nice if we just hit enter and it compiled. So you can do that here. Will that save you time? Probably not. Do I think it's cool? Yes. If you can think of a smarter thing to do with all of that idle time, let me know. I think that would be cool. So the next couple slides are going to be pseudocode of just the general algorithm that I'm using to identify these compilable methods. So if we get that all modules value I showed, we search every loaded module. For each module, we search every name and value within it. first checking the predicate, and then every time we get anything else, then we generate the compilable methods from that. In the signatures, we'll get into find types soon, but we get the Cartesian product of the concrete types of the methods, and then we check the limit. If it exceeds the limit, we ignore it, we move on. Otherwise, we'll process the signature, which most of the time will be called to the compilation or the logging. This finding types, if it's concrete, then we're good, we just keep that. If it's annotated with no specialize, then that's also compilable, good, we keep that. If it's uninull, we don't want to handle that. I don't know how to handle that, sounds like a lot of work. And for abstract types, like I mentioned, we also filter those on the predicate using the module name and the name of the type that you're getting it from. Yeah, so in conclusion, you can use this as package compilation. I would say not very often. If you're just getting something set up, you want something quick and dirty, go for it. It's not going to add loading time, and you might catch some like strongly typed methods you put there. If you have a bunch of dynamic, like abstract methods, this is not going to be very helpful for you. You can also use this in your startup file. Yeah, that's all we got. Do we have any questions?
Question.
First of all, not a question, but Tim, 2 years ago we talked about it'd be really neat if someone did this. So thanks for doing this.
I think I saw that issue, right?
I might have been, yeah. Yeah, thanks for the talk. I had two quick questions. One was, do you find an issue with the fact that precompiles are entry points, usually for dynamic dispatches, and many entry points may be statically reachable, and so like, do you end up with redundant code problems where like if A calls B calls C calls D, and then you end up precompiling all of those, but you could have just precompiled A, then do you get like redundant code in there? Is that an issue?
I have not measured that, and I believe there's some internal behavior that can very quickly just tell me, no, this is already done. If you run this with compile on, and then you run it a second time with a, like if you do it on base, the second time will go super quickly. But perhaps there is some gains to be made there.
Cool, no, that's great. And the second question was just, is it possible to generate entry points for trim rather than just precompile statements?
I have no idea.
Okay, cool, thanks.
Thank you.
Any others? All right. Well, I'll ask. So I guess the issue that Nathan was asking is about the redundant ones. It's presumably just the level of almost the text parsing, right? Because you won't compile anything more than you need to, right? So in other words, if you compile a method and one of its callees, but inference would do that for you, that second precompile statement will essentially take no time, presumably, right? I mean, so precompile just does the.
If it's a real call, then basically like the compiler caches it anyway. So the compiler is already doing the caching behind when you call compile or precompile, and so if you call precompile twice, the second one does nothing. Well, it doesn't do nothing, but it's basically nothing. So there shouldn't be any issue if you do like compile A that compiles B, and then you do compile B. It's going to take like a microsecond to check, oh, I'm already being compiled, but there shouldn't be any issues. And regarding it about the native code, if the code doesn't get inlined on A, then yes, there's already a native code. But for example, if B was inlined in A and you asked B to be precompiled, it might be that you also now generate an entry point into B. it's a little questionable if that's worth it or not, and there's some heuristics that work around this, which are not great, so your mileage may vary.
All right. Well, just for reasons of time, we should move on. Let's thank the speaker again. And so our next speaker is I'm sorry, we'll mangle your name. So maybe
Satoshi Terasaki.
Very good, thank you. Much appreciated. And we'll be speaking on Let's Read the Julia documentation in your preferred language.
Okay. Okay, let's get started. Hello, my name is Satoshi Terasaki. This is a link to this slide. Please scan in advance. And today I'm going to show my Julia package named Doctrine Translation that is related to the title of my talk. Let's read Julia documentation in your preferred language. Why my talk exists? Julia is sort of the two language programs. This is fast and it is easy to write code like Python. This is great. I want to more people to use Julia. I like Julia and I want more people to use Julia. But this is I have one question, one problem. When you want to learn something about Julia, we need to install English in my brain. This is not a joke. Let's try. Okay, let's install English in my brain. Let's learn English. Error happens. Sorry, English, because I'm Japanese, English is difficult for me. This happens yet another two language problems. Okay, joke is over. And, I know we are in America. There are lots of people who can speak English. So if you are one native speaker, no problem. If you are good at reading English, it's okay, I think. But in this case, you is me, and this block, I fall into this block because my this language is not equals to English, so it takes a lot of time to understand documentation written in English. If I could, I want to read documentation in Japanese in this case. Because this is why I need to explain the why. The number of Japanese who use English there is limited. We Japanese use Japanese to read, write, listen, discuss something in Japanese. So that's why I created the docstring translate.jl package. Just translate docstring into any language. Okay, let's try translate the simplify function. If you want to know about the EX function, what is EXP? I know the explanation function. According to the docstring, it computes the natural basic expansion of x. In other words, e to the x. Okay, let's translate Japanese. Goma-chan, could you do this? Okay. Here's the result. To reproduce my result, we need to prepare OpenAI API key because it works OpenAI behind the scenes. And please add my package, docstring translation. Just add package, add docstring translation. The key concept is my package is the switch lang ban macro. We specify JA. JA means language code of Japanese. We can set as Japanese or Spanish, Hindi, anything. So the result is out to be something like this. Let's compare the original and the translated one. As you can see, it is translated into Japanese and while keeping Markdown structure. Okay, let's see another example. Okay. This is not a joke. Let's start. Load docs translation, switch lang to Java. Sign function is translated. If you want to eigenfunction, the Spanish output, and Hindi we got. Okay, this is not a joke, and demo is over. Okay, you may wondering how it works. I'm hacking, actually I'm hacking docs.parsedoc, the docstring method. This is a main line I modified. In this line, I inject a translation engine. Here, this is a markdown object. This MD is passed to translate docstring with OpenAI MD. The left-hand side is a translate result. The object is assigned to d.object. It works. For more details, please refer the actual implementation. Actually, this is so messy. So actually, this method overriding the existing method is called type piracy. So this is not good practice, but benefits outweigh drawbacks. This is a trade-off. Here is an example displaying eigenfunction, the docstring of eigenfunction in Spanish. Here is a result of displaying docstring of eigenfunction in Japanese. So if you teach something to Japanese, please use this package. And the application, you may be wondering, we have shown that we can translate docstring into any language. You may be wondering, can we translate documentation built with documenta.jl? So answer is easy. Let's see the example. This is docs/make.jl. doc/make.jl. So this is special function. This comes from special functions. We only have to insert the 3 lines of code. Just load docstring translation and switch line ban macro. This is just technical reason. We do not have to ignore. We don't have to insert it. Okay, here is a result of translation of documenta.jl based documentation. The left-hand side explains the gamma function. This is original edition. The right side shows a translated Japanese translated result. It is translated and keeping markdown structure. Okay, so furthermore, we can translate the official junior documentation in any other language. Let's see. I have prepared lots of lists. Let's see. Français. Okay. you can see, if you know about Francais, this is translate in Francais. Les calculs, sorry, I can't. So, désolé, monsieur, je ne parle pas français. So, when I touch the performance tips, it jumps translated page, not original one. So we can learn Julia language in French. Likewise, go to Japanese. We can learn Julia in Japanese. Okay, and my documentation, my doctrine translation adapts OpenAI backend. Technically, we can inject any kind of translation engine. I have prepared lots of various packages. If you have time, please use this. Okay, let's summarize my talk. I introduce a doctrine translation, enable machine learning support for documentation. I believe it solves yet another two-language problem. Thank you. Please try my package.
We are actually a little over time, so I might have to ask people to hold their questions, but thank you for an amazing demonstration of what you can do when you hack into the internals of some of these systems. So this actually concludes our session, although the next talk is very compatible with our goals of this symposium. Is there somebody else introducing the next speaker? You are? Okay, yeah, great, yeah. Oh, I am. Okay, all right. So I'll introduce it. So the tooling session is officially over. So let's first take a moment to thank all of the speakers. It's been a really fantastic set of talks. Very high impact. So thank you all for participating in the symposium. I guess I get the great honor of introducing Cody Tapcott, who's works at JuliaHub, and Cody is going to be talking about a topic certainly near and dear to my heart, that is, what can we do about invalidations?
Great, okay. Can everyone hear me okay? Great. Can you see my slides? Great, okay, cool. We've only got 10 minutes, and I think we've definitely spent a lot more than that already talking about invalidations in the past. So all I'm hoping to share with you guys today is a bit of a fresh perspective, looking at it from another angle and saying, if we stop looking at type stability so much as an issue, what else can we find out about the invalidation problem, and how might we be able to tackle that? So first thing we should do is kind of start to hone in on this problem. One issue that can happen a lot that I think people have hit in the open source ecosystem is when you extend methods where you shouldn't. This frequently causes invalidations because no one else is extending that method. There's maybe just one generic definition in base, and then you provide the second one, and a large portion of the ecosystem invalidates. This can happen, for example, if you accidentally provide the one argument version of hash instead of the two argument version. Really subtle, but really important if you want to avoid these kind of latency problems. The issue that I want to focus on today is going to be the second issue here, which is when you're actually doing everything right. Like the author of the package said that you're doing the right thing. They wrote their code knowing that they might dispatch the method that you're providing. You're not committing type piracy, and yet we still got invalidations. So we're trying to kind of look at the happy scenario here where the user should be able to do everything they want, and yet somehow they have trouble having their cake and eating it too. So then we're going to be talking, in order to get to that, we're going to necessarily have to start looking at type unstable code. Type stable code is great. By no means, we've got nothing against it. That's awesome, but not every code can be type stable. And Julia makes it really easy to write type unstable code. It's one of our biggest kind of marketing pitches. So we want to make sure that this works well for users. And right now, the reality is you can easily end up invalidating, even if you're following all the rules, just if you have type unstable code. So yes, it's true that type stable code mostly doesn't have this problem. But today we're going to say, actually, you wrote type unstable code, and we want that to work for you as well as it possibly can. So where does this actual invalidation end up happening? Well, there's a whole pipeline of the compiler where we go from your source code to specializing this function and then evaluating a call that ends up invalidated at some point later. For what we're talking about today, we mostly don't need to worry about that pipeline. The key detail is that at some point we do something called call resolution, where we end up evaluating, in this case, a call to convert that knows you're passing in the specific type string, but what it doesn't know very well is the second argument, which is any type at all. And so the compiler here might look up the list of methods that match. And this is a pretty wide call. Any can match any type in the system at all. But in this case, we'll say that the compiler got lucky. I mean, this is totally fictitious here, but we'll say that it matched only 2 methods. And then everything else it knows would be a method error. So the idea here is that the compiler can compile those 2 methods, and then it can kind of speculate and say, man, I hope that this doesn't match anything else in the future. Boy, would that be great, because I've already got all the code you need. And if it's wrong, then you invalidate. And that's kind of where the root source of this problem here is, that you end up with wide calls in your code, and then we hope that the small list of methods we got back remains small in the future, and it doesn't. So let's look a little bit at that in more detail, especially as it applies to like multiple functions calling each other. So here you can see here that we start with one body of code calling another body of code, and that call starts out static. And then what happens is maybe someone else adds a new method here. So we had one match at first, but this is designed to be extended. So we have some wide signature like the one we were seeing before, and now we get a second method in that list. Okay, the compiler says, you know what, 2 methods, I can still manage with 2 methods. That's not too bad. So it adds a union split in your code. That's a fancy little optimization, but it basically means that we now have 2 dispatches, or 2 invokes of the static methods that we know might be there. And we say, great, let's hope that it's really just 2 now. You added 1, that was already not great, we invalidated code. Let's hope we don't have to do it again. And then it does happen again, so now we get a full-blown dynamic dispatch. And we're like, oh, this sucks. I don't know anything about the type of any of these functions that they're returning. It's much slower than a normal invoke of this code. You know, a normal Julia developer, I think, would look at the code type and say, oh, this is not good, we shouldn't end up here. But I think if we zoom in to what happened here, we actually might conclude a little bit the opposite. So if you look at the life cycle of what happened here, remember we started from the assumption your call is going to be wide. It's going to have many callees. So in a way, we expect this scenario to happen with many callees. So we started from the scenario with just one callee, and we added one and we got an invalidation, and then we added a couple more, and we got more invalidations. And we got to this point at the end where we had the dynamic dispatch. And at the stage where we have the dynamic dispatch, your code is now the slowest it will ever be. In fact, invalidations only ever add a ton of JIT latency to slow down your code compared to what it used to be, but so that it can have new functionality in terms of being able to call new targets that it couldn't call before. So that's really interesting. It doesn't feel like a great position to be in, but it's actually exactly where we want it to be, because if we think about it here, you have many callees. We know that this code is going to be type unstable. So in a way, that dynamic dispatch was the right thing to do. In fact, if we go back to look at the code again, and look at these side by side, we said, oh, look, static dispatch to a single callee, that's great. That's a single invoke. That's great for performance, but it was actually the wrong code to emit, because I knew you were going to end up with lots of callees later. And so in reality, that code was the code that we couldn't use at all. We pre-compiled it, and then it was useless. And the code that was useful was the quote-unquote bad code, which is this dynamic call to many callees. And so that's a very interesting perspective, is if you accept the type instability, then the problem is actually about understanding when you can eagerly say your method list is going to stop growing, or when you can say, actually, we expect this to be extended by people in the future. So for type unstable calls, we have to kind of guess about this. And if it guesses wrong, we get invalidations. So if that's kind of the premise here, that's the core speculation that's going wrong, then what can we do about it? You know, like if this is our perspective and this is the specific form of invalidation we're trying to fix, what can we do? I'm not sure. We're not going to tackle all the options here, but there is a couple I think I want to put in front of you, and a couple of options that I think people have talked about that may or may not solve this problem completely. One is that we could try to just disable world splitting. World splitting was that case where we have this really wide function call. We have a little bit of it matching on a couple specific types, but the majority of the call is totally uncovered and unimplemented. And in that case, sure, you could do that, and maybe for the convert code, we're okay with giving up some performance there. But I think that overall, this optimization is actually quite important for 2 reasons. One case is that it's very common to have functions that are really not extended at all. Internal functions in a package, for example, that you create for yourself, you just create a function, some internal function name. You maybe created your own little type hierarchy here with an abstract type and created your own types under it, but you never actually expect this to be used by someone else.
So these methods are never going to get extended, which means that if the compiler is able to do what it can do today right now, where on the right-hand side it looks at that internal bar call, and it may not know very much about obj. All it knows about obj is that it's some abstract object, which sure, right now that's just type 1 and type 2, but later when we add other types, it could be all sorts of other things. So the compiler doesn't really know very much anything useful about obj. But what it can say is, I know that there are exactly 2 implementations of internal bar, and they both return string. So all of a sudden, out of something that was effectively super type unstable, basically any, we got back down to a really type stable return type, which is the string type here. And that's something that happens all the time in internal package code, and I don't think we want to just give up that optimization completely, because this would cause the reverse problem now, where we kind of assume everything might be extended, and in the frequent case where it isn't extended, we now pay a huge performance cost that doesn't give any benefit to the user. There's another problem here too, which is that it doesn't solve the unexpected specialization problem. This is a case where you have a call, like a call for show type, and this is technically covered by a generic implementation, like a default implementation provided by the package, or in this case, a default implementation in base. And then you might want to allow the user to override that. Sometimes that's very intentional. Sometimes the generic implementation is just an error that says, hey, you're supposed to implement this. And so we want to also be able to allow generic implementations to be overridable, but maybe not all of the time. I think show type is a case where we may not want to allow this to be overrided, but a lot of users do want that, and I think our ambiguity about, is this allowed and the compiler is going to expect you to do it, or is it not allowed and you shouldn't be overriding this generic implementation, that ambiguity is something we pay for a lot in the form of invalidations. And I think there are definitely lots of cases in the ecosystem where we do want to support this kind of overriding. So for that reason, also, I don't think that disabling world splitting alone is enough to solve this problem, because we do see this a lot in other packages. The other solution here, I mean, very hand-wavy, but we could just try to cache more aggressively. However, my response to this is really just a general level of compiler skepticism. I think that like a lot of the experiences we like to provide for the users are inherently dynamic with brand new code. We've got revise working, we have REPL working, and we can try to save a lot of the effort that your compiler does, but sometimes your compiler just does brand new work. And it's definitely a huge additional cost if a significant fraction of that brand new work we're doing is wasted work because I didn't know that you were going to end up throwing it out later just to extend a type unstable call like we talked about earlier. So I think more caching is great. It might cause some improvements, but I just don't think it's going to get us all the way there to solving this problem. And so then finally, I think the main option remaining is to try to improve this heuristic directly. We could try to add some smarts to the compiler, but I'm not quite sure what we'd want to do. So I think the main thing we might want to consider would be to give the compiler a hint. Right now, what it does basically is that it checks whether or not you have a certain number of matching methods, and if it's below that number, it can manually optimize and then say, add a little marker to say invalidate if this ever changes. But I think what we really want is something more like the ability to say, will this thing ever see new methods? And then we can jump straight to that dynamic call if we know that you're going to end up extending this interface. And I think this has been, I know that this has been brought up before in the ecosystem. Like if we had interfaces like static languages do, then we wouldn't have this problem. And I think there's some truth to that, but I also think that there is some design space that we haven't explored yet, which is in particular that we don't need type information to make this do the quote unquote correct thing here. Like our dynamic call is already slow, and we're already happy with it after the invalidations. The problem is the invalidations that we have to pay in order to get us to the slow dynamic dispatch. And so we don't need type information. All we really need is a single bit of information, which is, are you going to be putting new methods here or not? And then if you have type information, that's great. Like then I could use that to say, oh, you not only promised me that you're going to put new methods here, but any of the methods you put there are going to return string. That's even better. Now I can optimize this and give it a better ABI. I don't have to box the return type every time it comes back out, for an example. But that's not required to avoid the invalidation. That's just required to optimize the ABI when we call into it. So this is my idea about, I think, the direction we should potentially explore in. But more importantly, I think the big takeaway here is that if we're going to accept type unstable code, I think there's a fundamental issue about guessing whether or not we're going to see extension, like new methods in different parts of the method table. And when we get that guess wrong, we pay the cost in form of invalidations. And so the real question is, how can we start to guess that right? And that's it. That's my talk.
So first, actually, I don't remember. This is the last talk, I think, right? So I'm not going to be aggressive about cutting off questions this time. So did I see? Did you, Stefan? Okay, yeah.
Could we? It seems to me that the problem with invalidation here is that you then have to recompile all the code.
Yeah.
I mean, my immediate thought is like, is there a way to patch the existing code? But I guess part of the problem there is that a lot of the type inference that you did is probably wrong at that point.
Yeah, we do lose a lot of type information. I think the main thing, yeah, I think there are some big design questions to figure out there. I'm a little bit skeptical that you could get that to solve all these kinds of issues, but it would certainly be nice to have an extra tool in the tool belt. The other thing that would be particularly nice is that one of the things that gets brought up in this space is that, for example, we can't really use interfaces because if we add an interface with a type assertion in base, then it wouldn't be backwards compatible. But if we had something, for example, like on-stack replacement where we could just drop down to an interpreter and leave the compiled path with the type assumptions in it, then that would be a huge improvement. And then you just have like an optionally enforced interface that gives a hint. Like if you want your code to be compiled, compile with the interface. If you don't care about being compiled, then do whatever you want.
Well, I mean, yeah, I guess one version of that is that you compile the code assuming that there's a limited number of methods, but in such a way that it will work correctly if there are more methods. So then you sort of have the fast path code, but you also generate the slow path code at the same time. So then you don't actually have to invalidate because it'll still work. It's just slow.
Yeah, we can do that. I mean, the way you described it is easy. I think the hard part is to know which methods you want to include. And then when you're still giving up type information when you do that because of the else branch. And that's still a big
Well, one of the branches has bad type information and the other one has good type information.
Right,
I don't
but
know if
then they
that's
merge.
helpful,
And
but, yeah.
I just mean that it's still, like you don't get the case where we talked about here, where we can world split, for example, in your internal code, and I get good type information with just string coming out of this. I don't get to recover that type stability anymore if I do that.
I think the worst thing about that is it makes it sensitive to the order in which you load packages and define methods, which ones get good performance and which ones get crappy performance. But, you know, we're in a space of playing trade-offs, so.
Yeah, I wanted to ask about exactly this example because, I mean, you don't have to use an abstract type, right? I mean, you could define struct type 1, type 2, and then do a const union abstract object of both of the types if you really wanted it to be final, and that would do away with the problem because then it, like... Okay, yeah, because I mean we had this long Slack thread yesterday, and I made my opinion there clear already. But I feel like if it was really disabled while splitting, then okay, yes, probably some code would run slower than it currently does. But I feel like it would not be hard to fix, and it would be very predictable to fix the places where it hurts you. I feel like, but. Yeah. I mean, it's hard without any numbers about any of this, right? Like, probably it would be good to do some kind of measurements on real-world packages and, but yeah, I don't know if that was not really a question, just an observation about this thing. That
No, I can comment on that. This, first of all, you're right that this example is something you could pretty straightforwardly optimize. If this really is the whole, world of concerns that you have just right here, you could rewrite that as a union type. And then secondly, I do actually agree with you. I think that the world splitting optimization is something we should try to see, like, what are the exact costs of turning it off? Where in the ecosystem do we start to run into, bad trade-offs there? This is mostly here to say that, like, there's a good chance it won't get us all the way there, and that we are really benefiting from this if we just look at a few examples. And we expect users to kind of write code like this. And so it would be nice if we come up with another solution that doesn't end up paying off type stability and the quality type inference that we have today.
Hi. Like, you brought out the convert example, and like, for me, I guess I don't have a super clear mental model of invalidations yet, but like, convert in base already has like a ton of methods, right? So if you're adding a method to convert,
in like some package, like, are you going to invalidate anything? Like, it feels like anything which is already a dynamic dispatch is going to stay a dynamic dispatch, and so it wouldn't have to be changed?
So it depends on the exact call site. Convert may not have been the greatest example. I haven't actually checked how many methods for convert to string specifically that we have in the system by default. I actually don't think we have very many conversions to string, which might make this invalidate, but you're totally correct that if it's a common conversion target, then you might already have enough methods in the system that we go straight to the dynamic dispatch case, and then we're already kind of doing the right thing. Yeah, it's going to depend on the particular type that you're converting to and those kind of details.
And how much type information you can successfully extract from the call site. So.
Absolutely, yeah.
Yep.
Would you talk about the viability of disabling world splitting for code gen, but keeping it for type inference, and then invalidating only if somebody defines a method which returns a different type?
I think I understand the proposal. I'm not sure I can give you an off-the-cuff answer about how I feel about it, but it's an interesting idea. We should talk about it more afterward.
Cool, thanks.
Yeah.
I was curious about the case where if you had a specific, like 4 or 5, which is more than you're kind of looking at number of types, and then after that you want to go to dynamics dispatch, and where you could even be, you know enough about the types you have, you could order the types so that this is the 90% case or 50% case, and this is a 30% case. You want those to be dispatched by if else. Otherwise, you go into the dynamic dispatch. Would there be a possibility to have something where you could specify that? So it's kind of like just a union, but there's a possibility it has to go to dynamic dispatch.
Yeah, I see. You're asking whether we can optimize specific callees that we expect to be more frequent than others. Maybe the default implementation is like a hot target, yeah. Sure. Yeah, I think that's a very reasonable thing to explore as an extension to something like trying to give an explicit source text hint of these kinds of interfaces to the compiler, where we expect this kind of extensibility and you want to provide it, like let it know that you got a hot callee that's going to be more frequent than others. I also feel that that probably goes in the bucket of like, these improve the performance beyond what we already get today. Because what it does is you get to that dynamic dispatch, and then now that dynamic dispatch performs better than it does right now, which would be great. I think those improvements are awesome, but they're not the invalidation problem. Yeah. Yeah, exactly. Yeah, I do think that would solve another pain point for users. Yeah, absolutely.
Okay, I have just been informed that despite this being the last talk, we do need to cut this off. I imagine some of our very helpful AV people actually need to go home at some point. So with apologies for extending your workday, let's again thank Cody, and thanks to you all as well. Have a wonderful evening.
Oh, and I have a